everyone. Welcome to the 2020 TensorFlow Developer Summit Livestream. I'm Megan Cacholia, VP of Engineering for TensorFlow. Thanks for tuning in to our 4th annual Developer Summit and our first ever virtual event. With the recent developments of the coronavirus, we're wishing all of you good health, safety, and well-being. While we can't meet in person, we're hoping the Dev Summit is more accessible than ever to all of you. We have a lot of great talks along with exciting announcements, so let's get started. When we first open sourced TensorFlow, our goal was to give everyone a platform to build AI to solve real-world problems. I'd like to share an example of one of those people. Erwin is a radiologist in the Philippines and no stranger to bone fracture images like the ones that you see here. He's a self-proclaimed AI enthusiast and wanted to learn how AI could be applied to radiology, but was discouraged because he didn't have a computer science background. But then he discovered TensorFlow.js, which allowed him to build this machine learning application that could classify bone fracture images. Now, he hopes to inspire his fellow radiologists to actively participate in building AI to ultimately help their patients. And Erwin's not alone. TensorFlow has been downloaded millions of times with new stories like Erwin's popping up every day. And it's a testament to your hard work and contributions to making TensorFlow what it is today. So on behalf of the team, I want to say a big thank you to everyone in our community. Taking a look back, 2019 was an incredible year for TensorFlow. We certainly accomplished a lot together. We kicked off the year with our Dev Summit, launched several new libraries and online educational courses, hosted our first Google Summer of Code, went to 11 different cities for the TensorFlow Roadshow, and hosted the first TensorFlow World last fall. 2019 was also a very special year for TensorFlow because we launched version 2.0. It was an important milestone for the platform because we looked at TensorFlow end-to-end and asked ourselves, how can we make it easy to use? Some of the changes were simplifying the API, settling on Keras and eager execution, and enabling production to more devices. The community really took the changes to heart, and we've been amazed by what the community has built. Here are some great examples from winners of our 2.0 Dev Post Challenge, like Disaster Watch, a crisis mapping platform that aggregates data and predicts physical constraints caused by a natural disaster, or Deep Pavlov, an NLP library for dialogue systems. And like always, you told us what you liked about the latest version, but more importantly, what you wanted to see improved. Your feedback has been loud and clear. You told us that building models is easier, but that performance can be improved. You also are excited about the changes, but migrating your 1.x system to 2.0 is hard. We heard you, and that's why we're excited to share the latest version, TensorFlow 2.2. We're building off of the momentum from 2.0 last year. You've told us speed and performance is important. That's why we've established a new baseline so we can measure performance in a more structured way. For people who have had trouble migrating to 2, we're making the rest of the ecosystem compatible so your favorite libraries and models work with 2.x. Finally, we're committed to 2.x core library, so we won't be making any major changes. But the latest version is only part of what we'd like to talk about today. Today, we want to spend the time talking about the TensorFlow ecosystem. You've told us that a big reason why you love TensorFlow is the ecosystem. It's made up of libraries and extensions to help you accomplish your end-to-end ML goals, whether it's to do cutting-edge research or apply ML in the real world. There's a tool for everyone. If you're a researcher, the ecosystem gives you control and flexibility for experimentation. For applied ML engineers or data scientists, you get tools that help your models have real-world impact. Finally, there are libraries in the ecosystem that can help create better AI experiences for your users, no matter where they are. All of this is underscored by what all of you, the community, bring to the ecosystem, and our common goal of building AI responsibly. We'll touch upon all of these areas today. Let's start first with talking about the TensorFlow ecosystem for research. TensorFlow is being used to push the state-of-the-art of machine learning in many different subfields. For example, natural language processing is an area where we've seen TensorFlow really help push the limits in model architecture. The T5 model on the left uses the latest in transfer learning to convert every language problem into a text-to-text format. The model has over 11 billion parameters and was trained off of the colossal clean crawled corpus dataset. Meanwhile, Mina, the conversational model on the right, has over 2.6 billion parameters and is flexible enough to respond sensibly to conversational context. Both of these models were built using TensorFlow. And these are just a couple examples of what TensorFlow is being used for in research. There are hundreds of papers and posters that were presented at NeurIPS last year that use TensorFlow. We're really impressed with the research produced with TensorFlow every day, at Google and outside of it. And we're humbled that you trust TensorFlow with your experiments, so thank you. But we're always looking for ways to make your experience better. I want to highlight a few features in the ecosystem that will help you in your experiments. First, we've gotten a lot of positive feedback from researchers on tensorboard.dev, a tool we launched last year that lets you upload and share your experiment results by URL. The URL allows for quickly visualizing hyperparameter sweeps. At NeurIPS, we were happy to see papers starting to cite tensorboard.dev URLs so that other researchers could share experiment results. Second, we're excited to introduce a new performance profiler toolset in TensorBoard that provides consistent monitoring of model performance. We're hoping researchers will love the toolset because it gives you a clear view of how your model is performing, including in-depth debugging guidance. You'll get to hear more about tensorboard.dev and the new profiler from Gal and Schumann's talks later today. Researchers have also told us that the changes in 2.x make it easy for them to implement new ideas, changes like eager execution in the core. It supports NumPy arrays directly, just like all the packages in the PyData ecosystem you know and love. The tf.data pipelines we rolled out are all reusable. Make sure you don't miss Rohan's tf.data talk today for the latest updates. And TensorFlow datasets are ready right out of the box. Many of the datasets you'll find were added by our Google Summer of Code students, so I want to thank all of them for contributing. This is a great example of how the TF ecosystem is powered by the community. Finally, I want to round out the TensorFlow ecosystem for research by highlighting some of the add-ons and extensions that researchers love. Libraries like TF Probability and TF Agents work with the latest version. And experimental libraries like JAX from Google Research are composable with TensorFlow, like using TensorFlow data pipelines to input data into JAX. But TensorFlow has never just been about pushing the state-of-the-art in deep learning. A model is only as good as the impact it has in the real world. This is one of TensorFlow's core strengths. It has helped AI scale to billions of users. We've seen incredible ML applications being built with TensorFlow. We're really humbled by all the companies, big and small, who trust TensorFlow with their ML workloads. Going from an idea to having your AI create real-world impact can be hard, but our users rely on TensorFlow to help them accomplish this. That's because the TensorFlow ecosystem is built to fit your needs. It makes having to go from training to deployment less of a hassle because you have the libraries and resources all in one platform. There's no switching costs involved. I want to highlight a few new things that will help you get to production faster. First, you've told us that you love working with Keras and TensorFlow because it's easy to build and train custom models. So we're committed to keeping tf.keras the default high-level API. But if you're not looking to build models from scratch, TensorFlow Hub hosts all the ready-to-use pre-trained models in the ecosystem. There are more than 1,000 models available in TF Hub with documentation, code snippets, demos, and interactive collabs, all ready to be used. When you're ready to put your model into production, you can build production-ready ML pipelines in TensorFlow Extended to make sure your ML engineering just works, from data validation to ML metadata tracking. And today, I'm very excited to announce that using TensorFlow in production is getting even easier with an exciting launch: Google Cloud AI Platform Pipelines. We've partnered with Google Cloud to make it easy to build end-to-end production pipelines using Kubeflow and TensorFlow Extended, hosted by Google Cloud. Cloud AI Platform Pipelines are available today in your Google Cloud console. And if you're running TensorFlow on Google Cloud, TensorFlow Enterprise, which we announced last year at TF World, gives you the long-term support and the enterprise scale that you need. Finally, you can train and deploy your models and pipelines on custom hardware specifically designed for AI workloads, cloud TPUs. In the latest version, TensorFlow is now optimized for cloud TPUs using Keras. This means the same API you started with now helps you scale to petaflops of TPU compute. All of these libraries are within the TensorFlow ecosystem, are 2.2 compatible, and help you scale so your ML application can reach your users. But for AI to have that kind of impact, it needs to be where your users are, which means getting your models on device. Now, we all know this requires working in some constraints, like low latency, working with poor network connectivity, all while trying to preserve privacy. You can do all of this by using tools within the TensorFlow ecosystem, like TensorFlow Lite, which can help make your models run as fast as possible, whether it's on CPUs, GPUs, DSPs, or other accelerators. Here's an example of how we've optimized performance for MobileNet V1 from May last year to today. It's a big reduction in latency and something you get right out of the box with TF Lite. We're also adding Android Studio integration so you can deploy models easily. Just simply drag and drop into Android Studio and automatically generate the Java classes for the TF Lite model with just a few clicks. When network connectivity is a problem and you need these power-intensive models to work while still offline, you can convert them to run better on device using TensorFlow Lite. In the latest version, we rebuilt the TF Lite converter from the ground up to provide support for more models, more intuitive error messages when conversions fail, and support for control flow operations. The browser has become an exciting place for interactive ML, and TensorFlow.js is allowing JavaScript and web developers to build some incredible applications. There's some exciting new models that are now supported, like Face Mesh and Mobile BERT. Hugging Face introduced a new NPM package for tf.js, which allows you to do question answering directly in node.js. Finally, the new WebAssembly backend is available for improved CPU performance. The next few years will see an explosion of platforms and devices for machine learning, and the industry needs a way to keep up. MLIR is a solution to this rapidly changing landscape. It's compiler infrastructure for TF and other frameworks. And it's backed by 95% of the world's hardware accelerator manufacturers, and it's helping to move the industry forward. We see how important infrastructure like MLIR is to the future of ML, which is why we're investing in the future of TensorFlow's own infrastructure. The new TensorFlow runtime is something you won't be exposed to as a developer or researcher, but it will be working under the covers to give you the best performance possible across a wide variety of domain-specific hardware. We're planning on integrating the new runtime later this year, but you'll hear more from Mingxing later today. So to recap everything you've seen so far, whether you're pushing the state-of-the-art in research, applying ML to real-world problems, or looking to deploy AI wherever your users are, there's a tool for you in the TensorFlow ecosystem. Now, I'd like to invite Manasi on stage to talk about how the ecosystem is helping empower responsible AI. Thank you.
Thanks, Megan. Hi, everyone. My name is Manasi Joshi, and I'm an engineering director on TensorFlow team. As Megan mentioned and you saw, TensorFlow ecosystem is composed of a number of useful libraries and tools that are useful for a diverse set of use cases, whether they are coming from ML researchers or practitioners alike. However, the field of ML and AI is raising the question whether we are building systems in the most inclusive and secure way. I'm here to tell you how TensorFlow ecosystem empowers its users to build systems responsibly, and moreover, what type of tools and resources are available to our users to accomplish those goals. Before we deep dive into the details of what TensorFlow has to offer its users, let's take a step back and define what we mean by responsible AI. As we know that machine learning has tremendous power for solving lots of challenging real-world problems. However, we have to do this responsibly. Now, to us, in TensorFlow, the way we define responsible AI is based on a 5-pillar strategy. Number 1, general recommended practices for AI. This is all about reliability, all the way from making sure that your model is not overfitting to your training data. It is more generalized than that. Making sure you're aware of limitations of your training data when it comes to different feature distribution skews, for example. Ensuring that the model outputs are robust when the training data gets perturbed. Ensuring you're not using only a single metric across all your models to determine its quality, because different metrics matter to different contexts. How your model is used for promotion, demotion, filtering, ranking, so on and so forth, right? The second principle, fairness. Fairness is a fairly evolving thing in AI. For us, we define it as not to create or reinforce unwanted bias. Fairness can be extremely subjective, can be context sensitive, and it is a socio-technical challenge. Third, interpretability. Interpretability is all about understanding the mechanics behind models' prediction, ensuring that you understand what features really matter to the final output, which features were important, which features were not. Fourth, privacy. For us, this is all about taking into account sensitivity of your training data and features. And fifth is security. In the context of ML, security really means that you understand vulnerabilities in your system and the threat models that are associated. Now, for a typical user of TensorFlow, this is how the overall developer workflow looks like. You start by defining a specific goal and objective for why you want to build the system. Then you go about gathering relevant data for training your model. As we understand, data is gold for machine learning model training. And so you have to prepare the data well. You have to transform it. You have to cleanse it sometimes. And then once your data is ready, you go about training your model. Once the model is built, it's converged, you then go about deploying the model in production systems that want to make use of ML. Deployment phase is not a one-time task. You have to continuously keep iterating in an ML workflow and improving the quality of the model. Now, along this developer workflow, there are many, many different moments at which you as a modeler needs to be asking all of these questions. Questions like, who is the audience for my machine learning model? Who are the stakeholders, and what are the individual objectives for the stakeholders? Going on to the data side of it, is my data really representing real-world biases or distribution skews? And do I understand those limitations? Am I allowed to use certain features in a privacy-preserving way, or they are just simply not available due to constraints? Then on to the training side of it. Do I understand implications of the data on model outputs or not? Am I doing deployments very blindly, or am I being a little bit mindful about deploying only reliable and inclusive models? And finally, when we talk about iterative workflow, do I understand complex feedback loops that could be present in my modeling workflow? Now, along all of these questions, I'm happy to tell you that TensorFlow ecosystem has few set of tools which could be helpful to answer some of them. I'm not going to go through everything here, but to just give you a few examples, starting with fairness indicators. It's a very effective way by which you can evaluate your model's performance across many different subgroups in a confidence interval-powered way, such that you can evaluate simple but effective fairness metrics for your models. We have what-if tool that gives you the notion of interpreting the model's output based on the features and changing those features to see the changes in the model's output. It has very compelling textual as well as visual information associated with your data. And then finally, TensorFlow Federated. It's a TensorFlow 2.x compatible library that helps you train your models with data that's available on device. Kat and Miguel have a talk later today that dives deep into fairness and privacy pillars of the responsible AI strategy. Be sure not to miss it. We are excited to work on this important part of TensorFlow ecosystem with all of you, the TensorFlow community. And now, to talk more about the community, I would like to turn it over to Kamal. Thank you.
Thank you, Manasi. Hi, everyone. My name is Kamal, and I'm the product director for TensorFlow. So you've heard a lot from Megan and Manasi about our latest innovations. Now I'm going to talk about the most important part of what we're building, and that's the community. And I want to begin by thanking all of you. Your feedback, your contributions, what you build, this is what makes all of this possible. We have an incredible global community. We love hearing from you, and we really appreciate everyone that came out to a roadshow of our TensorFlow World last year. And going into 2020, I want to take some time to highlight more opportunities to get involved in the community and new resources to help you all succeed. Let's start with ways you can get involved locally. One great way to connect is to join a TensorFlow user group. These grassroots communities started organically, and we now have 73 of them globally. We launched the first 2 in Latin America after the roadshow in São Paulo, and now we expanded our presence in Europe. The Korea group is the biggest with 46,000 members, and China has user groups in 16 cities. I'm sure this map can have a lot more dots, so if you want to start a user group, please reach out and we'll help you get started. Another way to get involved are the special interest groups, or SIGs. SIGs exist to help you build areas of TensorFlow that you care the most about. We will have 12 SIGs, with SIGs Graphics being our latest addition starting at the end of the month. Most SIGs are led by members of the open source community, such as our fantastic Google developer experts. We love our GDs. We now have 148 of them, and I want to take a moment to recognize all of them. They give tech talks, organize workshops, and doc sprints, and I want to give a special shout out to Hason, pictured above, who organizes Doc Sprint in Seoul. They reviewed several PRs and wrote hundreds of comments in 5 hours. Again, GDs are amazing, so please let us know if you're interested in becoming one. Okay, so TensorFlow user groups, SIGs, and GDs are great ways to get involved, but we all love a little competition, and we all love Kaggle. As Kaggle now supports 2.x, we've had over 1,000 teams enrolled in our last competition. I want to give a special shout out to our 2.0 prize winner, Deep Thought. And speaking of competition, we saw great projects in our last DevPost challenge, including Psychopathology Assistant, an intelligent assistant that tracks patients' responses during face-to-face and remote sessions. And everyone danced faster, and everybody danced now video generation library using HTPU and TensorFlow 2.0. Thank you to everyone who participated. And today, we have a new challenge. So Manasi spoke earlier about how TensorFlow can help empower all users to build AI systems responsibly. So we want to challenge you to create something great with TensorFlow 2.2 and something that has the AI principles at heart. We can't wait to see what you build. So another area that we're investing in a lot is education, starting with supporting our younger community members. For the first time, we participated in Google Coding, and it was a success. We were very impressed by the students, and we want to thank all the awesome mentors who made this possible. We hope someday to see the students at our Summer of Code program. I love Summer of Code. It's an awesome opportunity for students to work with TensorFlow engineers. We saw amazing projects. In fact, one of the data visualization for Swift, which is still being used today by our team. So I'm happy to announce we're doing it again this summer, and we're excited to see what new projects students will work on. Programs like this are key to the growth of the developer community, so please visit the Summer of Code website to learn more and apply. We also want to help produce great educational content, starting with our machine learning crash course, a great resource for beginners. So today we launched an updated version of the course. Our NGDU team completely revamped the programming exercises using Keras 2.0 and made them much simpler in the process. Go check it out on this link. And we want to provide resources at every stage of learning. At the university level, we want to empower educators and support them as they design, develop, and teach machine learning courses. Last year, we supported Georgia Tech, the University of Hong Kong, Pace University, and many others. And this year, we have a commitment to fund schools from underrepresented communities in AI, historically Black and Latinx colleges and universities. So if you're a faculty and you want to teach ML, please reach out. And we also want to help people self-study. That's why we partner with deeplearning.ai to give people access to great educational material. To date, over 200,000 people have enrolled in our courses. The Data and Deployment course is a great specialization course that covers TensorFlow.js, TensorFlow Lite, TensorFlow Dataset, and more advanced scenarios. This is a great option for people who are really looking to build their ML coding skills. And you can audit it for free. And there's more. Imperial College London just released a Getting Started with TensorFlow course on Coursera. This course was created in part by the TensorFlow funding I mentioned earlier, and we're super happy to see this. So you're taking all these courses, you're becoming better at ML, but how do you show your expertise to the world? This is why I'm excited to announce the launch of the TensorFlow Certificate Program, an assessment created by the TensorFlow team, covering topics such as text classification, using NLP to build spam filters, computer vision, using CNN to do image recognition, sequences and prediction. By passing this foundational certification, you'll be able to share your expertise with the world and display your certificate badge on LinkedIn, GitHub, or the TensorFlow Certificate Network. And to widen access to people of diverse backgrounds and experiences, we're excited to offer a limited number of stipends for covering the certification costs. You can find out more at tensorflow.org/certificate. So, a lot of things to do. And I want to thank you again for making the TensorFlow community so awesome. As you've seen, the TensorFlow ecosystem is having incredible impact in the world today. And what it really comes down to is how AI is helping make people's lives better. That's really what inspires us as a team to build all these amazing tools. So I'd like to end by sharing one final story.
Médecins Sans Frontières is providing care in 70 countries. Each time we go in a new country, in a war zone, we discover more and more patients infected with multi-drug-resistant bacteria. They're arriving with the wrong antibiotics given to them. Antibiotic resistance is everywhere. If we don't act today, we'll have 10 million deaths per year by 2050. Once you identify that there is a bacteria, you do multiple tests to know which type of bacteria it is, and then you test the sensitivity of several antibiotics in order to identify the most effective one. There is an additional step that is the interpretation of those results. In the majority of the countries where we work, there is a lack of microbiologists and human resources to do this interpretation step.
Anwar, he is 10-year-old, and his injury was a bullet. It exploded inside his leg. He has very resistant type of infection. We are the last hope for Anwar.
I thought AI might be one of the solutions to this problem.
We developed an application to help lab technicians to interpret the results of diagnosis tests only using their mobile phones. We're using TensorFlow, computer vision, and machine learning to detect interactions happening between the bacteria and antibiotics based on an uploaded image of the petri dish. Our goal is not to replace the lab technicians. The app is really meant to support them in doing their diagnosis test, whilst always keeping a human in the loop. We managed to train a model within a matter of days using Keras and 15,000 anonymized pictures of diagnosis tests. The API was super expressive, and it was surprisingly really quick and easy to achieve. We are deploying the app using TensorFlow Lite, so it can be used offline on any range of mobile devices in all of our clinics.
Today we have a prototype. We've got a responsibility to make the diagnostic test available, easy, affordable, all over the world. I'm excited because, for me, this application can be a game changer that's going to help millions and millions of people.
For anyone, there is one antibiotic suitable for this infection. I think this app, it will solve many problems everywhere in the world.
That's just amazing and incredibly inspiring. When I see something like this, it makes me very proud to be building TensorFlow. So go build amazing things, and we'll be there to help. And with that, I'll pass it on to Paige to kick off our day. Thank you.
Hi, my name is Paige Bailey, and I am here today to deliver the talk of Carmel Allison and Yash Kataria, who unfortunately couldn't be here today. But for the purposes of this talk, just imagine that I am Carmel. So to get started, my son is in kindergarten, and he's just starting to learn to read. And one of my favorite parts of this process is that even before he could reliably decode words, he started to produce them. And of course, doing what I do, I can't help but be amazed at how similar his learning process is to a neural net's. The rule set for spelling and grammar is so complex in English that we rarely present a set of instructions that he can follow. Instead, he starts almost randomly with letters and sounds, and then he gets feedback from me and from other readers in his life, which he incorporates. Some things he memorizes, some are lucky guesses, and somehow over months of learning, he's started to form a consistently interpretable mental model of written words. And he produces mostly understandable text. So here you can see I was eating breakfast with my cousins and my sister. I've been particularly fascinated by my son's learning here because it happens to align with what many of us have started to call an NLP revolution. We have enough data and enough tools that we've started to rapidly push the cutting edge in natural language understanding and related tasks. I've heard it said that with text today, we're at a Cambrian explosion, like when ResNet was first published. We're at the beginning of this faster than expected progression of language models. So we're going to take advantage of all of this research and tooling, and we're going to teach a simple neural net to generate the next word of a phrase. And we'll use this to tell a robot children's story. So the first thing we need is data, and we're going to take advantage of the children's book test corpus released by Facebook. This data set is a set of Creative Commons children's books that have been converted into a series of passages and fill-in-the-blank style questions about each passage. From this model, we just need the raw book text, which looks like what you see here. As an aside, these books are out of copyright, which means they're often old, and that means the corpus is full of literature that's problematic by today's standards. I'm going to gloss over that for the sake of this talk, but if you go and actually use this data set, please do consider what cultural norms you might be teaching your machine learning models. So first, we're going to load the data. Now that we have a corpus, we can load it into our Python interpreter and start playing with it. Here we use the text line data set to load the data, and we can simply print out a few lines to see what we have. So tell me what you notice here. It looks like we have some cleaning work to do. So using our data set, much like we would use a NumPy array or Pandas data frame, we can filter and map transformations across it. Here I'm dropping those pesky book titles and filtering out punctuation within each row. And after that transforming, I can print out a few lines to check and make sure the data looks as expected. Now I have a data set where each row is a sentence of arbitrary length. And I've decided I want to train a windowed model to predict a new word given some words to start. So I need to take these data set rows and make them all equal length. Once again, without leaving TensorFlow datasets, I can split, flatten, and regroup my rows so that each row is a set of 11 words. But I want that last word in each row to be a separate label. So I just define a simple row-wise function or pop out like my labels, and voila, we have pairs of examples and labels. But there's still a problem with this data. Why can't I just feed this into a dense network or any arbitrary model? Well, it's words. Machine learning models don't speak English. And of course, the problem with this data set is that we need numbers. Only numbers, not lions, just numbers. So we're going to need to transform our input sentences into numeric representations. And the way that we do this is with pre-processing layers, which are highly exciting and a new addition to TensorFlow 2. So pre-processing layers were recently reviewed as part of the Keras API specification, and they're a set of layers that take care of data transformations that are outside the training path. These follow the same APIs as normal layers and can be called and composed just like layers. They play nicely with TensorFlow datasets as well, so you can parallelize pre-processing transformations. And importantly, just like normal Keras layers, these become part of your model and therefore get serialized in the save model and become part of inference to prediction, which is critical to minimizing training serving skew. This is the set of pre-processing layers that is already complete. They are experimental in 2.2 as we ensure that the APIs match how you use them, so please check them out for all of your pre-processing needs. So now we know how to get our data into the correct format, and the next step is to build a language model that can learn a representation of all of these words so that we can generate text on the fly. One of the classic models used for text translation and generation is a sequence-to-sequence model. A sequence-to-sequence model typically has two parts, an encoder that uses RNN blocks to encode input data, and a decoder that borrows state from the encoder in order to correctly predict the target outputs. Now, sequence-to-sequence models have some complicated moving parts. It's not a simple feed-forward network, and there are a lot of parameters to keep track of. But luckily, we don't have to go it alone here. TensorFlow Add-ons is a community-maintained repository built on top of TensorFlow 2 that provides especially complex or experimental layers, optimizers, and other utilities. And one such utility is the seek-to-seek package, which provides a number of layers and classes that make building sequence-to-sequence models much easier. And you'll see me use these throughout this example. Because the architecture of the sequence-to-sequence model is fairly complex and requires special state passing, we're going to subclass the Keras-based model and build our network explicitly. We start here with the text vectorization layer we've already discussed, since that's going to be what we feed our input data through to convert it to indices. After we vectorize the inputs, we're going to pass them through the encoder blocks, first in embedding, then in LSTM. And you'll note that in our init function here, we're just configuring the layers, and we're not actually passing any data through them yet. In Keras, each layer has two stages: the construction, when you parameterize your layer, as seen here, and the calling of the layer, which will come later when we pass our data through. The decoder is somewhat more complicated, but here we can leverage the TensorFlow add-on sampler and decoder and set up the decoder LSTM and connect it to the projection layer, which is our final dense layer that maps to the vocabulary we want to predict, plus 2 tokens for predicting calls in out-of-vocabulary words. The final set of layers we will set up are a pair of attention layers. There is a large and growing field of attention research and machine learning, but given the time constraints of this talk, I'm only going to give you a very hand-wavy explanation and say, attention is a technique that allows the model to track intermediate states as it steps along sequences, and it'll allow the model to give more weight to certain time steps of a sequence when predicting the final word. Here, we use a simple dense attention layer that comes with TF Keras, and you'll see how we connect this between our encoder and decoder in a minute. So we have a lot of state to pass between our encoder and decoder, which means we can't just use the standard Keras fit call. And one of the things I'm most excited about in TensorFlow 2 is that we have refactored and cleaned up the Keras training loop, and we've made it much more modular. So instead of overriding the entire fit loop or throwing it out altogether, I'm just going to define a single forward pass for my model in this special function, train step, and that is going to get called by model.fit with each step. So we overwrite train step in our encoder-decoder model. That train step is going to get one batch of data at a time, so we just need to define the forward pass for that one batch. And the first thing we do here is unpack our data and separate the example from the label. You'll note that we call our own vectorization layer here to ensure that our input strings get correctly transformed to indices. Next, still inside our single training step, we're going to record our forward pass under a gradient tape. Anything that needs to be backpropped through should go under here. So while the vectorized layer, a pre-processing layer, was out of the tape, our encoder, embedding, LSTM, and so forth all belong under the tape. And here we pass our inputs through the set of layers we defined in our init to encode them. We also set up our attention layers to track the intermediate state coming out of the encoding layers. And next, we decode, which is to say we try to predict our targets using the state from our encoder. The decoder here will go over the many epochs it runs for, train its own weights separate from the encoder weights, and in concert, the encoder and decoder will learn to predict text based on the outputs. And now that we've run all of our layers and necessary to form the forward pass, we can compute the loss and collect the outputs of this step so that they can be optimized. The Keras model takes care of collecting variables and setting the optimizers, so we just choose how we want to pass things through here. As the final step, we collect and return the metrics we set in our model. The next step is to pick an optimizer loss and accuracy metric for our model. And these are going to govern the actual training and optimization process. And we select them from a bunch of independently parameterizable options that are built into TF-Keras. And then we train. It might take a while to convergence, so I throw in a model checkpoint callback to make sure I can save my model weights as I go. We can monitor progress as we train, and our goal is to reach some degree of convergence of the reported accuracy. And with this model, this happens somewhere around 45 epochs at about 70% accuracy. And 90% accuracy is pretty good, but we might ask ourselves, can we do better? And the parameters I chose when training were thoroughly arbitrary, copied from somewhere on the internet. Maybe the model should be bigger or smaller. Typically, we spend some time tuning these model parameters to ensure that we have the best results for a given model architecture. We call this process hyperparameter tuning. And notably, easy hyperparameter tuning is one of the most requested features for Keras. And good news, we have a package for that. Keras Tuner was released last October, and it works with TensorFlow, Keras, and even scikit-learn. It allows you to create hypermodels that encode tunable parameters, distribute through your training, and state the model for others to use. So let's take it for a quick spin in order to tune some of our model's parameters. For example, let's say we wanted to tune the number of RNN units in our model. We can import the pip installable Keras Tuner package and then define a function that takes a hyperparameter object and uses it to build and compile our model. Inside this function, instead of passing in a fixed int for RNN units, we can use the magic int selector object, which will allow us to try any integer in this range. There are a number of different selectors you can use here, including floating point numbers and enums. We can then define a tuner algorithm for searching our hyperparameter space and use the tuner to build and fit our model intelligently across that space. Because we overwrote train step with our custom functionality, everything works within the Keras ecosystem. And the tuner will be able to call .fit just like we did to get the correct training behavior. The tuner will run through all of the different hyperparameter combinations you've configured, and it even works with Colab and prints out trial information as you see here. And after a few tuning sessions, we see that, in fact, the best RNN unit count is 1024. And rerunning with 1024 units, we improve our accuracy. And now we have an even better model that gets above 90% accuracy. So now that we have a trained model, of course, our goal was not just to create it, but to actually generate text. So how do we take the model we've built and use it to write a sentence? The first step is to use our model to predict one word given the length of the input, which is exactly what we trained the model to do. Just as we did with train step, we can overwrite predict step to define the operations on just one batch of data. And our predict step, we run the inputs through the same encoder and decoder we saw with training, but now with fixed weights. We can also throw in some custom logic here, and we allowed the model to predict from the top n choices instead of always the most likely word. And we also convert back to the actual English word rather than just returning the numeric indices. We can try this out, and we see that indeed we produce the next predicted word correctly. But of course, we don't want single words, we want a whole sentence. So we can go further and define a custom predict that just takes a single string and then generates one word at a time to continuously append to that starting string and generate a much longer string. And lo and behold, we can generate vaguely meaningful statements. It's not perfect, and it's entirely unpunctuated, but it can be a lot of fun. And unlike Carmel's 6-year-old, It doesn't lie and happens to like telling funny stories. And doesn't get tired. You can see that there is a little bit of punctuation that is vaguely human understandable, even though the model is quite simple and the data is relatively small and constrained. And indeed, the model we just built is the very first baby step of text processing, and it is heavily restricted by having it fit onto slides. But these same tools and techniques are used to build some amazing large-scale models that run at Google scale. So if you're interested in moving from just learning to sending emails and going big with text in TensorFlow 2, check out some of the code that researchers and engineers at Google have released, including the TF text repository and Keras BERT, as well as Keras Transformer, which is an example of a truly cutting-edge NLP model. You'll also hear more about TF Hub in the next talk, so stay tuned. So to summarize, use TensorFlow datasets and preprocessing layers to transform your inputs. Check out TensorFlow add-ons to special use layers and utilities, subclass Keras models for complicated training pipelines, tune your hyperparameters with Keras Tuner, and don't forget to check out the entire ecosystem of NLP tools built on top of TensorFlow. So thank you so much to the author of the presentation, Carmel and Yash, to the illustrator of the presentation, the artist responsible for all of these drawings, and to all of you who are listening online. Very excited to talk about all of these TF Keras and TF text improvements. Thank you.
Hi, my name is Sandeep Gupta, and I'm a product manager in the TensorFlow team. I'm going to talk to you about TensorFlow Hub. I'm presenting this work on behalf of my colleague Gus and our Europe-based TF Hub team. So when you want to apply ML to solve a problem, you first need a suitable model. And now everyday powerful new models are published in research papers or in blog posts. So let's say you read about one of these, and you want to see how great it is, and you want to try it on your problem. So you search for more details, and you might find the model code repository somewhere. Sometimes the pre-trained model is right there. Sometimes it is stored on some other storage. Sometimes you may need to download and run a script to get access to the model. So as you do this, you have many questions. How do I use this model? Is it safe? How was it trained? What was the data? Am I using the correct version? This is where TensorFlow Hub comes in to help you. So tfhub.dev is the place for all your TensorFlow model needs, to easily find the latest ready-to-use models with documentation, code snippets, and much, much more. So TensorFlow Hub's rich repository of models covers a wide range of machine learning tasks for all of your common ML needs. For example, in image-related tasks, we have models for image classification, object detection, image augmentation, and also image generation, such as for style transfers and more. For text, we have state-of-the-art models like BERT and Albert. We have universal sentence encoders and many more embeddings that can support a wide range of natural language understanding tasks, such as question and answering, text classification, semantic analysis, and many more. We also have video-related models, which can help with video action recognition, such as gestures, and also video generation. And now we have recently added audio models for things like pitch detection. So we've invested a lot of energy in making models in TensorFlow Hub be easily reusable for composing new models for transfer learning for your problem. With one line of code, models can be pulled into your TensorFlow 2 code for retraining with your own data. Now, this works whether you are using the high-level tf.keras API or the low-level APIs. This can also be used in your training pipelines through TensorFlow Extended. Recently, we have added support for models that are ready to deploy on all platforms where you use TensorFlow. These pre-trained models have been prepared for a wide range of environments which run across the TensorFlow's ecosystem. For example, you can use TensorFlow JS models for web and node-based environments. You can use TensorFlow Lite models for your mobile and embedded devices. In TensorFlow Hub, you can also discover ready-to-use models for the Coral Edge TPU devices. These devices combine TensorFlow Lite models with a fast and efficient accelerator, which helps companies create models that perform really fast inference on the edge. You can learn more about this platform at coral.ai. So today, we have more than 1,000 models available with documentation, code snippets. And for some of them, there are also simple demos that you can try interactively. These models can be easily found by searching or exploring the TensorFlow Hub repository. Now, many TensorFlow Hub models also have an interactive Colab notebook that links directly to the model page, which lets you play with the models with code examples right from your browser. And this is all hosted on Google's infrastructure, so you can be getting started with nothing to install. So now that we have seen what TensorFlow Hub is, let's take a look at a couple of examples and see how it can help you solve your problems. So the first example I'll show you is about style transfer. So here, let's take a look at how TensorFlow Hub can do artistic style transfer that can work on arbitrary painting styles using generative models. So let's say you have an image of this yellow Labrador shown here, and you would like to imagine it in the style of your favorite painter. So you can find a style transfer model on TF Hub, as shown at this URL. And then you import the TensorFlow Hub module, and you can download this model from its URL with these lines of code shown here. And now you have the model is ready for calling inference on your image, and you get back the stylized image as shown here. You can get more details of this example at the URL shown on the bottom. The second example we'll take a look at has to do with text classification. So let's look at how you can use a model with a layer from TensorFlow Hub that you can use and train your own model. So imagine you want to participate in a Kaggle competition that's related to text classification. Now, for text problems, you usually start with a text embedding, which is a way of converting raw text into a more useful structured numeric representation that a neural network model can take in. Now, training your own embeddings can take a lot of time and data. The good news is that TF Hub has multiple embeddings in many languages that are ready for your use. So with TensorFlow Hub, you can pull any of these pre-trained embeddings with one line of code. Here we are importing one of these embeddings as a Keras model layer, as you see with that last line there. And now this Keras model layer can be incorporated in the rest of your TensorFlow 2 model training code using standard Keras APIs by adding additional layers and then calling the model training and the compile and fit functions. So you can see how easy it is to build a powerful custom text model on top of a pre-trained embedding directly from TF Hub. Another thing I wanted to highlight is that TF Hub also helps bring these models to life in a very interactive way. So some of our publishers have created custom components that highlight the amazing work of these models, which you can try out directly in the browser on your own image or on your own audio clip without having to download or install anything. Before I close, I want to show you some of the recent improvements and additions on TensorFlowHub.dev. So first, as our model collection on TF Hub has grown, we have greatly improved the search and discovery feature on TensorFlow Hub to make it easy for you to find the model that you need. So you can filter by model type. You can filter by model formats or deployment targets. For example, if you need a model to run on mobile or in the browser, you can find them easily and quickly. You can also use these filters to specifically find models that are fine-tunable on your own data. Also, we have done a lot of work to support the variety of TensorFlow deployment formats. So for TensorFlow Lite, we now support additional metadata along with the TF Lite model file. This metadata stores useful information about the model, such as its version number, its input outputs, and also its class labels, etc., which makes managing these models in your mobile applications much, much easier. For TensorFlow JS, we are excited to announce 2 new models today for face tracking and hand tracking, which are built by our MediaPipe team. These models enable some really cool interactive web applications, and in future, we will be adding more text models for web use cases. Lastly, TensorFlow Hub is powered by the TensorFlow community. When we first launched TensorFlow Hub, we used it as a platform for sharing Google-authored models, but now we are beginning to share models from many more publishers, such as Microsoft, the Metropolitan Museum, NVIDIA, and many, many more. For example, very recently, we completed a TensorFlow 2.0 Kaggle question answering challenge competition, and we are happy to announce that Kaggle has published all of the winners' models on TensorFlow Hub. Now, with over 1,000 state-of-the-art models from an increasing number of organizations, you can find models that cover a much wider range of machine learning tasks and data sets. So to everyone who has helped contribute models to TF Hub, a big thank you. If you are interested in publishing your models, we are now accepting submissions. We are in the early stages of building out our third-party module collection, and our focus is still on adding high-quality models with strong documentation. And we are very interested in helping people share reusable pieces of ML models with the wider world. So if you would like to share your models, please visit the link shown here or find it on our website. So that's it about TF Hub. Thank you so much for watching. And with that, I would like to hand it over to Gal, who will tell us more about TensorBoard. Thank you.
Hi, everyone. My name is Gal Oshri, and I'm a product manager on the TensorFlow team. I'm here to talk to you about collaborative machine learning with TensorBoard.dev. Machine learning often involves collaboration, where you exchange ideas with the team, post questions on Stack Overflow, share your code on GitHub, and publish your findings to the broader research community through papers and conferences. In all of these, there's something you're expressing about what you've done, potentially through visualizations. For example, it is common to share experiment results in papers through various charts. But it is also common to include this type of information when asking for troubleshooting help. In this case, someone posted an issue on GitHub asking why they're not achieving the expected results alongside a screenshot of their TensorBoard to explain what's going wrong. The problem is that pictures don't convey all the information. For example, you might want to show what other metrics are being tracked, how many trials were run, or let the reader explore the model structure in more depth. Even when the code is released, it can require quite a bit of setup before the results can be viewed. So how can we make this easier? Well, we already have TensorBoard, which is TensorFlow's visualization toolkit. It is commonly used by researchers and engineers to understand their experiment results. It lets them track metrics, visualize their model, explore model parameters, view their embeddings, and a lot more. And we're consistently adding new capabilities to it. Last year, we launched the hparams dashboard to help visualize hyperparameter tuning results. This can help you identify which hyperparameters are most promising for further exploration. Given that many people are already using TensorBoard, and some are even sharing screenshots of it, we launched TensorBoard.dev to make all of this easier. With TensorBoard.dev, you can upload your experiment results and get a link that can be shared with everyone for free. Others can view and interact with your TensorBoard with no setup or installation. We started with the Scalars dashboard, but more dashboards will be added soon. We're only at the beginning of this journey, and we want to continue evolving this to help drive state-of-the-art research. As inspiration, I wanted to share a few awesome examples with you today. The TensorFlow/models repository on GitHub provides a collection of officially supported TensorFlow models on cloud TPUs. Many of them now provide a link to TensorBoard.dev. This allows you to quickly view the training dynamics and gives you a point of reference if you're training the model yourself and trying to understand if something is going wrong. In this example, Sean is using Twitter to share some work on large-scale ML experimentation. TensorBoard.dev is used to help tell that story more effectively. This team of researchers at Google recently published a paper on optimizer grafting to help better understand optimizer performance. Along with the paper, they've also uploaded results to TensorBoard.dev to show 550 grafting curves that help illustrate their technique. This would be difficult to convey purely in a paper. Another project from Google Research introduces Big Transfer, a recipe for scaling up image-based general visual representation learning. By transferring using a simple heuristic, they achieve state-of-the-art results across multiple vision tasks. They uploaded their results to TensorBoard.dev to show how their model's performance reaches state-of-the-art and compares with the baseline across multiple data sets. This paper from Europe's 2019 discusses binarized neural networks. Their GitHub repository includes several links to TensorBoard.dev to illustrate model accuracy. But what's really cool is that as part of the Nearest Reproducibility Challenge, another group of researchers published a report on this paper. In this report, they included links to TensorBoard.dev as well to provide a more complete picture of the training process and include other useful information to help others with debugging. So all of this sounds great, but how do you get started? You continue using TensorBoard in the same way that you use it today. In this example, the TensorBoard Keras callback is shown, but there are other APIs that can be used. If you're not familiar with TensorBoard, check out tensorflow.org/tensorboard for some great Colab tutorials. You can upload these logs with the TensorBoard dev upload command and provided the log directory. Just last week, we enabled optionally adding a name and description to your experiments to provide more context to those that view it. This can include links to your paper, GitHub repo, or simply point out what is really interesting about your results. You'll get a link to your TensorBoard that you can immediately view, even if your experiment is still in progress. Finally, you can share the experiment by copying the URL or using the share button in the top right. As I mentioned, we'll be adding more of TensorBoard's dashboards over time, as well as enabling more collaboration capabilities. You can learn more at tensorboard.dev and follow a simple example to get started. Thank you for your time. And next up is Julia to tell you about Kaggle with TensorFlow 2.
Hi, I'm Julia Elliott, and I lead Kaggle's competitions team. I'm speaking today about using TensorFlow 2 on Kaggle. This is based on work led by Phil Coulaton. So what's Kaggle? Kaggle is a data science platform. Over 4 million data scientists from all over the world come to Kaggle to participate in machine learning competitions, practice data science, build portfolios, and share data sets and code. It's an incredibly exciting place. My job at Kaggle is to run machine learning competitions. They run the gamut. Right now, we have 17 running, including deepfake detection in videos, image classification, an abstraction and reasoning challenge by Francois Cholet. If you haven't seen his paper entitled The Measure of Intelligence, it's really amazing. You should check it out. An NLP challenge, and a bot building simulation competition. Basically, if you're interested in data or machine learning, we'll likely have a competition that'll excite you. TensorFlow is really heavily used in our competitions. It's actually currently being used in all 17 of them. But in the past few months, we've run 2 TensorFlow-specific competitions, a question-answering NLP competition that Sandeep mentioned earlier, built around the launch of TensorFlow 2, and a new competition for image classification that introduces TPUs to our platform. We have tens of thousands of people using TensorFlow 2.1 right now to solve problems. 3 of the top solutions for the question-answering competition actually use TensorFlow and TPUs. If you'd like to check out TensorFlow 2.1, especially with a GPU or TPU, Kaggle makes it super easy. You can see from the list on this slide that we've eliminated a lot of the obstacles to making TensorFlow 2.1 build your models fast, and with next to no specialized code. No provisioning the right kind of VM, no setup, data sets that are ready to go, and a weekly amount of TPU, GPU time allotted to users for no cost. We'll look at some code right now that'll build a model on Kaggle for a competition to classify flowers on CPU, GPU, and TPU with no changes. So we start off simple. Import TensorFlow and the Kaggle datasets library. The rest of the code here does a little bit of magic. It figures out what kind of accelerator is attached to your VM and automatically parallelizes your model building. This will return an appropriate strategy, whether you're using a V3 TPU or a simple CPU VM. So basically, this code asks for a TPU. If it gets one, it connects it. If it doesn't, it sets that up as well. The rest of the code is entirely accelerator agnostic. So normally, outside of Kaggle and Colab, you need to provision this TPU for usage. But on our platform, it's not necessary. Just select the TPU in the dropdown and go. Now we'll load up our competition dataset. It's provided in a sharded TF record format for fast loading. We set some parameters for our training and validation sets, shuffling our training set, batching them for optimal performance, setting our training set to repeat so it'll loop around for each epoch. And in the end, we have nice out-of-memory datasets ready to run in our accelerator of choice. This code does some real work. Here, we load up a VGG16 for some transfer learning, compile our model, and start training and validating. We're using a standard distribution strategy that was made possible by that previous code that automated the strategy based on the accelerator used. Note the with strategy.scope block. That's basically saying, hey, whichever type of parallelization you're doing here, this is the process that parallelized. Now, our model will be built and trained on the accelerator. Making some flower predictions is real easy after this. We load up our test set, run model.predict, and write our predictions out in a format that Kaggle can read. With a few tweaks and a few more epochs, it can actually score pretty well. I'll finish off this code section with some of the fun flowers that our model made predictions on. You can see that some are right, they have the little OK above them, and some are wrong. If you're interested, you're more than welcome to drop by and beat this model. It's not hard, and it's super fun. If you're interested in seeing TensorFlow 2.1 at work on Kaggle, come check it out. Try out the code I just showed you, compete in the flower competition, or try it out with a dataset of your choice on our hosted notebook platform. In the next coming months, we'll be launching even more competitions where you can leverage the power of TensorFlow and TPUs. This was a huge group undertaking, and a special thanks to Martin Gorner, the DevRel PM who led the effort to integrate TPUs. It's pretty awesome to see how easy it is to use TensorFlow 2.1 on Kaggle now. Thank you so much. Next up is Chumin to tell you about TensorFlow profilers.
I'm Chumin. I'm a software engineer at Google working on TensorFlow performance. Today, I'm very excited to introduce you to our brand new TensorFlow 2 performance profiler. We all like speed, and we want our models to run faster. TensorFlow 2 profiler can help you improve your model performance like a professional player. In this talk, we will first talk about what's new in TF2 profiler, and then we'll show you a case study. I'm a performance engineer, and this is how I used to start my day. In the morning, I ran a model and capture a trace of it. I will gather the profiling results in a spreadsheet to analyze the bottlenecks and optimize the model. We often have gigabytes of traces, and the process all of them manually is boring and time-consuming. Then, after that, we'll run the model again to check for performance. If the performance is quite good, hooray, we have done our job. Go and grab coffee. Otherwise, we'll go back to step 1, recapture a profile, gather results, and find out the reason, fix it, and try again. Repeat this iteration by n times until the performance is good. This is a typical day of a performance engineer. Can we make it more productive? The most repeated work here is to gather the trace information and analyze the result. We always want to work smarter. At Google, we found out a way to build tools to automatically process all the traces, analyze them, and provide automated performance guidance. It does intensive trace analysis, learns from how Google internal experts tune the performance, and automate it for non-expert users. Here's the thing I'm very excited about. We are releasing this most useful set of internal tools today as a TF2 profiler. The same set of tools in TF2 profiler has been used extensively inside Google, and we are making it available to public. Let me introduce you to the tool set. Today, we will launch 8 tools. 4 of them are common to CPU, GPU, and TPUs. This enables consistent metrics and analysis across different platforms. The first tool is called Overview Page. This tool provides an overview of the performance of the workload running on the device. The second tool is Input Pipeline Analyzer. it is very powerful to analyze the TensorFlow input pipeline. TensorFlow reads data from the files in a pipelined manner, and an inefficient input pipeline can severely slow down your application. This tool presents an in-depth analysis of your model input pipeline performance based on various performance data collected. At the high level, this tool tells you whether your program is input-bound. If that is the case, the tool can also walk you through the device and host state analysis to debug which stage of the pipeline is the bottleneck. The third tool we released today, called TensorFlow Stats. TensorFlow Stats tool presents TensorFlow ops statistics in charts and tables. The fourth tool we released today is called Trace Viewer. Trace Viewer tool displays detailed event timeline for in-depth performance debugging. We also provide 4 tools that are TPU or GPU specific. They are all available today on TensorBoard. Please check out. Now, let's look at a case study. Let's assume that we are running an unoptimized ResNet 50 model on a V100 GPU. TF2 Profiler provides a number of ways to capture a profile. In this talk, we will focus on keras callback. To check out other ways of profiling, including sampling and programmatically profiling, refer to TensorFlow docs for more details. Using keras TensorBoard callback, we simply need to add an additional line specifying profiling range. The argument profile batch equals to 150 to 160 here indicates we will start to profile from batch 150 to 160. Run the model, launch TensorBoard, and go to the profile plugin. Here's a performance overview. Let's zoom in and look at the overview page. It contains 3 sections: performance summary, step time graph, and the recommendation for the next step. Let's zoom into each of them. First, let's look at the performance summary. It shows the average step time and breaks it down into the time spent on compilation, input, output, kernel launches, and the communication time. The next is the step time graph. We can see the step time is broken down into compilation time, kernel launch, communication as well, and you can see how these breakdown changes over a number of steps. In this example, there's a lot of redness in this chart and indicates it is severely input bound. The next is what I felt most excited about. This is the recommendation provided by our tool. It says, your program is highly input bound because 81.4% of the total step time sampled is waiting for input. Therefore, we should first focus on reducing the input time. Overview page also provides a recommendation on which tool you should check out next. In this example, Input Pipeline Analyzer and Trace Viewer are the next tools to see. In addition, this tool also suggests the related useful resources to check out to improve the input pipeline. This related article is, let's follow this recommendation and check out the Input Pipeline Analyzer tool. See, this is a host analysis breakdown provided by the tool. It automatically detects the most time spent on the data preprocessing. What should we do next? Our tool actually tells you what can be done next to reduce the data preprocessing. This is what is recommended by our tool. You may increase the number of parallel calls in the dataset map or process the data offline. If you follow the link on the dataset map, you will see how to do that. According to the guide, we changed the sequential map to use the parallel calls. We are also not to forget to try the most convenient auto-tune option, which will tune the value dynamically at runtime. After this optimization, let's capture a new profile. Now you can see the redness is all gone in the step time graph, and the model is no longer input bound. Checking the performance summary again. Now you get 5x speedup. Overview page now recommends differently. It says, your program is not input bound because only 0.1% of the total step time sampled is waiting for input. Therefore, you should instead focus on reducing idle time. Here's another thing we can do. If you look at the other recommendations, the model is all using 32 bits. If you replace all of them by 16 bits, you can get 10x speedup. This release is just the beginning, and we have more features upcoming. We are working on keyword-specific analysis and the multi-worker GPU analysis. Stay tuned. We also welcome your feedbacks, and please let us know and contribute your ideas. TensorFlow 2 Profiler is the tool you need for investigating TF2 performance. It works on CPU, GPU, and TPU. Here's more things to read: a tutorial, guide, and GitHub source code. There are also 2 more related talks on performance tuning in this afternoon. They are super excited, and don't miss them. Finally, I want to thank everyone who worked on this project. You are all super amazing teammates. Thank you. And next up, Robert and the guests will come to answer a few questions.
Hi, I'm Robert. I'm on the TensorFlow team here at Google, and with me today are Sandeep and Paige. We've had some great talks, and we've received some great questions, so let's see if we can get some answers. Okay. First up, this one's for Paige.
Okay.
Do you have any ideas on the advances of TensorFlow probability, and what is the plan on developing the module? I would love to see Bayesian methods in TensorFlow.
That is a phenomenal question, and we're really excited about all of the latest advances coming through with TensorFlow probability. Something that you'll want to check out if you haven't already is Bayesian methods for hackers has been updated to TensorFlow 2. We're also sort of expanding out the surface area of TensorFlow Probabilities API, adding some new features. They now have a JAX backend, which is quite experimental, but works sort of in lockstep with TensorFlow, so you can use TensorFlow or you can use JAX as your backend. And there are also more advances coming soon. So that is definitely still continuing work on TFP, definitely options for Bayesian methods, and we're excited to see what you build. So if you do create a really cool example, be sure to share it with us.
All right, that's great. Okay, the next question is for Sandeep. What are some new changes made specific to TensorFlow JS as a part of TensorFlow 2.0 that machine learning developers will find useful?
Yeah, thank you. So TensorFlow JS is near and dear to my heart. There are tons of enhancements and improvements in TensorFlow JS. So specifically for 2.0, we have new process for taking a TensorFlow 2 saved model and directly using it with TensorFlow JS with the Node backend without any conversion necessary. We have a bunch of new models that you will see later today. We have some text models. We have models for face and hand tracking, etc. And we have a lot of performance improvements and new backends. So I don't want to scoop my colleague Naz talk too much, but please do be sure to check it out later in the afternoon, and you'll learn a lot more about this.
All right, so stay tuned. Okay, our next question is for Paige. In the NLP hypertuning discussion, I would like to know if there are any advancements on how to address language regionalization.
So there are a couple, but I highly encourage you to look at documentation and also the TF text NLP resources that we've made available. For most of that, you can find it on TensorFlow.org. But in terms of NLP, we're really excited about the latest features being added to TensorFlow 2. Yeah.
Great. Okay, one more, if we have time. This is for Sandeep. Can I tune a pre-trained model which is trained by transfer learning by using Keras Tuner?
Yes, yeah, very good question. So as Paige showed us earlier in her talk, Keras Tuner is one of the most widely requested features because it makes the job of hyperparameter tuning super easy, which is something that all developers deal with. And you can absolutely use Keras Tuner for transfer learning and tuning a pre-trained model. Anytime you have a Keras model, Keras Tuner should be able to help you for your hyperparameter tuning. Do check out our documentation. Look at examples for transfer learning, and then if you create an end-to-end example with transfer learning and Keras Tuner, we would love to see that. So tweet it at us and maybe even contribute to some of the developer documentation.
Absolutely. There are several examples, as Sandeep mentioned, on the Keras Tuner website. I also wanted, just in case, because I forgot for the last question for language regionalization, be sure to check out TF Hub as well. To the point of your talk, there are a whole bunch of language embeddings for languages outside of English, and we're seeing more and more getting added every day.
Great. Okay. Well, thanks. That's all we have right now, but thanks for the great questions, and stay tuned. We're going to be taking a 20-minute break, and then we'll be back with more great talks and great questions. Thanks very much.
Thank you.
Thanks.
I'm Lawrence. I'm an AI advocate on the TensorFlow team, and I'm here with my colleague and friend Jason.
Hi there, I'm Jason, and I'm a developer advocate on TensorFlow.js.
Now, I hope you're as excited as we are about everything we've seen so far at the TensorFlow Dev Summit. There's a whole lot more still to come. The sessions are going to continue live from the main stage in just a bit. But in the meantime, we're going to try to answer some of your questions that you've been sending us with the hashtag AskTensorFlow. Now, you can keep tweeting us your questions right now with that hashtag, or ask them right here in the live stream chat. Jason, I, and some of the other team members, we're going to be active in the chat throughout the day to answer as many of those as we can. So why don't we start and try answering some of the questions now? What do you think, Jason?
Sounds like a plan to me. So first up, we have Ad Kumar, who asked, how do we extend Keras APIs, model subclassing, and generally improve the ease of use?
Oh, wow. That's a great question, and it's one that we get a lot because if you are new to TensorFlow, you probably are thinking, it does everything that I need to do in training models and all of that kind of stuff. But then once you get a little bit more advanced into TensorFlow, you realize that sometimes you're trusting some code that was written for you by somebody else, and you want to be able to subclass that. Yeah. You want to be able to override that. You want to be able to customize it, like custom training loops and that kind of thing. And that's a relatively advanced thing that you want to do, but a very important one as you get more advanced, particularly in research. So we've realized that the training and the information for this is kind of scattered all over the place. There's lots of files. I think the original question, he mentioned that there are over 100 files. And I haven't counted them, but I'm sure there are quite a few. So I'm actually right now hard at work at trying to put all of this together and produce a training course for Advanced TensorFlow and Advanced Keras. So teaching you some of that stuff, such as subclassing some of the classes that are there, creating custom training loops and all of that kind of thing, so that you really, I like to see it as like, driving stick instead of driving automatic. And so we're working on that. We're hoping to get it published in the next few months. So just watch out, and hopefully you'll have something that you can enjoy. So next question. This is one for you, Jason.
Excellent.
So IO62898019, that's a great handle, asked, what about web developers? And particularly web developers who are new to AI and machine learning, and they want to get started with all of this, but do they have the technology to help them?
Indeed we do, and that's why I'm here. We actually have TensorFlow.js, which is our JavaScript implementation of TensorFlow. And that means you can basically run it anywhere that JavaScript can run. So that might be client-side in the browser, in Node.js on the server side, on Internet of Things like Raspberry Pi, and we've just announced support for React Native as well, so even in native app development, which is pretty neat.
That's new to me. I didn't know that. Wow, cool.
And then, of course, if you are really prone to using Python, you can actually still use that. And we have a command line converter that allows you to convert the Python saved models into a TensorFlow.js format, which you can then use in all of those environments as well.
I love how you say prone to using Python. So, but which is one of the really nice things that, like with TensorFlow.js, where you can train it in the browser.
Yes.
Right.
Exactly.
It's not just for the data scientists that do Python and all that kind of stuff. So if you're a JavaScript developer, you don't have to learn something new. You can actually do your training
That's right.
in there.
You can stick to what you're used to, I guess. And
yeah.
There are some caveats if you're going client-side or server-side. So if you've got smaller models, they work very well on the client side, and you get other features like privacy and such as well. And if you want to train larger models, then Node.js works just as well as Python does and can do all that hard, heavy lifting for you.
Nice.
Yeah.
And one of the things I really liked about it when I started playing with it was that if I'm a JavaScript developer who hasn't learned Python, but I have teammates, who've been building models in Python for a long time, there's a converter.
Yes.
Right.
Exactly.
It converts the model into like a JSON object notation, and then I can start using that, load my interpreter, and off I go, which is kind of cool.
And another fun fact, if you are using Node.js, you can actually run saved models without conversion in Node, but you can't use them on the front end. So if you're just sticking to server side in Node.js, then you can run Python models without conversion now. And they actually run slightly faster because of a just-in-time compiler, which is very cool.
Very nice. Cool. I'm learning a lot today. Thanks, Jason.
Awesome.
So, and also one thing that, just a shameless self-plug, I hope you don't mind, but like a lot of this stuff around TensorFlow.js, when I got excited about it and I decided to put together a course to teach,
of course, yeah.
And I'm one of those who's prone to Python. So I did it from that perspective, like for people who, not necessarily just JavaScript developers, but people who are Python developers who are used to building ML, just to see how easy it is to do stuff in the browser. And we got some cool projects they can play with. And,
awesome.
And it's all on Coursera if they want to check it out.
I should have to take that one as well.
Yes, please. Yes, I need all the students I can get. So, actually another question for you, and this one comes from Isbelen Erdem, and they ask, are there any TensorFlow.js transfer learning examples, in particular for object detection?
That's a really good question. That's something I was looking into when I first joined the team a little while ago. Before I answer that though, I just want to talk a little bit about object detection and what that is versus image detection. So object detection is essentially the ability to recognize one or multiple objects in a given image and also find their locations with little bounding boxes. That's different to image detection, which essentially allows you to know if something is in an image but not where it is, and also typically for one thing only. So now we know that, how do we do it in TensorFlow.js? Well, I think the easiest way to do this is actually to use Cloud AutoML, which now supports exporting the custom trained models you make on there to TensorFlow.js format.
Okay.
And of course, with that, you can then use that anywhere, as we discussed before. You can check out the documentation to get started that online. But essentially, all you need to do is have a folder full of images, like cat images, and then a CSV file that has the coordinates of the bounding boxes for each image, showing where the cat is in each image. And that is then used as the training data to retrain the model to then work with your data. You then download that and then use it as you need to.
Okay,
so, yeah.
That's pretty cool. So instead of like you building a transfer learn model yourself, you're using an existing online model and having Cloud AutoML retrain
Exactly,
that.
yeah. If doing this in TensorFlow.js for something like Cocoa SSD might be a little tricky unless you have access to the full model, the original model, if you will. So if you don't have access to that, you can just leverage Cloud AutoML instead.
So check out the Cloud AutoML documentation on that.
Definitely,
for details.
sounds good to me.
Cool. Should we go to the next question?
Let's do it. Okay, so next up we have Conrad WT, who asks, does TensorFlow leverage Metal when running on macOS?
I take it they mean iOS and not macOS.
Ah, yes. True.
All right. So it's there are a number of ways that you can use Metal on iOS. The simple answer is yes, you can. So with TensorFlow Lite, there's a thing called a GPU delegate that allows you that some mobile devices have access to GPU, some do not. On iOS, of course, it's more common to have access to the GPU. So with the GPU delegate in TF Lite, you can actually effectively access Metal, which gives you the ability to run inference using the GPU, so you can have much faster inference on the device
Very
itself.
useful, yeah.
Super useful. Faster inference means you're using less battery life, means you're more responsive with your application and stuff like that. It's pretty cool. It's a bit complex to go over all of that here in this video, but I would say check out the tensorflow.org/lite site, or search for GPU on that site as well, and you'll see all the details. There's a whole bunch of stuff, and there's including some sample apps showing you how you can enable it and how you can use the GPU delegate so that you can just have a little bit of fun using your GPU to do faster inference on mobile. Not just Metal and iOS, but also things like the Neural Network API and Android.
Nice, very cool.
So the next question that came in was from Rishav16, and they asked, what's the best way that someone like a high school student could engage with TensorFlow and could learn maybe some of the basics around ML and start doing some real things, and then from that then be able to move on to the different components and submodules for their projects and their work. And
sounds good.
It's a good way for a high schooler to get started.
Yeah. So I guess when you're starting out, you want to kind of try something a little more graphical to get started, to just learn how things need certain amounts of training data and what biases might come into this kind of situation. So I recommend checking out a website called Teachable Machine, which is made by Google, and it allows you to simply point your webcam at various objects, or maybe use a microphone, whatever you want to use, and train on that data. And within about 1 minute, you can have a machine learning model that can classify speech or objects and even poses, which is pretty cool.
Right. So very quickly within the browser, being able to put something together so they can just see how machine learning models work.
Exactly, and they can try it live after the model's trained. The webcam will be fired up, and you can then repoint it at the things you're training on and see the class it predicts right there in the browser in real time, super low latency. And if you like it, if it's actually useful to you, you can then download that model. It's just a JSON file essentially, which you can then reuse on any website you want to deploy that on essentially.
Nice, what a great way to get started.
Very cool. I wish they had that back in my day.
Like last year.
Yeah. So next up we have one Amar Vind, who asks, what are TensorFlow records and why are they needed for input?
That's a great question, and to understand why you need TensorFlow records, you have to kind of double-click a level above that and think about data. Right? Data is really the lifeblood in training any kind of machine learning application. But data comes in all shapes and sizes.
That's very true.
Right? There might be a zip file over here with images. There might be CSV files. If you are inclined to be a JSON person, you might be JSON files. Those kind of things. And it's without having a lot of skills in being able to understand this, it becomes a huge learning curve for people to say, okay, which one am I going to use? How am I going to use it? How do I unzip? How do I use JSON? How do I? And when I've seen like a lot of people building models, you might have like this much code for building a model, but this much is the model architecture, and this much is like downloading the data, figuring it out, putting it into formats like I'm Python inclined, and putting it into the, like, NumPy format so that I can do training, or if it's JS, putting it into JSON sort of tensors so that I can do training and that kind of thing. And it's a whole amount of calories that I have to burn just before I can even get started.
That's very true.
So the idea behind TF Record and something called TensorFlow Data Services and TensorFlow Data Sets is to try and make that as easy as possible. So what we've done is we've taken a whole bunch of different data sets and put them into an API so that with 1 or 2 lines of code, you have everything that you need to start training.
Very cool.
So now instead of going from this with this much for your data, you're going from this to this with only this much for your data.
Very nice.
If that visualization works okay. And so things like that. And then the core of that is the TF record. So you need to have like one kind of that base class from which you can do everything. And then when you're doing that, there's all of these different optimizations for training. Like if you're doing distributed training and you want to manage pipelines. And I always like to think about it as like, say, take for example, you have a CPU and a GPU and you're going to do your training on the GPU. Well, you do all your data pre-processing on the CPU, right? So the CPU is grabbing the data and handing it to the GPU, and then while the GPU is working, the CPU also has to be doing something, and to get the two of these to work in parallel can be very difficult.
Sure.
So there's a lot of pipelining technology in TensorFlow, and that is built to use TF record to be able to manage all that
I
data.
see.
So
very neat.
you know, it seems like one small thing, and you might think, well, why on earth would I want to use this when I've got CSV or I've got databases or I've got all of that kind of thing? But once you start using it in that way, you'll see it has great benefits for your training.
Awesome.
Well, that's the end of the questions. That was a whole lot of fun. Thanks, Jason.
It was. Thank you for inviting me.
You know, so stay tuned. There's the rest of the sessions will be coming up pretty soon.
And for those of you at home, we also run in the web browser, of course. So that means we'll be sending those out after the show as well. So stay tuned for details on that.
That's one of the really nice things about JavaScript. You can
Indeed,
just push it
runs
out
everywhere.
And for those of you also on the live stream at home, keep those questions coming. #AskTensorFlow. Jason, myself, the rest of the team will be here to try and answer as many of them as we can. So thank you, and we'll see you around.
Hello, my name is Alex, and I work on TensorFlow. I'm here today to tell you all a little bit about how you can use TensorFlow to do deep learning research more effectively. What we're going to do today is we're going to take a little tour of a few TensorFlow features that show you how controllable, flexible, and composable TensorFlow is. We'll take a quick look at those features, some old and some new, and not by far all the features that are useful for research, but these features let you accelerate your research using TensorFlow in ways that maybe perhaps you're not aware of. And I want to start with by helping you control how TensorFlow represents state. If you've used TensorFlow before, and I'm sure you have at this point, you know that a lot of our libraries use tf.variables to represent state, like your model parameters. And for example, a Keras dense layer has one kernel matrix and an optional bias vector stored in it. And these parameters are updated when you train your model. And part of the whole point of training models is so that we find out what value those parameters should have had in the first place. And if you're making your own layers library, you can control absolutely everything about how that state is represented. But you can also crack open the black box and control how state is represented, even inside the libraries that we give you. So for example, we're going to use this little running example of what if I wanted to reparameterize a Keras layer so it does some computation to generate the kernel matrix, say to save space or to get the correct inductive bias. And the way to do this is to use tf.variableCreatorScope. It is a tool we have that lets you take control of the state creation process in TensorFlow. It's a context manager, and all variables created under it go through a function you specify. And this function can choose to do nothing, it can delegate, or it can modify how variables are created. Under the hood, this is what distribution strategy.scope usually implies. So it's the same tool that we use to build TensorFlow that we make available to you so you can extend it. And here, if I wanted to do this reparameterization of the Keras layers, it's actually pretty simple. First, I define what type I want to use to store those things. And here I'm using this factorized variable type, which is a tf.module. tf.module is this very convenient type. You can have variables as members, and we can track them automatically for you and all sorts of nice things. And once I've defined this type, it's really just a left half and a right half, I can tell TensorFlow how do I use objects of this type as a part of tensor computations. And what we do here is we do a matrix multiplication of the left component and the right component. And then, now that I know how to use this object, I can create it. And this is all that I need to make my own little variable creator scope. In this case, I want to peek at the shape. And if I'm not creating a matrix, just delegate to whatever TensorFlow would have done normally. And if I am creating a matrix, instead of creating a single matrix, I'm going to create this factorized variable that has the left half and the right half. And finally, I now get to just use it. And here I create a little Keras layer. I apply it, and I can check that it is indeed using my factorized representation. This gives you a lot of power, because now you can take large libraries of code that you did not write and do dependency injection to change how they behave. Probably if you're going to do this at scale, you might want to implement your own layer so you can have full control. But it's also very valuable for you to be able to extend the ones that we provide you. So use tf.variableCreatorScope to control the state. OK. Big part of TensorFlow and why we use these libraries to do research at all, as opposed to just writing plain Python code, is that deep learning is really dependent on very fast computation. And one thing that we're making more and more easy to use in TensorFlow is our underlying compiler, XLA, which we've always used for TPUs, but now we're making it easier for you to use for CPUs and GPUs as well. And the way we're doing this is using tf.function with the experimental compile equals true annotation. What this means is, if you mark a function as a function that you want to compile, we will compile it or we will raise an error. So you can trust the code you write inside that block is going to run as quickly as if you had handwritten your own fused TensorFlow kernel for CPUs and a fused CUDA kernel and done all the machinery yourself, but you get to write high-level, fast Python TensorFlow code. One example where you might easily find yourself writing your own little custom kernel is if you want to do research on activation functions, which is something that people want to do. And activation functions, this is a terrible one, but they tend to look a little like this. They have a bunch of nonlinear operations and a bunch of element-wise things, but in general, they do apply lots of little element-wise operations to each element of your vector. And these things, if you try to run them in the normal TensorFlow interpreter, they're going to be rather slow because they're going to do a new memory allocation and a copy of things around for every single one of these little operations. While if you were to make a fused single kernel, you just write a single thing for each coordinate that does the exponentiation and logarithm and addition and all the things like that. But what we can see here is that if I take this function and I wrap it with experimental compile equals true, and I benchmark running a compiled version versus running a non-compiled version, on this tiny benchmark, I can already see a 25% speed up. And it's even better than this, because we see speed ups of this order of magnitude or larger, even on fairly large models, including BERT. So, because on large models, we can fuse more computation into the linear operations and your reductions and things like that, and this can get you compounding wins. So try using experimental compile equals true for automatic compilation in TensorFlow. You should be able to apply it to small pieces of code and replace what you would normally have to do with fused kernels. So you know what type of researchy code a lot of people rely on that has lots of very small element-wise operations, and that which would greatly benefit from the fusion powers of a compiler? And I think it's optimizers. And a nice thing about doing your optimizer research on top of TensorFlow is that Keras makes it very easy for you to implement your own stochastic gradient descent style optimizer. You can make a class that subclasses the TF Keras optimizer and override 3 methods. You can define your initialization where you compute your learning rate or whatever in your init. You can create any accumulator variables like your momentum or higher order powers of gradients or anything else you need in create slots. And you can define how to apply this optimizer update to a single variable. Once you've defined those 3 things, you have everything TensorFlow needs to be able to run your custom optimizer. And normally, TensorFlow optimizers are written with hand-fused kernels, which can make the code very complicated to read, but ensures that they run very quickly. What I'm going to show here is an example of a very simple optimizer. Again, not a particularly good one. This is a weird variation that has some momentum and some higher order powers, but it doesn't train very well. However, it has the same sorts of operations that you'd have on a real optimizer. And I can just write them as regular TensorFlow operations in my model. And by just adding this line with experimental compile equals true, I can get it to run just as fast as a hand-fused kernel. And the benchmarks I ran here, it was over a 2x speed up. So this can really matter when you're doing a lot of research that looks like this. Something else, so Keras optimizers and compilation let you experiment really fast with fairly intricate things, and I hope you will use this to accelerate your research. The next thing I want to talk about is vectorization. It's again super important for performance. I'm sure you've heard at this point that like Moore's law is over and we're no longer going to get a free lunch in terms of processors getting faster. The way we're making our machine learning models faster is by doing more and more things in parallel. And this is great because we get to unlock the potential of GPUs and TPUs. But this is also a little scary because now, even though we know what we want to do to a single little data point, we have to write these batched operations, which can be fairly complicated. In TensorFlow, we've been developing recently automatic vectorization for you, where you can write the element-wise code that you want to write and get the performance of the batch computation that you want. So the working example I'm going to use here is Jacobians. If you're familiar with TensorFlow's gradient tape, you know that tape.gradient computes an element-wise, computes a gradient of a scalar, not a gradient of a vector-valued or matrix-valued function. And if you want the Jacobian of a vector-valued or matrix-valued function, you can just call tape.gradient many, many times. And here I have a very, very simple function that is just the exponential of the square of a matrix. And I want to compute this Jacobian. And I do this by writing this double for loop, where for every row, for every column, I compute the gradient with respect to that row and column output, and then stack the results together to get my higher order Jacobian tensor. This is fine. This has always worked. And however, you can replace these explicit loops with TF.vectorize map. And one, you get a small readability win, because now we're saying that, yes, you're just applying this operation everywhere. But also, you get a very big performance win. And this version that uses TF.vectorize map is substantially faster than the version that doesn't use it. But of course, you don't want to have to write this all the time, which is why really, for Jacobians, we implemented it directly in the gradient tape, and you can call tape.jacobian to get the Jacobian computer for you. And if you do this, it's over 10 times faster on this example as doing the manual loop yourself, because we can do the automatic vectorization. But the reason why I opened this black box and showed you the previous slide is so you can know how to implement something that is not the Jacobian, but it's like a Jacobian yourself, and how you can use TensorFlow's automatic vectorization capabilities together with the other tools you have in your research to make you more productive. And so remember to use automatic vectorization so you can write short code that actually runs really fast, and let us add the batch dimensions ourselves. And here is another interesting performance point, because TensorFlow, we have always had the big rectangular array or hyperarray, the tensor as the core data structure. And tensors are great. In a world where we live in today, where we need to leverage as much parallelism as we can to make our models go fast, operations on tensors, they tend to be naturally highly parallel by default. It's a very intuitive API to program the capabilities of the supercomputers we have today with many GPUs and TPUs wired together. And as long as you can stay within this tensor box, you are happy, you get peak performance, and everything is great. However, as deep learning becomes more and more successful, and as we want to do research on more and more different types of data, we start to want to work with things that don't really look like these big rectangular arrays, structure that is ragged and has a different shape. And in TensorFlow, we've been recently working really hard at adding native support to ragged data. So here's an example. Pretend it's 10 years ago, and you have a sentence, and you have a bunch of sentences, they all have different lengths, and you want to turn them into embeddings so you can feed them into a neural network. And so what you want to do here is you're going to start with all the words in that sentence, you're going to look up their index in your vocabulary table, then you're going to use the index to look up a row in an embedding table, and finally you want to average the embeddings of each sentence to get an embedding for each, the embeddings of all the words in a sentence to get an embedding for each sentence that you can then use in the rest of your model. And even though we're working with ragged data here, because all the sentences have different lengths, if you think about the underlying operations that we're doing here, most of them don't actually have to care about this raggedness. So we can make this run very efficiently by decomposing this representation into two things. A tensor that concatenates across the ragged dimension, and a separate tensor that tells you how to find the individual ragged elements in there. And once you have this representation, it's very easy and efficient to do all the computations that we wanted to do to solve the task from the previous slide. You have always been able to do this manually in TensorFlow. We've always had the features and capabilities for you to do this. Now with TF.ragged tensor, we're taking over the management of this from you and just give you an object, a ragged tensor that looks like a tensor, can be manipulated like a tensor, but is represented like this. And so it has ragged shapes and can represent much more flexible data structures than you could otherwise. So let's go over a little bit of a code example here. Here is my data, same one from the previous slide. It's just a Python list. And I can take this Python list and turn into a ragged tensor using tf.ragged.constant, and the right thing is going to happen. TensorFlow is going to automatically concatenate across the ragged dimension and keep this array of indices under the hood. Then I can define my vocabulary table and do my lookup. And here I'm showing you how to do your lookup or any operation on a ragged tensor where that operation hasn't actually been rewritten to support raggedness. You can always use tf.ragged.mapFlatValues to access the underlying values of your ragged tensor and apply operations in them. Then we create an embedding matrix, but also many of the TensorFlow core operations have been adapted to work with ragged tensors. So in this case, if you want to do a tf.gather to find out the correct rows of the embedding matrix for each word, you can just apply your tf.gather on the ragged tensor and the right thing will happen. And similarly, if you want to reduce and average out the ragged dimension, it's very easy to do. You can just use the standard tf.reduceMean. And the nice thing is that at this point, because we've reduced out the ragged dimension, we have no ragged dimension, and we just have a dense tensor that has the original shape you expect it to have. And I think this is really important, because now it's much easier, much more intuitive and affordable for you to work with data that doesn't necessarily look like the big rectangular data that TensorFlow is optimized for, and yet it lets you get most of the performance that you'd get with the big rectangular data. It's a win-win situation, and I'm really looking forward to see what interesting applications you all are going to work on that use and exploit this notion of raggedness. So please, play with TF.ragged, try it out. It's very exciting. So next up, we're going to go over a particular interesting example of research done with TensorFlow. And Akshay here, who is a PhD student at Stanford University, is going to come and tell us all about convex optimization layers in TensorFlow. Thank you.
Hi, my name is Akshay. I'm a PhD candidate at Stanford. And today, I'm going to talk about some recent research that makes it possible to embed convex optimization problems into TensorFlow. This is an optimization problem. And in an optimization problem, the goal is to find a value for a variable x that minimizes a cost function while also satisfying some constraints. So here, the variable might represent a decision, or it might represent weights in a machine learning model, or it could be the design of a physical device. And one thing to notice is that an optimization problem is a declarative object. It's not a procedural method. So basically, all you have to do is to articulate the objective function f, which measures how much you dislike any given value of x. And then you specify the constraints that your variable has to satisfy. And also notice that the optimization problem here is parameterized by a vector theta. And this vector determines the shape of the objective function and the constraints, and it's going to be important later. Unfortunately, most optimization problems are computationally intractable, but convex optimization problems are the subset that we can solve easily. Convex optimization has a lot of properties that make it a useful tool. So for one, convex optimization problems can be solved exactly and very quickly, up to thousands or even millions of times a second. Convex optimization is also easy to use in practice, thanks to software libraries like CVXPy. And to make things really concrete, here's a 5-line snippet of code that constructs and solves a convex optimization problem using CVXPy. So first, you construct a variable. Then you construct the objective function and a list of constraints. Then the objective and the constraints are used to construct a problem object. And you can call the solve method on this object to produce a value of x that solves the problem, i.e. it minimizes the objective function and satisfies the constraints. And I guess the only reason that any of this matters is that convex optimization has tons of applications. It's got many more applications than people once thought, actually. And I'll really quickly give you guys a few examples. Convex optimization is used on board self-driving cars for tasks like generating trajectories and tracking paths in real time. It's also used to control actuators in spacecrafts and to generate landing trajectories for rockets. Convex optimization has even been successfully used to design airplanes and other physical structures. Until now, it was very difficult, if not impossible, to use convex optimization problems in TensorFlow pipelines. And as a result, the parameters theta in the optimization problem were chosen and tuned by hand. So this means that the structure of the problem was often painstakingly crafted by a human. This process of choosing parameters in a problem is carried out in basically every field, and in different fields, it goes by different names. So in machine learning, we know it as hyperparameter tuning. It's an essential part of controls engineering. In finance, it's called backtesting. But if machine learning has taught us anything, it's that we should prefer gradient-based tuning of parameters over manual tuning whenever possible. And this observation gets to the heart of this talk. So last year, my lab mates and I figured out how to differentiate through convex optimization problems. This makes it possible for the first time to tune the parameters in a convex optimization problem using gradient descent. Once we figured out the math, we wrote a software library called CVXPy layers that makes the math actionable. Our library turns a CVXPy problem into a differentiable convex optimization layer that you can use in TensorFlow. And the basic idea is to view a convex optimization problem as a function mapping parameters to an optimal solution. So on this slide, the layer is represented by the function x star of theta. And x star of theta is the argmin of a convex optimization problem parameterized by theta. Different values of theta lead to different convex optimization problems and different solutions. And just like any other layer in TensorFlow, a CVX-Pi layer has a forward pass and a backward pass. In the forward pass of the layer, the parameters are taken as input. Then the forward pass solves the CVX-Pi problem and outputs a solution. The backward pass computes the gradient of the solution with respect to the parameters. And here's the upshot. Our software lets you learn the parameters theta in a convex optimization problem using gradient descent. And this automates what has traditionally been a very manual process. So let's walk through a short code snippet that shows how to use a CVX-Pi layer in TensorFlow. In the first 3 lines highlighted here, we import 3 packages. We import CVX-Pi to construct the problem, TensorFlow, and then we import CVX-Pi layers. In this next highlighted block, we construct a simple convex optimization problem using CVX-Pi. In line 4, we construct the variable x. In line 5, we declare the parameters in the optimization problem, which are a and b. So a and b here correspond to the vector theta that we saw in the previous slides. In line 6, we constrain x to be non-negative. In line 7, we construct the objective, which here is to minimize the 1 norm of ax minus b. And in line 8, we construct the problem. In line 9, we construct a CVX-Pi layer. And all we have to do in order to do this is to pass in the problem, the parameters, and the variable to the CVX-Pi layer constructor. And we can now use this layer in TensorFlow. In this last highlighted block, in lines 10 and 11, we construct TensorFlow variables that represent the parameters a and b in the problem. And line 13 is where the magic starts to happen. So in line 13, we solve the convex optimization problem. And notice that the CVX-Pi layer is a callable object. So you pass it the parameters, and it returns a solution to a corresponding convex optimization problems. And the details of the solution algorithm are completely abstracted away from you, the user. A lot of stuff happens behind the scenes, but we abstract all of that away. In line 15, we compute the gradient of the solution with respect to a and b, the parameters. And again, the details of the derivative are completely abstracted away from you. And that's it. So in just 15 lines of code, we constructed a convex optimization layer, solved the convex optimization problem, and then we differentiated through it. I'll end by showing just one example of the things that you can do with CVX-Pi layers. And in this example, we're going to learn how to control a self-driving car. So the setting is we've got a car, and we want to learn a control policy that allows it to track a given path at a given speed. We can control the car by choosing its acceleration and its steering angle at each time step. And these 2 things are the control inputs. So today in the real world, you might choose the controls using something like PID, or you might use a painstakingly hand-tuned controller. So in this example, we use a CVX-Pi layer as the policy that chooses the control inputs. And this allows us to naturally incorporate constraints on the acceleration and the steering angle in the policy itself. In order to learn the policy, we randomly sample a bunch of different paths, and we tune the parameters in the layer using gradient descent. The objective is to minimize some cost function that measures how well we're tracking the path and the speed. So this plot shows the performance of the control policy on a randomly sampled path, but before any training happened. The solid black curve is the path that we're trying to track, and the dotted curve is the path that the car actually took. So clearly, the untrained policy doesn't do too well. So in order to try to improve the performance, we train the policy for 100 iterations in simulation. And each iteration, we solve a bunch of convex optimization problems, and then we differentiate through the sequence of optimization problems using gradient descent to update the parameters. The train policy does a lot better. That's the plot on the right here. So the same desired path is actually plotted on both the left and the right. The car on the left just traveled more slowly and only made it to the top of the loop. So after 100 iterations of training, the train policy tracks the path much more accurately. So if any of that sounded interesting to you, I would encourage you to check out the links on this slide. Our software package, CVX-Pi Layers, is online at GitHub, and you can also download it using pip. If you want to learn more about the inner workings of convex optimization layers, you can check out our NeurIPS paper. And if you like that car example we just saw, check out our recent paper in L4DC, which develops that example and a lot of other examples in a lot more detail. And the code for all of these examples is online. And that's it. Thank you guys for listening. Next up is Rohan to tell you about tf.data.
Hi all, I'm Rohan, and I'm here to talk to you about how you can scale up your input data processing with TF data. So let's start with a high-level view of your ML training job. Typically, your ML training step will have two phases to it. The first is data pre-processing, where you're going to look at the input files and do all kinds of transformations on them to make them ready for the next phase, which is model computation. While you're doing data pre-processing, which happens on the CPU, you might be doing some kind of things such as for images, you're cropping them, for videos, you may be sampling them, and whatnot. So if your training speed is slow, you could have a bottleneck in either one of these two places. And I hope that the talk on profiling would give you an indication on how to figure out which one of the two phases you're getting slow at. And I'm here to talk to you about the first kind of pre-processing bottleneck, the bottleneck which is data pre-processing. So let's try to look into what this bottleneck really is. So in the last few years, we've done a fantastic job making accelerators which do the ML operations really fast. And so the amount of time it takes us to do a matrix operation on all the linear algebra operations is a lot smaller. But the hosts and the CPUs that feed the data to these accelerators have not been able to keep up with them. And so there ends up being a bottleneck. We thought that we could mitigate this by making the models more complex, but what happens is that the accelerators have constraints on how much RAM they have, and more importantly, where you deploy these models tends to be something like a mobile device or something like that, which tends to restrict the amount of complexity you can introduce into your model. So that hasn't really panned out. The second approach people take is that they try to train larger batch sizes. But larger batch sizes require a larger amount of pre-processing to assemble the batch. So then that puts further pressure on them. So that's why this is becoming an increasingly larger problem within Alphabet and even externally. And I'm going to talk to you about how you can solve it using TF data. TF data is TensorFlow's data pre-processing framework. It's fast, it's flexible, and it's easy to use. And you can learn more about it at our guide. To for background for the rest of the talk, I think I'm going to go through like a typical TF data pipeline, and that will help us in the later stages. So suppose you have some data in some TF record files, which are your training data. So you can now start off with a TF record data set with that data, and then after that, you start doing your pre-processing. This is typically the bulk of the logic. So if it's images, you're doing cropping, maybe flipping, all sorts of things there. After that, you'll shuffle the data so that you don't train to the order in which you see the examples and the input, and that helps you with your training accuracy. And after that, we would batch it so that the model, the accelerator, can now take use of vectorized computations. Finally, you want to do some software pipelining so that you ensure that while the model is off working on one batch of data, you can then, the pre-processing side can produce the next batch so that everything works very efficiently. Finally, you can then feed this TF data set to a Keras model so that you can now start doing your training. So given that sort of basic pipeline, and suppose you have a bottleneck, the first thing I'd recommend you to do is to go through our single host performance guide and try to utilize every trick and transformation that is available in TF data to be able to extract the maximum possible performance, so that you're using all the cores and whatever. There's excellent information at the guide that we have here, and even Giri did a great talk at the ML Tokyo Summit, which you can take a look at to learn more about this. So that's the first thing I'd recommend you do. But suppose you've done that and you've tried all the different recommendations that we have here, but you're still bottlenecked on that data preprocessing part. And don't worry, you're not alone. This is very common. We've increasingly seen this with a lot of internal customers. And so now I'm very pleased to present a couple of solutions that we've been working on the team to help you solve that problem. So the first idea is that why don't we just reuse the computation? So suppose you're playing around with different model architectures, your input preprocessing sort of part kind of remains the same. And if it's expensive and time consuming, why don't we just do it once, save it, and then every subsequent time we just read from it and do that quickly. So we noticed a bunch of internal customers, teams within Alphabet who were trying to do this on their own outside of TF data, and we decided to bring it into TF data and make it incredibly fast, flexible, and easy to use. And so this is what we call snapshot. The idea is what I explained to you. It's you materialize the output of your data preprocessing once, and then you can use it many, many times. This is incredibly useful for playing around with different model architectures, and if you've settled down on an architecture, doing hyperparameter tuning. And so you can get that speed up using snapshot. Next, I'm going to go through the pipeline that we talked about before and see how you can add snapshot to it to make it faster. So that's the original pipeline that we had. And so notice that there's this preprocessing step, which is expensive. So now with snapshot, you just add a snapshot transformation right after that with a directory path. And with this, everything that is before the snapshot will now be written to disk the first time it's run. And then every subsequent time, we would just read from it. And we would go through the rest of the steps as usual. One thing I'd like to point out is that we place the snapshot at a particular location before the shuffle, because if it's after the shuffle, everything gets frozen. So all the randomization that you get out of shuffle, you lose, because every subsequent time, you're just going to be reading the same exact order again and again. So that's why we introduce it at that stage in the pipeline. So snapshot, we've developed it internally. There are internal users and teams that are using it and deriving benefit out of it. And now we're bringing it to the open source world. We published an RFC, which has more information about it and some of the technical details. And this would be available in TensorFlow 2.3. But I believe it would be available in the nightlies shortly. So remember, I talked about two ideas. So the second idea is that now not all computation is reusable. So because suppose you had some randomized crops in there, and if you wrote that to disk and read them back, you'd again lose that randomization. And so a snapshot is probably not applicable in that scenario. So the second idea is to be able to distribute the computation. So the initial setup is that you have one host CPU, which is driving a bunch of these accelerators. But now you can offload this computation from this host to maybe a cluster. And now you can utilize the ability and the computational power that you have for all these different workers to be able to feed the host so that you're not bottlenecked on the input preprocessing anymore and things move fast. This is TF Data Service. It's a it's a TF data feature that allows you to scale your workload horizontally. So if you're seeing a slowness in your input preprocessing, you can start adding workers, and it'll just scale up. It's got a master worker architecture where the master drives the work for the different workers, and it gives you fault tolerance. So if one of the workers fails, you're still good, and you still can make progress. So let's see how you can use the TF data service for the example that we have. So here, instead of having sort of an expensive preprocessing, let's say you have some randomized preprocessing. So now this is not snapshotable, because if you snapshot, then you lose the randomization. So we'll provide you a binary which allows you to run the data service on the cluster setup manager that you like, whether it's Kubernetes or cloud or something like that. And then you can, once you have that up and running, you can just add a distribute transformation to your TF data pipeline and provide the master address. Anything before the distribute transformation would now get run on the cluster that you have set up, and everything after will run on the host. And so this allows you to sort of scale up. Again, note that because we are not doing any kind of freezing of the data, we can now put this transformation as late as possible in there. So notice that I've put it after the shuffle transformation. The service, like Snapshot, has been developed with internal users. They've been using it, and it's been like a game changer in terms of TPU utilization. And now, again, we're bringing it to you. And so we published an RFC, which was well received, and this should be available in 2.3 for you to play around with. So to summarize, what did I talk about today? So as with various trends in hardware and software, we've ended up in a scenario where a lot of input machine learning jobs are getting bottlenecked on input preprocessing. And I've told about 2 solutions that TF data team has been working on to help you solve this bottleneck. First is Snapshot, which allows you to reuse your preprocessing so that you don't have to do it multiple times. And the second is the TF data service, which allows you to distribute this computation to a cluster so that you get the scale up that you need. I hope you play around with these and give us feedback. And thank you for your time. Next up is Ongwei, who's going to talk about the second part of bottlenecks, which is on the model training side. Thank you.
Good morning and good afternoon, researchers and TensorFlow developer. My name is Zhongwei Zhou. I'm from TensorFlow performance team. Today, I'm going to tell you more about TensorFlow distributed training. Let me start a talk by sharing a piece of experience that you might already encounter before. Suppose that you have an awesome prototype machine learning model that you work so hard to make it run efficiently on single host with multiple GPUs. Now it's time to really get it running end-to-end with some more resources. Then you started 4 of your beefy cloud virtual machines, each with multiple modern GPUs connected with fancy 100 gigabits network. With all these resources, you deploy your models and hope to see it run blazingly fast. But wait, why am I only getting 1.5x faster than a single machine while I'm using 4 of them? Yes, I know, this is really frustrating. If you have similar experience and questions, this talk is for you. In today's talk, you are going to learn how to scale out your TensorFlow 2 Keras model to multiple machine, multiple GPU, and using the optimization we will ship in the upcoming TensorFlow 2.2 release, you are going to dramatically improve your training throughput. I used one case study, Bird Squad, for today's talk. But of course, it has to be this revolutionary NLP model, which is very popular in the past year. I use the fine-tuning task, which is the squad reading comprehension task, for example. Your training model is going to be given some reading materials and questions, and your model needs to answer the questions under the context and be evaluated with the accuracy. The model we use today are available in TensorFlow 2 official model garden, where you could go and download via this link and try it out following. And here is a quick demonstration of the BERT squad training throughput. Starting from the first line, this is the training throughput using TensorFlow 2.1 out of the box, with 3 optimizations in TensorFlow 2.2 that I'm going to introduce today. The model is now running 2.x faster. Aren't you excited and want to see these optimizations? But before diving into the exciting optimization, let me provide some background information and introduce how the model is synchronously trained on multiple hosts, multiple GPU. And here we are leveraging the native TensorFlow distributed training support, which is multi-worker mirror strategy. In the figure here, we have 2 GPU devices on 2 different hosts. And we are using a simple deep learning model, which have 2 layers, A and B, and with 1 variable each. So each GPU receives a subset of the training data and compute the forward pass using its local copy of model variables. And then it runs through the backward pass to calculate the gradients of each layer. After the gradients are calculated, all the devices now start communicating between themselves using all-reduced algorithm to aggregate the gradients. After gradient aggregation, each device will get back the same set of the aggregated gradients and then use that to update their local variables. We call it synchronous because every device needs to aggregate the gradient, get the same set of the aggregated gradient, update their variables before they can actually proceed to the forward pass of the next training step. So with so many phases in the deep learning training, how do we actually identify where the bottleneck is? Is it in forward path, backward path, gradient aggregation, or variable updates? How do we know where to optimize? Yes, of course, we are going to use TensorFlow Profiler, which Chumin just introduced to you today. So let's start run the BERT squad model, log into one VM, fire up the TensorBoard, take a profile, and then open the trace viewer. And here is the trace you will get from the trace viewer. In this view, if you see there's a pink bar with number 5 at the bottom of the profile, which means that this is the number 5 training step in your profile. And this is the whole operations within this training step. And the first 5 rows are events that is related to GPU. Specifically, in the first row, you will see GPU computation, which includes forward pass, backward pass, and variable updates. And you can also see a big blue bar called NACO or reduced kernel, which is the gradient aggregation. It's called NACO because, including TensorFlow, every machine learning framework is using NVIDIA NACO or reduced library to aggregate the gradients. So by far, you may already spot the problem, right? This is exactly the power of the TensorBoard profiler, which makes it so visualized and obvious. So the problem here we are facing is that the gradient aggregation time actually dominates the entire step time. All you see is these big blue bars of NACO or reduce. So how do we resolve this issue and optimize the training performance? Here comes the 3 optimizations. First optimization, from the profiler, you can get the information regarding the total time used in NACO or reduce, and you know your model, you know the total size of the model variables and gradients. And then from these 2 information, you can calculate your NACO or reduce throughput. And you also know you use how many machines and each machine, how many GPUs are there. Use these 2 informations, and following the NACO NVIDIA tuning guideline, you can calculate the ideal NACO throughputs. And in this case, we found out that the real NACO or reduced throughput is actually much smaller than the ideal throughput. Then we know that the first optimization is to actually tune your NACO to fully utilize the underlying cross-host network to improve the performance. Second optimization, so if you notice the big blue bar here, it says F32, which means that the gradient aggregation is in the full precision flow 32 format. And we know that the model can be trained with mixed precision, so the gradient can actually be in lower precision like flow 16. So can we actually aggregate a gradient in flow 16, which would efficiently cut the network data that is being transferred by half and thus improve the performance. The third one, if you notice, the neckle-all-reduce is exchange data across the network. And it doesn't even use the GPU itself a lot. So you see an empty space out there above the blue bar. So can we actually push the neckle-all-reduce forward a little bit so that it overlaps with the GPU computation happening in backward path? This way, we can reduce the GPU idle time and improve the training step time. So here is the three ideas. They all look good, and I'm gonna to show how to implement this idea using TensorFlow 2.2. First optimization, Neckle throughput tuning. So TensorFlow 2.2 is shipped with the latest NVIDIA Neckle libraries. And we have done a lot of experiments on Google Cloud VMs to identify a set of recommended parameters to help you reach the peak throughput. Users can append those parameters when running their models, such as the Neckle socket end threads parameter here, appended before the model main.py. So if users has different network environment than the cloud VMs, you might need to run the experiment to find out the optimum parameters. And this is suboptimum, and we are looking to improve that. We are working with NVIDIA to see if we can auto-tune the Neckle parameters. So in future TensorFlow release, users don't need to manually test and set any of these parameters. For now, with the optimum Neckle parameters, we see a dramatic 30% to 30% throughput improvement in bird squad. This is good for just one optimization. So are you excited to see the second optimizations? Okay, here it comes. If you remember, we are looking to aggregate the gradients in lower precision with this flow 16. The prerequisite is that the model is already trained with Keras mixed precision API, and we have an online tutorial following this link to tell you about the technical details and usage of this API. Generally speaking, mixed precision would use two types of floating point number representation during training, flow 32 and flow 16. If you can see from the figure, flow 32 with more data, it can represent larger range of numbers with high precision than flow 16. But flow 16 has its own advantages. Computing flow 16 in modern GPU can be up to 2 to 4x faster than FP32 computation. So this is really a trade-off between the model accuracy and the computing efficiency. But mixed precision API actually try to give you the best of the both worlds. To show the mixed precision under the hood, I will show the bird squad custom training loop code. With this code, user can get the maximum flexibility to change every aspect of the training. And here is the training loop code in TensorFlow 2.1. With mixed precision, your model variable are still kept in flow 32 for best model accuracy. But the computation, including the gradient computation here, are all done in flow 16. And after the gradient computation, the gradients are converted back to FP32 and then apply the gradient updates to the FP32 model variables. The apply gradients API here would actually implicitly aggregate the FP32 gradient for you. This is why you see the gradient is aggregated in FP32 from the previous profile. With TensorFlow 2.2, now you can change the custom training loop code a bit to enable gradient aggregation in flow 16. First, we modify the optimizer apply gradient API. It now takes an argument called all-reduce sum gradients. When you set this argument to false, it essentially tells the optimizer API not to do the gradient aggregation for you. Instead, the user can manually call gradient aggregation API from distribution strategy to do the all-reduce by yourself. And the best thing is that the user can apply any customized gradient operations before and after all-reduce using this manual all-reduce, including what we want to do for gradient aggregation in flow 16. So you simply just need to cast the gradient to FP16 before the all-reduce, do the gradient all-reduce, and then cast the gradient back to FP16. So this is as simple as what you need to do. And as you can see, you may find a lot of gradient casts here from between FP32 and FP16, which is okay because the TensorFlow graph optimization will actually remove the redundant casts under the hood. So you only live with one gradient cast from FP16 to FP32, which anyway you have to do because you are applying gradient to the FP32 model variables. So the cast here is just more for your code readability, but we are not downgrade your performance. Also, I want to make one more point. For advanced user that wants to customize gradient operation, including or reducing FP16, they can use the custom training loop to get maximum flexibility. But for average user who just want the or reduce in FP16 out of the box, so we are working on supporting this in Keras compound fit in the upcoming, in the future releases. So in the future releases, you can get or reduce in FP16 out of the box using Keras compound fit API. So with FP16 or reduce, we are now seeing that the burst squad training throughput is further increased by about 35%. We are now almost 2.2x throughput comparing with the TensorFlow 2.1 by far. But wait, we still got one more optimization. The third optimization, if you still remember, we want to reduce the GPU idle time by overlapping gradient aggregation with the backward computation on GPU. Let's take a look at the deep learning model figure we have seen previously. So in this model, after the TensorFlow calculate the gradient of the layer B, we can immediately send out the gradient of the layer B for aggregation. And at the same time, on your GPU, you can still calculate the gradient of the layer A. So as you can see right now, the network computation of or reduce the gradients of layer B is now run in parallel with the gradient calculation in layer A, and which we can use the GPU resources network both efficiently. To enable this overlap, let's make some more changes to the same custom training loop code in previous optimization. So in TensorFlow 2.2, we introduced these collective hints to the distribution strategy or reduce API by inputting an bytes per pack arguments to the or reduce API. It tells the TensorFlow to break your model gradients into multiple packs, and the TPU TensorFlow runtime will actually send out a pack once this pack of gradient is available in the backward computation. So this is as easy as it looks, just giving it a bytes per pack numbers, right? But the next question would be, what is the optimum bytes per pack to achieve the maximum training throughput? In TensorFlow 2.2, user needs to do some simple experiment to identify the optimum parameter. NVIDIA provide the official NACO or reduce benchmarks. User can get these benchmarks running on their multi-host with their networking environment, and they need to change the data or reduce data size. And typically what user will see, along with increase of the or reduced data size, so does the NACO or reduced throughput. It would also increase with the data size. But up to certain or reduced data size, the NACO throughput will start to plateau, which means that your NACO is reached the limits of your underlying network. And here, the data range of the data size is exactly the optimum pack size, which is sufficiently large to saturate your underlying network. If you set the pack size to be smaller, each gradient pack you send out cannot fully utilize the network, so you are wasting your network bandwidth. If you set the gradient pack larger, then it means that TensorFlow needs to wait for longer time to actually waiting for the first pack of the gradient. It means that you have less overlaps. So we know that the optimum pack size is actually the or reduced pack size that reach the throughput plateau. But this seems to still some work that required from the user. So in future release, we are also working on auto-tune this pack size so that user can get the optimum performance out of the box. So by far, we have seen these 3 optimizations, and it improves the burst squad training throughput by 2.5x. And these optimizations are very useful in public cloud when the networking between the cloud VMs is limited. We are also working on more improvements as I introduced along with the talk. We are going to support Keras compound fit, support auto-tune in NACO parameters and the pack size, all coming in the future releases of TensorFlow. So stay tuned for all more improvements. Next step is talk to a team to actually tell you more about Colab.
Hi, my name is Tim, and I'm the product manager for Colab. For those of you who don't already know, Colab allows you to write and execute arbitrary Python code via the browser. It's hosted Jupyter Notebooks by Google. It's integrated with your Google account, which means if you're signed into Chrome or signed into Gmail, you're already signed into Colab. And it's integrated with Google Drive, which means that when you create a Jupyter Notebook in Colab, it's automatically saved to your Drive account. Colab started in 2012 as an internal tool for data analysts. In 2014, we started using it for our internal machine learning crash course. This is actually where a lot of Googlers first learned TensorFlow. In 2017, we launched it publicly. We wanted the whole world to have access to the same great tool that Googlers were using to get their work done. Colab is easy to use. When you connect with a virtual machine in a Colab notebook, your Python environment is already set up for you. The latest version of CUDA is already installed for you. It just works. So how do we do this? Well, on the back end, we maintain a pool of pre-warmed VMs. These virtual machines have hundreds of popular Python libraries pre-installed, including TensorFlow, TensorBoard, TF Privacy, TF Datasets, and many more. There are resource limits in Colab, and those are there to ensure sustainability and reduce abuse. Without any further ado, here are my top 10 Colab tricks for TensorFlow users. Number 10, always specify your TensorFlow version in Colab. In Colab, when you import TensorFlow, by default, today, it imports a version of TensorFlow 1. But soon, it will, by default, import a version of TensorFlow 2. You can start using TensorFlow 2 in Colab today by specifying your TensorFlow version with the syntax shown on the screen. If you have old Colab notebooks that use TensorFlow 1, and you want those to keep working well after we switch to default TF2, make sure to specify TF 1.x in those notebooks. That will future-proof those notebooks so they'll keep working well. The bottom line, always specify your TensorFlow version in Colab. Number 9, use TensorBoard. Colab output cells can render essentially arbitrary HTML. And the TensorBoard team has taken advantage of this to allow you to use TensorBoard right in line with Colab. It works great, and I highly recommend it. Number 8, TF Lite, no problem. Even though TF Lite is for on-device machine learning, you can still train your TF Lite models in the cloud in Colab. And in fact, that's a popular way to use TF Lite. Number 7, use TPUs. It's free in Colab and very easy to do. You just go to change runtime type and select TPUs from the runtime from the dropdown. If you want to feel the raw power of TPUs under your fingertips, give them a whirl for free in Colab. And with TensorFlow 2.1, TPUs have never been easier to use. Number 6, use local runtimes if you want. If you have your own workstation and your own GPUs, perhaps, and you want to run your workload on your own hardware, that's fine. You can still actually use the Colab UI with a local runtime, and that's easy to do as well. Number 5, the Colab Scratchpad notebook. If you find yourself with Colab notebooks that have names like Untitled 17 and Untitled 18, the Colab Scratchpad notebook might be for you. This is a special notebook available at the URL shown here that's not automatically saved to your Drive account, and it's really great for doing your Scratch work. Number 4, copy your data into your Colab VM. Rather than calling data on external storage at runtime when you're, for example, training your models, first copy all your data into the Colab VM. This can result in speedups even if you're only going to use the data once. Number 3, mind your memory. If you've ever run out of memory in Colab, you may have noticed that perhaps later you were assigned a special high RAM runtime. Well, that may seem like a great thing, but it also means that you're more likely to run into the resource limits of Colab later. So the best thing to do is to not run out of memory at all, and mind your memory when you're doing your work. Number 2, close your tabs when you're done with Colab. This will help you disconnect from the underlying virtual machine sooner. Again, conserving resources makes it less likely that you'll run into the resource limits of Colab. Finally, the number 1 trick, only use GPUs when they're actually needed for your work. Now, of course, when using TensorFlow, often GPUs are needed for your work. But when you're doing work that doesn't require a GPU, just use a default runtime that only has a CPU. Again, conserving resources helps you get the most out of Colab by avoiding later running into the resource limits of Colab. Now, we do hear from users all the time things like, we want faster GPUs, we want more reliable access to P100s, we want longer runtimes, we want more lenient idle timeout periods, and we want longer maximum VM lifetimes. Or we want higher memory with more reliable access to high RAM runtimes. Well, we do hear you, and that's why we recently launched Colab Pro. Colab Pro comes with faster GPUs, longer runtimes, and more memories for $10 a month. We launched it in February, and it's been a big success. It's only available in the United States for now, but we're working as fast as we can to bring it to more countries. All right, so what's next in Colab? Well, first of all, the free version of Colab is not going away. The free version of Colab and Colab Pro will continue to coexist, and we're continuing to work on improving both of them. And as for feature development, well, that's where I would like to hear from you. Tweet at me, send feedback via the product, tweet at Google Colab. However you do it, let us know what you want us to build next in Colab, because it's user feedback from people like you that drives our roadmap going forward. So please let us know what you want next in Colab. All right, that's it from Colab. Next up will be Chris Mattman from NASA and the Jet Propulsion Laboratory.
Hey everybody, this is Chris Mattman, and I'm not able to attend physically the TensorFlow Dev Summit, so I'm giving my talk remotely. My talk is about TensorFlow and machine learning from the trenches. I'm the deputy CTO at the NASA Jet Propulsion Laboratory, and I'm going to talk about our experience using TensorFlow in the Innovation Experience Center at JPL. What's JPL? JPL is a federally funded research and development center. It's NASA's only FFRDC. They call these the National Labs. Its goal is to do first-of-a-kind missions in autonomy, technology development for space, in situ on the ground, remote sensing of the Earth, and various other really nationally critically functions. It's nestled there in the beautiful mountains of La Cañada Flint Ridge. We have about 6,000 employees, about a $2.6 billion business base. We have a pretty large facility, about 167 acres. At JPL, I am the lead for the Innovation Experience Center. I'm the Deputy Chief Technology and Innovation Officer. And what does our Innovation Experience Center look like? Our recipe for it is to find the most difficult space, the space that looks the ugliest, and make it our own. Take it, gut it, have the actual engineers and data scientists put it together and put it back together in the way that they want. Sit-stand desks, basically follow the sun sunshades, IoT internet devices that both frost and unfrost the conference room for smart glass and privacy, and so on and so forth. So that's our team. We're working in all of these areas, and we're really excited to be doing machine learning with TensorFlow. In particular, we're excited in a few different areas. Our organization is responsible for using TensorFlow in the following ways. The first is the M2020 rover that you just see right there. It's now named Perseverance. In that rover, in that clean room, we measure particulates in the air to determine if that we're adding any sort of biocontamination, because we don't want to do that when we send this to another planet. If we discover life, we actually want to do that. So we have small commodity IoT, Internet of Things sensors that are measuring particulates, increasing our ability to do that, increasing the density of the measurements that we have. And we're doing predictions using TensorFlow and machine learning to determine the next measurements, the next contaminations if we had them, and intervening if necessary. In the bottom right, you see our people counter. That's another IoT device. It uses TensorFlow and object detection and facial recognition and so forth to basically count people's heads as they go in and out of our tents at events like our IT Expo and so forth, so that we can tell people when the right times to actually attend these events so that they're not overcrowded. Besides that, we're not just doing institutional things with TensorFlow, we're looking beyond that. Today, our Mars rovers are currently running on what's called the RAD 750 processor. That's a radiation-hardened PowerPC 750-like processor. That's basically the amount of power that we had on an iPhone 1. Tomorrow, we'll have the ability to have high-performance spaceflight computing and the ability to use things like Snapdragons from Qualcomm, so real GPU like a deep learning chips, so that we could do actual computing on board. And if we could do high performance spaceflight computing on board, we could do really cool things like make the rovers intelligent make our rover smart, do things like drive-by science, which you see there highlighted in the right as one of our 3 ongoing tasks and initiatives to use and leverage high-performance spaceflight computing. Can we make rovers smarter? Absolutely, we can. In particular, we can take models like terrain classifiers, which we've built with TensorFlow. We call it Spock. There's a theme here. It's Star Trek. Our terrain classifier Spock is a CNN. It's a convolutional neural network using TensorFlow to do terrain classification, ripples, smooth with rocks, to figure out where the rover should drive and where it shouldn't. We test this in our Arroyo Seco, which is right by JPL, using our test Athena rover. Another TensorFlow-based model that we've been using and leveraging is the Google Show and Tell model for that, which is a combination of a convolutional neural network and LSTM, or recurrent neural network, long short-term memory, to basically do labeling, figure out the labels for a particular image for the rover, and then take the labels and actually learn a sentence description for it so that scientists can review them, and so that the rover, when it's on Mars, can, instead of sending back 200 images a day to plan what to do the next day, it can send back millions of image captions that are scientifically validated and to increase our density of observation. In terms of our terrain classifier, just some examples of that, Spock looks at the geometric features and so forth, and it's actually capable of recognizing terrain types from images. So this is really important both for Mars surface operations, but also to potentially plan where we should do future Mars missions and landings. Beyond that, one of the things we've been really challenged with, and it's been a big area of research for us, is putting TensorFlow models and taking them and porting them to TensorFlow Lite and moving them onto exotic hardware, some of which isn't even physically here and we only have emulators for, like the high-performance spaceflight computing emulator that we've been trying to look at various TensorFlow models like DeepLab, MobileNet V2, and then figuring out how do we port them into a TensorFlow Lite quantized model or TensorFlow Lite floating point model, and measuring the computation time from that. One of our key observations here is that MobileNet V2 tests were conducted on smaller imagery, and actually MobileNet V2 tests performed the fastest of any of the models that we were actually testing when we used TensorFlow Lite in a quantized fashion for that. So we've got ongoing research, and we're working on porting these models into these TF Lite environments. In particular, if we have drive-by science, if our rovers are smarter, and you look on the right, we don't want to miss that unnoticed green monster problem where the rover simply doesn't have enough power to be able to, and light time and bandwidth, it misses recognizing something that actually we really wanted to see, like our little buddy right there in green. And one of the challenges with that is that the rover has an 8-minute light time from round trip from Earth to Mars to basically send it a communication and to hear back from it. So it's got to do a lot of science and things on board. It's got to recognize things even without human intervention. Additionally, our geologists, they've got a headache with too many images and so forth. So having the ability to have the rover be smart, do drive-by science on board, and just send back, again, those textual captions and descriptions of images is really key, because then it can get beyond only being able to send 200 images per day and could actually send millions of captions. In particular, all the work that we're doing on TensorFlow in the book, I've been collecting it, I've been capturing it, and I'm writing a second version of the Machine Learning with TensorFlow book. It's called Machine Learning with TensorFlow 2nd edition. It's currently in the Manning Early Access Program, or MEEP. Please check out the link right there, and I would love for you to, basically ask me any questions. There's an online developer forum for it. Please let me know, and I'd be happy to get back to you. And you know what? I'm not there physically, but you can find me online at Twitter, Chris Mattman, @ChrisMattman, and thank you for giving me the opportunity to present today.
Hi everyone, I'm Paige Bailey, back again for our second Q&A segment of the TensorFlow Dev Summit. I have here Chuman, Alex, and Rohan, and we're really excited to see some of the questions that you've been posting online. So first up, from Ujwal, what is the relationship between TF module, tfkeras.model, and tfkeras.layers.layer? And that sounds like an Alex question.
Hi. So bottom up, tf.module is just a building block for all sorts of weird things in TensorFlow. For example, if you saw my talk, you saw me using a tf.module as a replacement for a variable. An optimizer should be a tf.module. Pretty much anything that can have tf.functions as methods or have tf.variables as members or submembers, it makes sense to represent as a tf.module. We can then do automatic tracking at runtime to find all the variables in your module that your module potentially references. We can save its functions and all sorts of other things. It has no structure on top of this. There's no call method. There's no graph tracking, nothing about shapes. Everything about it is yours to decide. TF Keras.layer builds upon TF.module, but it adds a lot of Keras-specific policy. You want to inherit from TF.Keras.layer if you want your model to interop with the rest of Keras. TF Keras layers, they have a particular method call that is very, very special, that Keras will do all sorts of things around it to make sure it works well with Keras' functional graph building mode, with Keras' training loops. Keras layers can track losses, they can track metrics, they have you can set them as frozen. They have a lot more functionality built in because that functionality is expected of everything that else is going to interop with Keras layers. They have hooks for you to implement Keras serialization, etc. But they are supposed to be building blocks. They're not supposed to be the entire end-to-end thing. And Keras model, which inherits from Keras layer, adds the necessary stuff to make it an end-to-end thing. So models are layers that have a compile method, that have a fit method, that have a train on batch method, and you can use you can attach loss functions and optimizers, and it's the actual big high-level unit. You can subclass model if you want to implement your own model with custom code. You can also build one using the constructor or using one of the subclasses that we provide, like Keras sequential.
Excellent. That's awesome. Thank you so much for that answer. Our second question for Chuman. The profiler looks great, but requires CUDA 10.2. Will TF 2.2 be built against CUDA 10.2? And this is from Sean Morgan, who's our SIG leader for add-ons.
So thank you for the question. So our profiler technically support CUDA 10.1, but only for single GPU. So if your model runs on a single GPU, that's fine, you can use CUDA 10.1. If your model runs on multiple GPU, CUDA 10.2 provides some good improvements, and we recommend you to go straight to CUDA 10.2.
Excellent. And the next question is about multi-worker strategy. So does this approach with multi-worker strategy work only with locally connected workers or with globally distributed workers over public net too?
Sure, I can answer that. So yeah, it works, but my concern would be that it might be a little slow because we rely on the network. And so you will not have the bottleneck on the computation itself, but you might end up having a network level bottleneck because if it's globally distributed, maybe the interconnect speed is not that fast. But sure, we definitely support it and it'll work.
Excellent. Thanks for the question, Philip Ray. And our next one, does automatic vectorization handle non-rectangular loops? Is there any way to get away from padding and packing sequences? This is from James McKean.
So we currently do not handle loops over ragged data. The inputs of your TF vectorized map are expected to be regular tensors. It's very interesting, and I think it's something that we're working on, how to handle ragged data, because you have two alternative options, as you pointed out. You can pad up to the maximum length, and then use regular operations and somehow ignore the information that's in the padded area, or you can pack across the ragged dimension, and then you have to rewrite your operations to apply to the packed data. There are different sets of times when padding is better than packing, and I think we still need to resolve what we're going to do about this before we move on to implementing it.
Excellent. There's a lot of great work being done with ragged tensors, and if you have ideas, make sure to submit them as feature requests on our GitHub repo.
Or RFCs.
Yes, that would be awesome as well. And then our final question from Paul Lopez. Are there any GitHub code examples for fairness with TensorFlow Constrained Optimization Library, or TFCO? And I can answer that. Yes, there absolutely are examples. I believe we have 2 available on GitHub today. So if you go and look at the TFCO repo under Google Research, you should be able to find those. We also just recently released a blog post on the Google AI blog. I believe it was just a couple of weeks ago, specifically around TFCO and some of the interesting applications that we've seen with the tool. So if you have any interest in learning more, please go and check out those resources. And if you create your own example, we are always excited to see it. Make sure to tweet it out, and we will take a look and potentially consider adding it to the official models repo, or the official examples repo, rather. So I believe that's it for today. Thank you so much for listening to our second Q&A session. We have a ton of great talks planned for the rest of the day, and hopefully you've enjoyed what you've seen so far. Make sure to send additional questions with the Ask TensorFlow hashtag, and also be sure to tweet your favorite impressions from the day with TF Dev Summit as the hashtag. Thanks again. I've been Paige Bailey. These are our awesome speakers, and keep building with TensorFlow.
Neural networks have emerged as an effective and promising approach to many machine learning tasks, including computer vision, language understanding, or classification in general. In this video series, we are going to introduce a new learning framework to you called neurostructured learning, which enables neural nets to learn with structured signals for improving model quality and robustness. I am Da Chen, and I'm going to be your guide. You do not need to know a lot to get started, and we will be coding with Python language. Don't worry, you have never used it. It's simple to understand, and you will be up and running in no time. So let's get started with a simple example. Consider you are creating a neural network to classify an image into a cat or a dog. Like this figure shows, the image is fed into the neural net, activating neurons layer by layer, forming several activation paths that determine this image to be classified as a cat or a dog. Seems pretty straightforward, isn't it? What if I tell you there are other similar images related to this input image? That is, there is actually a structure, for example, a graph, representing the similarity among all these images. And as you can see, all these images are English bulldogs. So, is it possible that we can make a neural net learn better with the whole structure in addition to just using one image? And the answer is yes, through neurostructured learning framework. Neurostructured learning jointly optimizes sample features and the structure signals existed among samples in order to learn a better neural net. Specifically, we now have two types of input for a neural net. The first input is the features of a training sample, for example, the pixels of an image. And the second input is the structure, for example, the graph representing the similarity among samples. Both the features and the structure will be fed into a neural net for training. You may now have a question. We know in a neural net, the input features are used to activate the neurons layer by layer for making a classification. But how do we use the structure to help a neural net learn? The structure is used to regularize the training of a neural network. Don't worry if you are not familiar with this concept. We are going to provide more details to you about this whole training process. Are you ready? First, each training sample is augmented to include its neighbor information from a given structure. Specifically, the neighbor information here refers to the features of a neighbor. So we get a new training batch where both the original training samples and their neighbors are included. Next, both the training sample and its neighbors are fed into the neural net. After the training sample is fed into the neural net, its features activate different neurons, layer by layer, forming an embedding representation for this sample. If you're not familiar with the concept of embedding layers, just think of it as a new representation formed by the second to last layer of a neural net. The neighbor is processed in the same way, so we will have an embedding representation for the neighbor as well. Then, the difference between the sample's embedding and its neighbor's embedding is calculated and added into the final loss as a regularization term. So what is the intuition here? By adding this regularization term, the neural network learns to keep the similarity between a sample and its neighbor. In other words, the neural net learns to maintain the local structure of a sample and its neighborhood. By leveraging these structure signals, neural nets can learn with less label data and also be more robust. We also provide several hands-on tutorials to guide you step by step how to use the neural structure learning framework. In the next video of this series, we will take what you have learned and apply that to a language understanding problem, classifying the topic of a document. You will find a tutorial for that in the description below, as well as more information on getting started with neural structure learning.
Hi, I'm Arjun Gopalan, and welcome to episode 2 of Neural Structured Learning. In the previous episode, you learned about what neural structured learning is and how this new learning paradigm can be used to improve model accuracy and robustness. In this episode, we'll discuss how neural structured learning can be used to train neural networks with natural graphs. Before we begin, let's define what a natural graph is. Essentially, it's a set of data points that have an inherent relationship with each other. The nature of this relationship can vary based on the context. Social networks and the World Wide Web are classic examples that we interact with on a daily basis. Beyond these examples, they also occur in data that is commonly used for many machine learning tasks. For instance, if we are trying to capture user behavior based on their interactions with data, it might make sense to model the data as a co-occurrence graph. Alternatively, if we are working with articles or documents that contain references or citations to other documents or articles, then we can model the dataset as a citation graph. Finally, for natural language applications, we can define a text graph where nodes represent entities and edges represent relationships between pairs of entities. Now that we understand what natural graphs are, let's look at how we can use them to train a neural network. Consider the task of document classification. This is a problem that frequently occurs in a multitude of contexts. As an example, machine learning practitioners might be interested in categorizing machine learning papers based on a specific topic, such as computer vision or natural language processing, or even reinforcement learning. And often, we have a lot of these documents or papers to classify, but very few of them have labels. So how can we use neural structured learning to accurately classify them? The key idea is to use citation information, whose existence is what makes the dataset a natural graph. What this means is that if one paper cites another paper, then both papers likely share the same label. Using such relational information from the citation graph leverages both labeled as well as unlabeled examples. This can help compensate for the insufficiency of labels in the training data. You might be wondering, well, all this sounds great, but what does it take to actually build a neural structured learning model for this task? Let's look at a concrete example. Since we're dealing with natural graphs here, we expect a graph to already exist in the input. The first step then is to augment the training data to include graph neighbors. This involves combining the input citation graph and the features of the documents to produce an augmented training dataset. The Packed Neighbors API in neural structured learning handles this. And notice that it allows you to specify the number of neighbors used for augmentation. In this example, we use up to 3 neighbors. The next step is to define a base model. In this example, we have used Keras for illustration, but neural structured learning also supports the use of estimators. The base model can be any type of Keras model, whether it's a sequential model, a functional API-based model, or a subclass model. It can also have an arbitrary architecture. Once we have a base model, we define a graph regularization configuration object, which allows you to specify various hyperparameters. In this example, we use 3 neighbors for graph regularization. Once this configuration object is created, you can wrap the base model with the graph regularization wrapper class. This will create a new graph Keras model whose training loss includes a graph regularization term. You can then compile, train, and evaluate the graph Keras model just as you would with any other Keras model. As you can see, creating a graph Keras model is really simple. It requires just a few extra lines of code. A Colab-based tutorial that demonstrates document classification also exists on our website. You can find that in the description below. Feel free to check it out and experiment with it. In summary, we looked at how we can use natural graphs for document classification using neural structured learning. The same technique can also be applied to other machine learning tasks. In the next video, we'll see how we can apply the technique of graph regularization when the input data does not form a natural graph. That's it for this video. There's more information in the description below. And before we get to the next video, don't forget to hit that subscribe button. Thank you. Hi, I'm Arjun Gopalan, and welcome to episode 3 of Neural Structured Learning. In the previous episode, we learned about natural graphs and how they can be used in neural structured learning. While natural graphs are common, there are many machine learning tasks where the input data does not form a natural graph. For instance, if you recall the document classification task from the previous episode, we used citations to form a natural graph. In the absence of citations, we wouldn't have had a graph. Similarly, if we're doing simple image classification or text classification, where the input data contains just raw images or text, then we may not have a natural graph in either case. In this episode, we'll discuss how we can apply neural structured learning to such tasks. So what do we do if we don't have a natural graph to begin with? The title of the video might have given this away, but the main idea is to build or synthesize a graph from the input data. Building a graph can be done in many ways, but in this video, we'll use the notion of similarity between instances to build a graph. In order to define a similarity metric, we need to convert raw instances, whether they are documents, text, or images, to corresponding embeddings or dense representations. We can do this using pre-trained embedding models, such as those on TensorFlow Hub. Once we convert raw instances to their embeddings, we can use a similarity function, such as the cosine similarity, to compare how similar pairs of embeddings are. If the similarity score is greater than a threshold, then we add a corresponding edge in the resulting graph. Repeating this process to cover the entire dataset builds a graph. And once we have a graph, using neural structured learning is straightforward, as we saw in the previous episode. Let's illustrate this workflow for the task of sentiment classification using the IMDb dataset. This dataset contains movie reviews, and the task is to classify them as good or bad. Let's see what the code looks like to build a neural structured learning model for this task. Here again, we use Keras for illustration, but neural structured learning also supports estimators. The first step is to load the IMDb dataset. For simplicity, we use a version of it that is part of Keras. Once that is done, we want to convert the raw text in the movie reviews to embeddings. We use swivel embeddings in this example, but any other embedding model, such as BERT, Word2Vec, or an embedding model of your choice, may also be used instead. Once we have created the embeddings, we can build a graph using those embeddings. Neural structure learning provides an API called buildGraph to do so. Notice that it accepts a similarity threshold as one of its arguments. This allows you to control the threshold below which edges are dropped from the resulting graph. In this example, we use a threshold of 0.8. Once we have the graph, we define the features of interest for our model and combine these features with the graph using the Pack Neighbors API in neural structure learning. In this example, we use a maximum of 3 neighbors to augment our training data. Now that we have the augmented training data, the next step is to create a graph regularized model. This part is similar to what we did in the previous episode. First, we define a base model, which can be any type of Keras model, whether it's a sequential model, a functional API-based model, or a subclass model. It can also have an arbitrary architecture. Then, we define a graph regularization configuration object, which allows you to specify various hyperparameters. In this example, we use 3 neighbors for graph regularization. Once this configuration object is created, you can wrap the base model with the graph regularization wrapper class. This will create a new graph Keras model whose training loss includes a graph regularization term. What's left is then just compiling, training, and evaluating the graph regularized model. This example is also available as a Colab-based tutorial on our website. You can find that linked in the description below. In summary, we looked at how to build a graph regularized model when the input data does not form a natural graph. This technique can be applied to all kinds of input data, such as text, images, and videos. Now, graph building is not the only approach to handle input data that does not form a natural graph. In fact, in the next video, you will learn about another aspect of neural structured learning called adversarial learning, which can be very useful to improve a model's robustness to adversarial attacks. That's it for this video. There's more information in the description below. And before you get to the next video, don't forget to hit that subscribe button. Thank you.
Welcome to the 4th episode of Neural Structure Learning series. In this video, we are going to talk about learning with implicit structure signals constructed from adversarial learning. I'm Da Chen, and I'm going to be your guide. You do not need to know a lot about adversarial learning to get started, and we will learn the concept along the way. Let's first quickly refresh the concept of neural structure learning. This is the example we mentioned in the first episode, building a neural net to classify an image into a cat or a dog. In reality, there are usually other similar images related to that input image, forming a structure that represents the similarity among all these images. And the neural structure learning framework jointly optimizes the sample features and the structure signals existed among the samples to learn a better neural net. You may want to ask, what if there's no explicit structure we can use to train a neural net? One approach is to construct the structure dynamically by creating adversarial neighbors. You may have another question, what is an adversarial neighbor? An adversarial neighbor is a modified version of the original sample, which targets at misleading the neural net to make it output incorrect classification. And the next straight line question is, how to generate such adversarial neighbors? We craft a small amount of carefully designed perturbation, usually based on the reverse gradient direction, and apply that perturbation to the original sample. Let's look at an example. Say, the sample is a panda image. The constructed adversarial neighbor also looks like a panda image. Usually, human eyes cannot tell the difference between the two. However, the neural net is confused by the adversarial neighbor and classifies it incorrectly into a gibbon. This is because the small perturbation applied on the sample successfully confuses the model, even that we human cannot detect it. After the adversarial neighbor is generated, we add an edge to connect the sample with its adversarial neighbor to dynamically construct the structure. Then this structure can be used in the neural structure learning framework. Let's pause for a bit and ask ourselves, why do we want to have a structure connecting the sample with its adversarial neighbor? In the neural structure learning framework, the neural net learns to maintain a structure by keeping the similarity between the sample and its neighbor. So essentially, this is telling the neural net the sample and its adversarial neighbor are actually pretty similar. So please keep their similarity and don't be confused by the small perturbation. In the neural structure learning framework, there are TensorFlow library and functions that you can use to generate adversarial neighbors. We also provide Keras APIs that you can use to enable easy-to-use end-to-end training with adversarial learning. If you are interested in the details of these library and APIs, please visit our website. Let's use a task in computer vision to see how the adversarial learning works. Say, we want to train a neural net to recognize these handwritten digits. In the next slide, we are going to write some Python code to design this neural net and train it with the adversarial learning. Are you ready? In this code example, we are going to train a neural net to recognize the handwritten digits using adversarial learning. First, we load the MNIST dataset that contains the image of the handwritten digits and their corresponding labels. The features of each image are pixels, with the values ranging from 0 to 255. So here, we normalize these features so that they will stay in the range from 0 to 1. Next, we build a neural net by using Keras APIs. You can use Keras sequential APIs, functional APIs, or build your model via subclassing. The neural structure learning framework supports all three types of Keras APIs, so feel free to use your favorite one. Here, we invoke the Keras APIs from the neural structure learning framework to enable adversarial learning. There are several hyperparameters we need to configure. For example, we need to specify the multiplier applied on the adversarial regularization. For each hyperparameter, we also provide the default values that empirically we know they work pretty well. Then we invoke adversarial regularization from the neural structure learning framework to wrap around the neural net we just constructed. After that, the rest of the workflow follows the standard Keras workflow: compile, fit, and eval. That's it. With the APIs from the neural structure learning framework, we are able to enable adversarial learning within 3 lines of code. Let's take a look at the comparisons between the neural nets trained with and without adversarial learning. The true label of this image is a 6. Both the baseline model and the model with adversarial learning correctly recognize this image as a 6. The next image is a 9. Again, both models correctly recognize this image as a 9. Let's see the third image. This image is actually an adversarial image. The baseline model is confused and recognizes it incorrectly as a 5, whereas the model with adversarial learning successfully recognizes it as a 6. Let's look at one more image. This image is again an adversarial image. The baseline misclassifies it as an 8, whereas the model with adversarial learning correctly classifies it as a 3. So yes, adversarial learning indeed makes a neural net more robust against this small but misleading perturbation. To summarize, in this video, we introduce how to construct the structure by generating adversarial neighbors. We also guided you through a code example using the API from the Neural Structured Learning Framework to enable adversarial learning. Here's more information in the video description below, along with the link to a Colab tutorial covering the example we discussed. Don't forget to subscribe to this channel. Thank you.
You've probably heard a lot about AI and machine learning over the last few months, and maybe you've been inspired by videos showing what's possible with AI and machine learning. But what is it really? Once you go beyond the hype and get down to writing code, what does AI really look like? Well, that's what we're going to go through in this video series, where we'll teach you what it's like to write code for machine learning and how it provides different, new, and exciting scenarios that will help you write applications that behave more like a human being, giving you artificial intelligence. I'm Lawrence, and I'm going to be your guide. You don't need to know a lot to get started, and we'll be using the Python language. Don't worry if you've never used it. It's super simple to understand, and you'll be up and running in no time. So let's start with a very simple example. Consider you're creating a game of rock, paper, scissors. When you play this with a human, it's very basic. Every child can learn it in just a few minutes. Now let's take a look at the most basic part of a game that the human brain is really good at, and that's recognizing what it's actually looking at. So consider these images. Most people can look at them and instantly recognize which ones are rock, which ones are paper, and which ones are scissors. But how would you program a computer to recognize them? Think about all of the diversity of hand type, skin color, and even people who do scissors like me with their thumb sticking out, and people who do scissors with their thumb in. If you've ever written any kind of code, you'll instantly realize that this is a really, really difficult task. It might take you thousands or tens of thousands of lines of code, and that's just to play rock, paper, or scissors. So what if there was a different way to teach a computer to recognize what it sees? What if you could have a computer learn in the same way that a human does? That's the core of machine learning and the path to artificial intelligence. So traditional programming looks like this. You have data, for example, a feed from the webcam, and you have rules that act on this data. These rules are expressed in a programming language and are the bulk of any code that you write. Ultimately, these rules will act on the data and give you an answer. Maybe it sees a rock, maybe it sees a paper, and maybe it sees scissors. But what if you turn this diagram around, and instead of you as the programmer figuring out the rules, you instead give it answers with the data and have the computer figure out what the rules are? That's machine learning. So now I can have lots of pictures of rocks and tell a computer that this is what a rock looks like, and this is what paper looks like, and this is what scissors looks like. And I can have a computer figure out the patterns that match them to each other. Then my computer will have learned to recognize a rock, paper, and scissors. That's the core of building something that uses machine learning. You get a set of data that has patterns inherent in it, and you have a computer learn what those patterns are. Before we write a neural network that learns something as complex as rock, paper, and scissors, let's use a much simpler example. Take a look at these numbers. There's a relationship between the x and y values. Can you see it? It's actually y equals 2x minus 1. So if you saw it, how did you get that? Maybe you noticed that the y value increases by 2, while the x value only increases by 1, so it was y equals 2x plus or minus something. And then you may have seen that when x was 0, y was minus 1, so you figured y equals 2x minus 1 would be a good guess, and then you took a look at the other numbers and saw that it worked. That's exactly the principle that all machine learning works on. So let's take a look. This is the entire code that you can use to create a machine-learned model that figures out what matches these numbers to each other. Don't worry if some of it doesn't look very familiar right now, you'll be able to pick that up in no time. This first line defines the model itself. A model is a trained neural network, and here we have the simplest possible neural network, which in this case is a single layer indicated by the keras.layers.dense code. And that layer has a single neuron in it, indicated by units equals 1. we also feed a single value into the neural network, which is the x value, and we'll have the neural network predict what the y would be for that x. So that's why we just say that the input shape is one value. When you compile the model, there are two functions, the loss and the optimizer. These are the key to machine learning. How machine learning works is that the model will make a guess about the relationship between the numbers. For example, it might guess that y equals 5x plus 5. And when training, it will then calculate how good or how bad that guess is using the loss function. And then it will use the optimizer function to generate another guess. The logic is that the combination of these two functions will slowly get us closer and closer to the correct formula. And in this case, it will go through that loop 500 times, making a guess, calculating how accurate that guess is, and then using the optimizer to enhance that guess, and so on. The data itself is set up as an array of x's and y's, and our process of matching them to each other is in the fit method of the model. We literally say, fit the x's to the y's, and try this 500 times. When it's done, we'll have a trained model. So now you can try to predict a y value for a given x. What do you think would happen if you tried this line of code, predict the y when x equals 10? You might think that the answer is 19, right? But it isn't. It's actually something like 18.9998. It's close to 19, but it's not quite there. Why do you think that would be? Well, the computer was trained to match only 6 pairs of numbers. It looks like a straight line relationship between them for those 6, but it may not be a straight line for values outside of those 6. There's a very high probability that it's a straight line, but we can't be certain. And this probability is built into the prediction, so it's telling us a value very close to 19 instead of exactly 19. Try the code out using the link in the description below this video to see it for yourself. This is something you'll see a lot more of in machine learning. In the next video in this series, we'll take what you've learned and apply that to a more interesting problem, computer vision, and seeing how you can teach a computer to see things using exactly the same methodology as you used here. We'll see you in that video, and don't forget to hit that subscribe button. Thank you. Hi everyone, and welcome to episode 2 of TensorFlow Zero to Hero. In the last episode, you learned about machine learning and how it works. You saw a simple example of matching numbers to each other and how, using Python code, a computer could learn, through trial and error, what the relationship between the numbers was. In this episode, you're going to take it a little further by teaching a computer how to see and recognize different objects. For example, look at these pictures. How many shoes do you see? You might say 2, right? But how do you know they are shoes? Imagine if somebody had never seen shoes before. How would you tell them that despite the great difference between the high heel and the sports shoe, they're still both shoes? Maybe they would think, if it's red, it's a shoe, because all they've seen are these two and they're both red. But of course, it's not that simple. But how do you know that these two are shoes? Because in your life, you've seen lots of shoes and you've learned to understand what makes a shoe a shoe. So it follows logically that if we show a computer lots of shoes, it will be able to recognize what a shoe is. And that's where the dataset called Fashion MNIST is useful. It has 70,000 images in 10 different categories. So there's 7,000 examples of each category, including shoes. Hopefully, seeing 7,000 shoes is enough for a computer to learn what a shoe looks like. The images in Fashion MNIST are only 28 by 28 pixels, so they're pretty small. And the less data used, the faster it is for a computer to process it. That being said, they still lead to recognizable items of clothing. In this case, you can still see that it's a shoe. In the next few minutes, I'll show you the code that will teach you how to train a computer to recognize items of clothing based on this training data. The type of code you write is almost identical to what you did in the last video. That's part of the power of TensorFlow that allows you to design neural networks for a variety of tasks with a consistent programming API. We'll start by loading the data. The Fashion MNIST dataset is built into TensorFlow, so it's easy to load it with code like this. The training images is a set of 60,000 images, like our ankle boot here. The other 10,000 are a test set that we can use to check to see how well our neural network performs. We'll see them later. The label is a number indicating the class of that type of clothing. So in this case, the number 9 indicates an ankle boot. Why do you think it would be a number and not just the text ankle boot? There's two main reasons. First, computers deal better with numbers. But perhaps more importantly, there's the issue of bias. If we label it as ankle boot, we're already showing a bias towards the English language. So by using a number, you can point to a text description in any language as shown here. Can you guess all the languages that we used here? When looking at a neural network design, it's always good to explore the input values and the output values first. Here we can see that our neural network is a little more complex than the one in the first episode. Our first layer has the input of shape 28 by 28, which, if you remember, was the size of our image. Our last layer is 10, which, if you remember, is the number of different items of clothing represented in our dataset. So our neural network will kind of act like a filter, which takes in a 28 by 28 set of pixels and outputs one of 10 values. So what about this number, 128? What does that do? Well, think of it like this. We're going to have 128 functions, each one of which has parameters inside of it. Let's call these F0 through F127. What we want is that when the pixels of the shoe get fed into them, one by one, that the combination of all of these functions will output the correct value, in this case, 9. In order to do that, the computer will need to figure out the parameters inside of these functions to get that result. And it will then extend this to all of the other items of clothing in the dataset. The logic is, once it has done this, then it should be able to recognize items of clothing. So if you remember from the last video, there's the optimizer function and the loss function. The neural network will be initialized with random values. The loss function will then measure how good or how bad the results were, and then with the optimizer, it will generate new parameters for the functions to see if it can do better. You've probably also wondered about these, and they're called activation functions. The first one is on the layer of 128 functions, and it's called ReLU, or Rectified Linear Unit. What it really does is as simple as returning a value if it's greater than 0. So if that function had 0 or less as output, it just gets filtered out. And softmax has the effect of picking the biggest number in a set. The output layer in this neural network has 10 items in it, representing the probability that we're looking at that specific item of clothing. So in this case, it has a high probability that it's item 9, which is our ankle boot. So instead of searching through to find the largest, what softmax does is it sets it to 1 and the rest to 0, so all we have to do is find the 1. Training is then very simple. We fit the training images to the training labels. This time we'll try it for just 5 epochs. Remember earlier we had 10,000 images and labels that we didn't train with? These are images that the model hasn't previously seen, so we can use them to test how well our model performs. We can do that test by passing them to the evaluate method like this. And then finally, we can get predictions back for new images by calling model.predict like this. And that's all it takes to teach a computer how to see and recognize images. You can try this out for yourself in the notebook that I've linked in the description below. Having gone through this, you've probably seen one drawback, and that's the fact that the images are always 28 by 28 grayscale with the item of clothing centered. So what if it's just a normal photograph and we want to recognize its contents, and you don't have the luxury of it being the only thing in the picture as well as being centered? That's where the process of spotting features becomes useful, and the tool of convolutional neural networks is your friend. You'll learn all about that in the next video, so don't forget to hit that subscribe button, and I'll see you there. Hi, and welcome to episode 3 of Zero to Hero with TensorFlow. In the previous episode, you saw how to do basic computer vision using a deep neural network that matched the pixels of an image to a label. So an image like this was matched to a numeric label that represented it like this. But there was a limitation to that. The image you were looking at had to have the subject centered in it, and it had to be the only thing in the image. So the code you wrote would work for that shoe. But what about these? It wouldn't be able to identify all of them because it's not trained to do so. For that, we have to use something called a convolutional neural network, which works a little differently than what you've just seen. The idea behind a convolutional neural network is that you filter the images before training the deep neural network. After filtering the images, features within the images could then come to the forefront, and you would then spot those features to identify something. A filter is simply a set of multipliers. So for example, in this case, if you're looking at a particular pixel that has the value 192, and the filter is the values in the red box, then you multiply 192 by 4.5 and each of its neighbors by the respective filter value. So its neighbor above and to the left is 0, so you multiply that by -1. Its upper neighbor is 64, so you multiply that by 0, and so on. Sum up the result and you get the new value for the pixel. Now this might seem a little odd, but check out the results for some filters, like this one, that when multiplied over the contents of the image, it removes almost everything except the vertical lines. And this one, that removes almost everything except the horizontal lines. This can then be combined with something called pooling, which groups up the pixels in the image and filters them down to a subset. So for example, max pooling 2x2 will group the image into sets of 2x2 pixels and simply pick the largest. The image will be reduced to 1/4 of its original size, but the features can still be maintained. So the previous image, after being filtered and then max pooled, could look like this. The image on the right is 1/4 the size of the one on the left, but the vertical line features were maintained, and indeed they were enhanced. So where did these filters come from? And that's the magic of a convolutional neural network. They're actually learned. They're just parameters like those in the neurons of a neural network that we saw in the last video. So as our image is fed into the convolutional layer, a number of randomly initialized filters will pass over the image. The results of these are fed into the next layer, and matching is performed by the neural network. And over time, the filters that give us the image outputs that give the best matches will be learned, and the process is called feature extraction. Here's an example of how a convolutional filter layer can help a computer visualize things. You can see across the top row here that you actually have a shoe, but it has been filtered down to the sole and the silhouette of a shoe by filters that learned what a shoe looks like. You'll run this code for yourself in just a few minutes. Now let's take a look at the code to build a convolutional neural network like this. So this code is very similar to what you used earlier, where you have a flattened input that's fed into a dense layer that in turn is fed into the final dense layer that is our output. The only difference here is that I haven't specified the input shape. That's because I'll put a convolutional layer on top of it like this. This layer takes the input, so we specify the input shape. And we're telling it to generate 64 filters with this parameter. That is, it will generate 64 filters and multiply each of them across the image. Then, each epoch, it will figure out which filters gave the best signals to help match the images to their labels in much the same way it learned which parameters worked best in the dense layer. The max pooling to compress the image and enhance the features looks like this. And we can stack convolutional layers on top of each other to really break down the image and try to learn from very abstract features like this. With this methodology, your network starts to learn based on the features of the image instead of just the raw patterns of pixels. 2 sleeves, it's a shirt. 2 short sleeves, it's a t-shirt. Sole and laces, it's a shoe, that type of thing. Now, we're still looking at just the simple images of fashion at the moment, but the principles will extend into more complex images, and you'll see that in the next video. But before going there, try out the notebook to see convolutions for yourself. I've made a link to it in the description below. And before we get to the next video, don't forget to hit that subscribe button. Thank you. Hi everybody, and welcome to the fourth and final video in this series of Zero to Hero with TensorFlow. I'm Lawrence, and today we're going to look back at the very first problem that we spoke about, and then we'll see how we can build a machine-learned model to solve it. Remember this, all the way back in episode 1, where we showed a scenario of rock, paper, and scissors and discussed how difficult it might be to create an application that recognizes hands of different shapes, sizes, ethnicities, decorations, and more. We discussed how difficult it would be to write code to detect and classify these, even for something as simple as a rock, paper, or scissors. But since then, you've looked into machine learning and you've seen how to build neural networks, first to detect patterns in raw pixels to classify them, and then to detect features using convolutions to have a convolutional neural network trained to spot the particular features that make up an item, like the soles of a shoe. Let's put all that together, and in this video, we'll see how to create a neural network that is trained on data of rock, paper, and scissors to detect and spot them. We'll start with the data. There's a data set here that has several hundred images of rock, paper, and scissors poses. We'll train a neural network with this data. So first of all, we have to download the zip files containing the data. The code to do that is here. One file has the training set, the other has a testing and validation set. In Python, you can unzip a file with the zip file library, and we unzip them to a temp directory like this. This creates folders with subfolders of each of our categories. When training in TensorFlow using an image data generator, it will automatically label the images based on the name of their parent directory, so we don't need to create labels for the images. It's a really nice shortcut. So I'll achieve that with this code. This creates an image data generator that generates images for the training from the directory that they were downloaded to. We can then set up something called a training generator, which, as its name suggests, creates training data from that. We can do exactly the same for the test set with this code. Later, when you see the model.fit, you'll see that we pass these in as the training and validation parameters. Now let's look at our neural network definition. This is very like what you saw in the last video, just with more layers. One reason is that the images are more complicated than the grayscale clothing you saw previously, and another is that they're bigger. You can see that our input is now 150 by 150. Our images are certainly bigger than they were before. And our output is a layer of 3 neurons. Well, why would that be? Because there are 3 classes, rock, paper, and scissors. Between these, the code is very similar to what you saw previously, just more of it. So we have 4 layers of convolutions, each with max pooling, before feeding into a dense layer. The dropout is a little trick to improve the efficiency of a neural network by throwing away some of the neurons. We'll compile the neural network as before with this code, and then we can fit the data with the model.fit call. Note that we don't have labels. That's because we're using the generator. It's inferring the labels from the parent directories of both the training and the validation datasets. When you run this, you'll probably get accuracy of about 100% on the training data quite quickly, with the validation data getting to about 87% accuracy. This is something called overfitting, which happens when the model gets really good at spotting what it has seen before, but it's not so great at generalizing. Think about it this way. So for example, if all your life, the only shoes you had ever seen were hiking boots, you probably wouldn't recognize high heels as shoes. You would be overfitting yourself. There are a number of methods to avoid this, and one of them is called image augmentation. And I've put the code for this into the notebook for you to try yourself to see how it helps avoid overfitting. Once your model is trained, you can then call model.predict to see how well it spots rock, paper, or scissors. This code will take an image, reformat it to 150 by 150, which the model is trained for, and it will then return a prediction. And here's a few examples that I ran so that you can see that it's actually predicting quite well. But the best thing to do is to try it for yourself. I've put a link to the notebook in the description below, and you can use this code to train a neural network to recognize rock, paper, and scissors images. That's it for this short series of videos. I hope it was useful for you to see the new programming paradigm that is machine learning, and through these examples of computer vision, how you can get yourself on the path to become an artificial intelligence engineer. If you have any questions, please leave them in the comments below, and don't forget to subscribe for more great content. Thank you.
Good afternoon, everybody. I am Jacques, and I'll be filling in for Tatiana today, presenting on MLIR, accelerating TensorFlow with compilers. Now, I don't think I need to tell anybody in this room that machine learning is everywhere. There's a wide range of deployments happening in the industry today, inference and training happening on the cloud and to the edge. We also have models getting larger and larger, and the computational requirements for training these models ever increasing. We see a near exponential growth of the complexity and size and the computational requirements for training these models. Now, if you combine the growth in different deployment strategies as well as models, velocity is a must. We need a faster, more scalable way to build infra to keep up with these bigger, complex models and deployment scenarios. So we need to build these ML systems faster. We want to unify efforts for extensibility and reusability while allowing customization as needed. So we want to be able to standardize representation of some basic concepts, such as operations and types. What defines an operation? How do you define an operation or a type? We want to create a common framework of reusable passes that you can combine to create your own solutions. And also, we want to make it such that it's fully customizable and extensible. The deployment scenarios and models of 5 years ago differ greatly from what we have today. And so we want a system that's able to scale and adapt for all the future needs. With that, enter MLIR. We designed MLIR, which stands for Multi-Level Intermediate Representation. It's an intermediate representation and compiler framework for TensorFlow and beyond. It's part of the LLVM project. So what is MLIR? And why do we believe it's a compiler infrastructure for machine learning? Well, for one, MLIR is state-of-the-art compiler technology. It's not just a serialization format, and there's nothing like it. MLIR is modular and extensible. You can build different solutions using MLIR, building blocks that suit your solution. Importantly, MLIR is not opinionated. MLIR does not try and force you into a box. It allows you to create a solution for your problem space. MLIR is also fully customizable. These different deployment scenarios needs different ways of integrating the components, and with MLIR, we want to make it easy for all of these different deployment scenarios to work. Finally, MLIR is part of the LLVM project. It's under neutral governments and effectively on the desk of many compiler developers all around the world already. And the industry agrees. MLIR is strongly supported by our partners. Some of our partners include the largest hardware partners in the world, consisting of 95% of the data center hardware, 4 billion mobile phones, and countless of IoT devices. And importantly, MLIR is an open community of academia and industry all working together to solve this problem of compiling machine learning models. So with MLIR, what do we want to use it for in TensorFlow? Well, we want to use it to build a better TensorFlow. We want to build better user experience as well as better pluggable hardware support. Now, if you're a user, we want to make it easier for you to debug your model. We want to make optimizations transparent and see what's going on. We want to make it, if you have an error message on your optimized model, we want to be able to track it back to your original location, and MLIR's location tracking enables this. And of course, we want faster performance. So going from writing a model to actually being able to get good performance on your hardware is essential. And speaking of hardware, for our hardware partners, we know it's an awesome time. There is so many new generations of accelerators coming up and new accelerators. And we want to make it simpler and easier to integrate with TensorFlow. Because while all the new accelerators are a great time, it's only really interesting when it's usable for our users. And of course, then for researchers, we want to provide a standard infrastructure for research. So going from being able to represent the different optimization passes and running it in an end-to-end workflow on some production models, we want to make it easy for these researchers to try new approaches, see new effects, and if it works well, of course, contribute it. So let's take a little bit of a closer look at MLIR, the progressive lowering, and the infrastructure around MLIR. Now, you've seen this before, like the TensorFlow architecture, and if we zoom in a little bit, we can expand the different components. But let's focus on the parts where MLIR will be used. So a lot of these, as I mentioned before, is the graph representation and optimization format for these TensorFlow models. But then also, particularly in the compilation, so for optimization and conversion passes between different computer frameworks, JIT compilation of modules, as well as actually for writing AOT kernels or generating AOT kernels, or exploiting these handwritten kernels, MLIR will be involved in all of these different parts. So as the previous slide showed, we can and will be using MLIR to do many tasks in TensorFlow, from graph optimizations, operation rewrites and lowerings, graph transformations, bridging frameworks and components, to code generation. So you can think of MLIR as a common graph representation and legalization framework. It's a common set of optimizations and conversion passes, as well as a full code generation pipeline. But importantly, as I mentioned, MLIR is modular. So you can tailor it for your use case. You can use what you need to solve your problems. So for example, you can reconfigure MLIR for a graph rewriting, and that's, for example, how we use it for the new TensorFlow to TensorFlow Lite converter. Just using the parts that we actually need to get the final product that we want. So what about it? So let's talk a little bit about the progressive lowering. MLIR, the ML in MLIR stands for multi-level. MLIR enables you to represent multiple different levels of operations, all in the same IR. So from a TensorFlow operation to XLA HLO to LLVM IR, all can be represented in MLIR. You can lower progressively from one form to another, and you don't need, and all of these can coexist together. So for example, you can have a function that actually has a TensorFlow op, an HLO op, and LLVM IR. This ability to mix and match these different levels of abstractions and dialects gives great power in actually modeling the problems to suit what your hardware specialization needs. But what about XLA? So we're using what we learned from XLA to build MLIR. XLA is a great acceleration tool for models with stable tensor shapes. And so, for example, the TF function API in TensorFlow 2.2 enables great performance improvements exploiting XLA, and we've made sure that they work really well together. And we are working on ensuring that there's full interoperability between MLIR and XLA. And speaking of full interoperability, we are working very hard to make MLIR and all the existing TensorFlow components all interact very well. So whether you want to import and export from a graph, XLA HLO proto, or TF Lite flat buffer, all of these are possible. So you can mix and match your workflows with XLA. Importantly, MLIR allows for open integration at any level of the stack. So you can start with a TensorFlow graph, import it into MLIR, lower it to HLO, mid-HLOs, or go further and lower it to LLVM IR and then cogen. MLIR allows you to hook into any parts of this configuration. And in particular, MLIR does not require that you only use one. So if for your problem you need a combination of these ops, that's possible. So this makes it very easy to incrementally enable MLIR in conjunction with your existing tools. Now let's look at MLIR in action. So we're specifically going to look at the new TF Lite converter as well as the new features provided by MLIR there. Now the new TF to TF Lite converter launched just in February this year. Very excited about it. So starting from a TensorFlow graph model, importing it to MLIR, doing all the optimizations and legalizations, and then finally exporting to TF Lite flat buffer for a TensorFlow Lite runtime to execute. All of these with better error messages, so being able to find out what went wrong during conversions and give more actionable feedback, to support for TensorFlow control flow. You can finally deploy some of these models with control flow on the edge, and also with a new unified quantization workflow. Now, looking ahead beyond the converter, you'll see MLIR in action in a lot of different places in TensorFlow. In particular, I mentioned MLIR as being the graph representation optimization framework in TensorFlow. So we'll be unifying the different graph optimization infrastructure that we have, as well as all the different converters using MLIR. Another part that's very important for us is the partner integration and supporting for new hardware. As I mentioned, new hardware is coming up every day. We want to make it very easy for folks to integrate with TensorFlow. So especially if you're a partner, please reach out to the TensorFlow team if you want to get involved in this discussion. And also for code generation, we're enhancing MLIR. We're looking at more advanced code generation, particularly code generation with dynamic shapes. And MLIR is also integrating very tightly with optimization and cogen with the new TensorFlow runtime. So there's many different ways of getting involved. Like I mentioned, MLIR is an open community. We have open design meetings where everybody can sign in and ask questions. There's talks from the team, from other teams. We have the TensorFlow MLIR special interest group. And of course, we have code on GitHub, both in the LLVM repo as well as the TensorFlow repo. So feel free to send some PRs and fix some bugs and add new features and get involved. And with that, thank you. Next up is Mingxing to tell you all about the new runtime.
All right, who here wants a shiny new runtime? I'm Ming-Shen Hong, tech lead and manager of the TensorFlow runtime team. Today, I'm excited to share with you our new project, codenamed TFRT. As you probably guessed, it stands for none other than TensorFlow Runtime. Some people might tell you that in the world of TensorFlow, runtime is what keeps tensors flowing. I think that if runtime does its job, you should never have to think about it. But since we are here talking about the runtime, let's first take a look at where runtime fits into the TensorFlow stack. Here's a diagram on the training workflow. Runtime can be driven by eager APIs. It can also execute graph programs produced by a graph compiler. Runtime is a low-level component that orchestrates all model execution by calling into the relevant kernels that implement machine learning primitives like matrix multiplications. We're building TFRT to replace the existing runtime, and let's first talk about why. We talked to many of you, our TensorFlow users, and heard from your pain points and requests. First, many of you are pushing the envelope in the performance and scalability of model processing across both eager and graph execution. Second, you're making continuous innovations through the addition of ops and kernels and devices to TensorFlow, and we need to make such extension work more streamlined and productive. And once you're done with the model research and tuning, you want to deploy TensorFlow everywhere across a diverse set of hardware platforms. For those great reasons, we're building a new runtime to help you. A new runtime that provides the performance, extensibility, and unification that you all are looking for. So, how does TFRT fit into the workflow of an ML model? Here, we see the TF training stack again. Through TensorFlow APIs, your program can either eagerly dispatch ops to the runtime, as you can see from the blue arrows on the left side of the diagram, or as the red arrows on the right side show, in the case of graph execution, your program first generates a computational graph, which gets lowered to the optimized target-specific program and then dispatched to the runtime. The optimization and lowering work uses the MLIR compiler framework, which Jack just spoke about in his MLIR talk. Finally, in both execution paths, TFRT will call into a set of kernels to complete the model execution, as the purple arrow shows. Again, the term kernel here refers to device-specific operations like a GPU-based matrix multiplication. TFRT orchestrates the efficient kernel execution over a heterogeneous set of hardware. Now, let's dive a little more into the technical design and look at how we realize the vision of building a performant, extensible, and unified runtime. First, to achieve high performance, we built a lock-free graph executor that supports concurrent op execution with low synchronization overhead. We have also made the eager op dispatch stack very, very thin, and the eager API calls will call into the relevant kernels with minimal runtime overhead. Second, to talk about extensibility, let's first cover some background. Host runtime is the component that drives whole CPU and I/O work, and it also drives locally attached devices through the device runtimes. TFRT keeps device runtimes separate from the host runtime, so that when you add new device runtimes, you don't have to extend the rest of the runtime. The TFRT design also focuses on building common abstractions such as shape functions and kernels to be used in both graph and eager execution. And this way, we get consistent behavior between eager and graph, and also avoid duplicated engineering efforts. Now, if you feel a bit lost in the last slide, don't worry about it. Let's step back and let's look at how these key design decisions will benefit the core TensorFlow use cases. For those of you who care about training, you will see improved performance as well as error reporting, and that should make it easier to debug your models. If you deploy TensorFlow models in production, you'll be glad to see some improved performance and some reduced CPU usage. And I will show you in a benchmarking study shortly. TFRT will also support deployments across a diverse hardware platforms. And in the next couple of slides, I will show you some initial results on serving support. TFRT is integrated into TensorFlow serving to form a flexible, high-performance serving system for production environments. If you follow the orange arrow, it shows a pre-trained model that's loaded into TFRT through TensorFlow Save Model API. Now, the blue arrows show that the serving clients can send requests to the model and get prediction results back. We expect this TFRT integration to be largely transparent to the end users. So TFRT works for serving. How does it perform? In this benchmarking study, we use an MLPerf benchmark model, ResNet 50, and measure the performance of GPU inference over TFRT and compared to the current stack. We chose to use FP16 and a batch size of 1 to focus the performance study on the runtime-related op dispatch overhead. Let's now look at the numbers. Can I have some drum rolls, please? Thank you. I should first note that the current runtime is already highly optimized for graph execution and serving needs. Through multiple runs, it had a respectable average inference time of 3.3 milliseconds. In comparison, TFRT had an average inference time of 2.4 milliseconds. Bam! There you have it. This is a handsome improvement of 28%. And there are more optimizations under the way. Our internal testing also showed that TFRT is scoring favorably over alternatives of TensorFlow on this model. We are very, very excited about this. The performance improvements are due to the more efficient use of multi-threaded CPUs, the asynchronous runtime design, and a general focus of low-level efficiency. While your actual mileage might vary depending on your workloads, this encouraging result helps validate our initial work and prepares us for the ongoing push to make TFRT production ready. I know you're excited too, right? And you're probably wondering, when can I have it? We will ship TFRT this year, and this is going to be an exciting journey. In addition to the maintenance and selected enhancement to the current stack, we plan to build out and integrate TFRT with the TensorFlow stack. As we roll out TFRT, we will initially make it available through an opt-in flag, giving us some time to fix issues and fine-tune the performance. Eventually, it will become the default runtime. We also plan to open source this project in the near future. We would love to get you all more involved. We will keep you updated of our progress through the developers and TensorFlow.org mailing list, so please make sure to join it. And also, if you would like to learn more about TFRT design, please join our deep dive tech talk at the March 19th MLIR Open Design Meeting. The meeting is open to all members of the community. Thank you all, and look forward to following up. Next, you'll hear about TensorFlow Extended.
Hi, everyone. I'm Chris Warkenden, and I'm a product manager on TensorFlow Extended, or TFX.
Hi, my name is Zhitao Li. I'm a tech lead manager from TFX Open Source.
At Google, putting machine learning models into production is one of the most important things our engineers and researchers do. But to achieve this global reach and production readiness, a reliable production platform is critical to Google's success. And that's the goal of TensorFlow Extended, to create a stable platform for production ML at Google, and a stable platform for you to build production-ready ML systems too. So how does that work? Our philosophy is to take modern software engineering and combine it with what we've learned about machine learning development at Google. So what's the difference between writing code and doing machine learning engineering? In coding, you might build something that one person can create end-to-end. You might have untested code, undocumented code, and code that's hard to reuse. In modern software engineering, we have solutions for all of those problems: test-driven development, modular designs, scalable performance optimization, and much more. So how is that different in machine learning development? Well, a lot of the problems from coding still apply to ML. We also have a variety of new problems. We have no problem statements. We might need some continuous optimization. We might need to understand when changes in data will result in different shapes of our models. We've been doing this at Google for a long time. In 2007, we launched Sybil, which was our production scalable platform for production ML here at Google. And since 2016, we've been working on TFX. And last year, we open sourced it to make it even easier for you to build production ML in your platforms. What does it look like in practice? Well, the entirety of TFX as an end-to-end platform runs from best practices all the way through to end-to-end. From best practices, you don't even have to use a single line of Google-developed code in order to get some of the best of TFX, all the way through to end-to-end pipelines that allow you to deploy scalable production-scale ML. This is what a pipeline might look like. On the left side of the screen, you'll see data intake. Then it runs through the pipeline doing things like data validation, schema generation, and much more in order to make sure that you're doing things in a repeatable, testable, consistent way and producing ML production results. So it's hard to believe that we've only been 1 year in open source for our end-to-end pipeline offering, but we have a lot of interesting things that we've done in 2019, including building the foundations of metadata, building basic 2.0 support for things like estimators, as well as launches of fairness indicators in TFMA. But we're definitely not done. In 2020, we have a wide variety of interesting developments coming, including native Keras on TFX, which you'll hear more about from Zhitao later, as well as TensorFlow Lite trainer rewrite and some warm starting, which can make your machine learning training 100 times faster by using caching. But we have something really exciting that we're announcing today, which you may have heard from Megan about in the keynote, which is end-to-end ML pipelines. These are cloud AI platform pipelines. We're really excited about these because they combine a lot of the best of Google AI Platform with TFX to create cloud AI platform pipelines available today. Please check out our blog for more information. You should be able to find it if you just Google Cloud AI Platform Pipelines. And now, could we please cut to the demo?
So I'll be giving an explanation about this demo. This is the Cloud AI Platform Pipelines page. As you see, you can see all your existing Cloud AI Pipeline clusters in this page. We already created one, and this page can be found as AI Platforms Pipelines tab from the left of the Google Cloud Console. If you don't have any pipelines cluster created yet, you can use the New Instance button to create a new one. This gives you a click button experience about creating clusters, which is usually one of the difficult jobs in the past. You can use the config button to create Cloud AI pipelines on Google Cloud. This gives you Cloud AI pipelines based on Kubernetes, runs on Google's GKE. You can choose a cluster to run it from, choose the namespace where you want to create a cluster inside, and choose your name of your cluster. Once you're done, you can simply click deploy and done. Since I already have a cluster, I will open up the pipeline dashboard here. In this page, you can see a list of demo pipelines that you can play with. You can see tutorials about creating pipelines and doing various techniques. And you can use the Pipelines tab from the left to view all your existing pipelines here. Since this cluster is newly created, there is no TFX pipelines in it yet. We are going to use the newly launched TFX templates to create the Cloud AI pipelines in this cluster. This is a Cloud AI notebook. I'm pretty much using this as a Python shell to run some simple Python commands. First, you set up your environments and making sure TFX is properly installed together with some other dependencies, making sure you have environment variables like path properly set up, and the TFX version is up to date. Now, you're making sure you have a Google Cloud project properly configured, and configure the Cloud AI pipelines cluster endpoint. Simply copy that from the URL into the notebook shell. Now we're also making sure we create a Google container image repo so that we can upload our containers to. Once that is done, we can fit the pipeline name and the project directory. Now we can use the template creation to create a new template. Since they are created, I'm going to show the content in the created by the templates. As you see, there are pipeline code in the pipeline.py file. This includes a classical taxi pipeline from TFX with all the components necessary to do production machine learning. There's config.py with some configurations related to Google Cloud, as well as some configuration about TFX itself. Once that is done, we enter the templates directory, making sure all the templates files are there. You can even run some pre-generated unit tests on the features to making sure the configuration looks right. Once that's done, you can then use TFX CLI command to create a TFX pipeline on Google Cloud Pipelines page. This will create a temporary image with all your code and the dependencies, upload them to GCR, then create a pipeline using this container image on the pipelines page. As we see, the pipeline compiles and the creation is successful. And we go back to the pipeline page, click on refresh. Boom, we have our new pipeline. Now, if we click through the pipeline, we are going to see all the TFX components here readily available. We can create a test run on this one and click on the run. You are going to see each of the components, when they run, they will gradually show up on the web page. The first component should be example.gen, CSV example.gen. Yes, it is there. This component has started running. You can click on it. On the tab, you can look at the artifacts, inputs, and outputs, what Kubernetes volumes used for the component manifest, and you can even inspect the logs of component run. We got this example.gen, stats.gen, schema.gen. And now the pipeline entered feature transform and the example validation at the same time. So now all the data preparation is finished. The pipeline enters into the training stage, which is producing a TensorFlow model. If we click on the trainer component, we can even inspect these logs. Now, once trainer is complete, we do some model validation and evaluation using TFX components. And once all the model evaluation is done, we use pusher to push the generated model onto external serving system. So you have a model ready to use in production. You can also use the tabs on the left to navigate on existing experiments, artifacts, and executions. We are going to take a look at the artifacts generated from this pipeline using the artifacts type. So here you can see you have a pipeline. If we click on the model output artifact from trainer, that represents the TensorFlow model. This is the artifact in ML metadata. We can see it's a model artifact produced by trainer. And this is a lineage view of the model. This explains what components produce this model from what input artifacts, and how this artifact is further used by other components, which takes this one as input, and what outputs generated from the downstream components. OK, this is all of the demo. Now I'm going to talk about another important development in TFX, which is supporting native keras. For those of you who are not very familiar with TensorFlow 2, let me capture a little bit of the history. TensorFlow 2 was released in Q3 2019 with a focus on providing a more Pythonic experience. That includes supporting the keras API, an eager execution by default, and a Pythonic execution. So this is a timeline of how TFX open source has been working on supporting all of this. We released the first version of TFX open source in the last Dev Summit, which only supports estimator-based TensorFlow training code. Back to last TensorFlow World, TensorFlow 2.0 was launched, and we started working on supporting the Keras API. Oh, previous slide, please. Previous slide, please. Back to Q4 2019, we released the basic TensorFlow 2.0 support in TFX 0.20. In that version, we supported TensorFlow 2.0 package end-to-end with a limited Keras support with Keras to estimator. And now, in the latest release TFX, I'm happy to release, we are releasing an experimental support of native Keras training end-to-end. So what does that mean? Let's take a deeper look. For data ingestion analysis, everything pretty much remains the same because TFDV, our data analysis library, is model agnostic. For feature transform, we added a new Keras compatible layer in TFT library so that we can transform features in Keras model. This layer will also take care of asset management and model exporting. For training, we created a new generic trainer executor, which can be used to run any TensorFlow training code which exports a saved model. This also covers the training using native Keras API. For model analysis and validation, we create a new evaluator component, which combines both evaluation and model validation capabilities. This new component supports native Keras out of box. And finally, when it gets to model serving validation, we will release a new component called infra-validator. This component can be used to verify inference requests with TensorFlow serving binaries to making sure any exported TensorFlow model can be used correctly in production, including anything trained with native Keras. Now, let's take a look at a case from one of our partners, Conquer Labs. Conquer Labs is a team in SAP Concur that explores new ideas and building prototypes. They help all the developers in SAP Concur using ML effectively in their solutions. To do this, they need a modern machine learning pipeline that secures, scales, and fits in their data platform. They find that TFX with native Keras trainer allows them to do more things. One of the successful stories here is an efficient BERT deployment. With the TF and the Keras, they can create simple models by using TF transform for the data preprocessing, using state-of-the-art models from TensorFlow Hub, and create simple model deployments with TensorFlow serving. The applications here covers some of the sentimental analysis and some of the question and answer type problems. They also created TFX pipelines to build preprocessing steps in exported BERT models. We just published a blog post on this, so feel free to check out the TFX blog post. Another successful story is TFX pipelines for TF-Lite models. This means they can create the TFX pipelines that produce two models, one in saved model format and one in TensorFlow Lite version. This simplifies their pipeline building process and reduces manual conversion steps. One of the most important things for the future of our ecosystem is great partners, like all of you out on the live stream. We hope you will join us to help making TFX work for your use case. Some of the areas we would love your help, including portability, on-prem and multi-cloud, Spark, Flink, HDFS integration, as well as data and model governance. One of the great things about TFX is the wide diversity of the ways it can be used. We have an exciting guest from Marcel from Airbus. He could not be here physically today, but he recorded a video to talk about one of the interesting ways to use TFX, which is TFX in space. For more, here is Marcel.
This is one of the most important moments for everyone involved in manned spaceflight. This is why we at Airbus are working hard and keep on innovating to ensure everyone on that space station is safe and can return back to Earth, to friends and family. Hello everyone, my name is Marcel Rumens, and I have the honor to tell you how Airbus uses anomaly detection with TFX to ensure everyone's safety on board the International Space Station. You might ask yourself, Airbus, space, how does that fit? Well, Airbus actually has many different products, like commercial aircrafts, helicopters, satellites, and we are also involved in manned spaceflight. For example, the Columbus module, which is part of the ISS. It was built and designed by Airbus and finally launched in 2008. It is used for experiments in space, for example, in the field of biology, chemistry, material science, or medicine. As you can imagine, such a module produces a lot of data. To give you an idea, we have recorded between 15 and 20,000 parameters per second for the last 10 years. And every second, we receive another 17,000 parameters. So we are talking about trillions and trillions of data points. But what does this data actually represent? Well, it could be any kind of sensor data. And we want to detect anomalies in it to prevent accidents. Let me give you an example. If you have a power surge in your electrical system, this could cause a fire. If you have a drop in temperature or pressure, this could mean that you have a hole in your module that you need to fix. So it is very important that we detect these anomalies and fix them before something can happen. Because just imagine for a second, it is you up there, 400 kilometers above Earth, and you only have these few inches of metal and plastic to protect you from space, this cold and dark place without any oxygen. If something would have happened to this little protection layer of yours, you would be in a life-threatening situation. This is why we already have countless autonomous systems on board the spacecraft to prevent these kinds of accidents. But with more and more automation, we can handle more complex data streams, increasing our precision of set predictions. But it is not about safety alone. It is also about planability and predictive maintenance. Because the sooner we know that a certain part needs replacement, the sooner we can schedule and plan a supply mission, decreasing the cost of set launches. How does this work? Well, right now this is a manual process. Our automation works in parallel with the engineers. Let me run you through it. We have our database on premise, storing all these trillions and trillions of data points. And then we use a Spark cluster to extract the data and remove secret parts from it, because some things we are not allowed to upload. Then we use TFX on Kubeflow to train a model. First, we use TF transform to prepare the data, and then we use TF estimator to train a model which tries to represent the normal state of a subsystem, so a state without any anomalies. Once we've done enough hyperparameter tuning and we're happy with the model, we deploy it using TF serving. Now, here comes the interesting part. We have the ISS streaming data to ground stations on Earth, which stream the data to our NIFI cluster running in our data center. Here we remove the secret part of the data again, and then stream it into the cloud. In the cloud, we have a custom Python application running on Kubernetes, which does the actual anomaly detection. It will query the model. The model will try to predict the current state of a subsystem based on whatever it has seen in the past. And then using this prediction and the reality coming from the space station, we can calculate a so-called representation error. If this error is above a certain threshold, we can use this as an indicator for an anomaly. Now, if we have an anomaly, we create a report and then compare it against a database of previously happened anomalies, because if something like this happened in the past, we can reuse the information we have on it. And then the final step is to hand this over to an engineer who will then fix the problem. And this is very, very important to us because we are talking about human life on that space station. So we want a human to make the final decision in this process. But this is TF Dev Summit, so I want to have at least one slide about our model architecture. We're using an LSTM-based autoencoder with dropout, and then we replaced the inner layers, so the layers between encoder and decoder, with LSTMs instead of dense layers, because our tests have shown that sequences just better represent the kind of information we have, producing less false positives. What kind of impact did this project have? Well, we have been able to reduce our cost by about 44%. Some of this is projected because, as I said earlier, we're running in parallel right now. But the cost benefit mainly comes from the fact that our engineers can dedicate more and more time on more important, less repetitive tasks. Tasks for which you really need that human creativity and intuition to fix these problems. Also, our response time has decreased. In the past, it could take hours, days, or sometimes even weeks to find and fix a problem. Now we are talking about minutes, maybe hours. Another benefit is that now we have a central storage of all anomalies that ever happened, plus how they have been fixed. This is not just good for our customer, because we have better documentation, but also great for us, because, for example, it simplifies the onboarding process for new colleagues. Next steps, looking into the future. We want to extend the solution to more subsystems and more products, like Bartolomeo, which is the latest addition to the Columbus module and scheduled to be launched later this month. But overall, these kinds of technologies are very important for future space missions, because as plans to go to Moon and Mars become more and more concrete, we need new ways and new technologies to tackle problems like latency and the limited amount of computational hardware on board the spacecraft. Coming back to TFX, we want to integrate more components, for example, the model validator, because now we have more labeled data that allows us to actually do this automatic model validation. And finally, the migration to TF2, which is ongoing, but very important to us because, of course, we want to keep up and use the latest version of TensorFlow. If you have any questions or want to learn more about the challenges we faced during that project, have a look at the Google blog. We will publish a blog post in the coming weeks that goes into more detail than I could do in 10 minutes. Before I close, I want to especially thank Philipp Grasshorn, Jonas Hansen, as well as everyone else of the ISS Analytics team for their incredible work and support, as well as anyone else who helped to prepare this talk. If you have any questions, feel free to find me on the internet, write me those questions, I'm happy to answer them. And also, I will be available in the Q&A section of this live stream. Thank you very much, and goodbye.
Thank you, Marcel, for the great video. And if you want to learn more about TFX, please check out our website, which has all the blog posts, user guide, tutorials, and API docs. Please also feel free to check out our GitHub repo with all the source code and engage with us on the Google group. Now, let's welcome Makoto from Google Cloud AI to talk about TensorFlow Enterprise.
Hello, everyone. My name is Makoto, a software engineer in TensorFlow Enterprise as a part of Google Cloud. Now that we have seen the great story about TensorFlow in production at work and its cool use cases even in space, now I'm going to talk about the enterprise-ready application with TensorFlow Enterprise. So what does it mean to be TensorFlow Enterprise? What is so different? What is so difficult? Well, after talking to many customers, we have identified a couple of key challenges when it comes to enterprise-grade ML. First is the scale and the performance. When it comes to production-grade enterprise applications, oftentimes the size of data, the scale of a model is beyond what fits into my laptop or workstations. As a result, we need to think about this problem differently. Second is the manageability. When developing business applications, it is better to not to have to worry about any nitty-gritty details of infrastructure complexity, including managing software environment and managing multiple machines in clusters and whatnot. Instead, it is desirable to only have to concentrate on the core business logic of your machine learning applications so that it makes the most benefit to your business. Third is the support. If your application is business critical and mission critical, the timely resolution to the bugs and issues and a commitment to stable support for application is essential to continue operating your applications. TensorFlow Enterprise brings a solution to those challenges. Let's take a look at the cloud scale performance. In a nutshell, with TensorFlow Enterprise, we compile and ship a special build of TensorFlow, specifically optimized for Google Cloud. It is purely based on the open source TensorFlow, but it also contains a specialized optimization specifically for Google Cloud machines and services in the form of patches and add-ons. Let's take a look at how it looks like in practice. This code trains a model with potentially very large training data that may be a terabyte of data maintained in Google Cloud storage. As you see it, it is no different from any typical TensorFlow code written with the dataset APIs. Except the path to the training file is pointing to the Google Cloud storage. Under the hood, the optimized I/O reader specifically made for Google Cloud storage is making this performant even with terabyte of training data and make your training very performant. This is another example that with training datasets from BigQuery table, which is the data warehouse which may maintain 100 millions of business data warehouse. This example is a little bit more involved, but still similar to the standard dataset API that all of you are familiar with. So that, your model can still train in your familiar ways, but under the hood, the optimized I/O for Google BigQuery can read many, many millions of rows in parallel in an efficient way and turn into tensors so that your training can continue with the performance. This is a little comparison of the throughput when large data is read from Google Cloud storage, with or without optimization that TensorFlow Enterprise brought in. As you see it, there is a nice throughput gain. The better I/O throughput performance actually translates into the better utilization of processors such as CPUs and GPUs because I/O is no longer the bottleneck of the entire training. What it means is your training finishes faster and your training wall time is shorter. As a result, your cost of training is actually cheaper because the compute cost is proportionate to the wall time that you use the compute resources. Now that you get some ideas about what kind of optimization we were able to make to TensorFlow, specifically for Google Cloud, let's see how you actually get it and how you actually take the benefit of it. We do this through managed services. We deliver TensorFlow Enterprise through a managed environment, which we call a deep learning virtual machine images and container images, where all the environment is pre-managed and pre-configured on top of standard Linux distributions. Most important is it has TensorFlow Enterprise build pre-installed together with all the dependencies, including device drivers and a dependency Python package with correct version combinations or whatnot, as well as configuration to the other services in Google Cloud. Because this is just a normal virtual machine image or container images, you can actually deploy it in many different ways in Google in cloud. Regardless of where you deploy it or how you deploy it, the TensorFlow Enterprise optimization is just there, so you can take the benefit of all the good performance. To get started, you only have to pick the TensorFlow Enterprise image and the desired resources such as CPUs and RAMs, or optionally GPUs. Start the virtual machine in just one command. In the next moment, you can already SSH into the machine that has TensorFlow Enterprise build already pre-installed and pre-configured, and it's ready to use, so that you can immediately start writing your code in the machine. If you prefer a notebook environment, Jupyter Lab is hosted and already started on the VM, actually. So thing you have to do is you have to point, you only have to point your browser to the VM and open up the Jupyter Lab and open up a notebook so that you can start writing your TensorFlow code, taking the benefit of TensorFlow Enterprise. Once you have the satisfactory model after many iterations of experimentations, now is the time to train your model at the full scale. It may not fit into the one machine, and you may want to take the advantage of the distributed training facility that TensorFlow offers, so that it can support the large scale of data in the model. For this, AI platform training is a managed service that takes care of the distributed training clusters and all other infrastructure complexities on behalf of you. More importantly, it drives the same TensorFlow Enterprise container image, which is exactly the same environment you have used to build your actual model. So you can be confident that your model just trains with full scale of data under the managed training service. You simply need to overlay your application code on top of the TF Enterprise container image, then issue one command to start a distributed training cluster. This example is grabbing 10 workers with larger machines per each worker with 8 GPUs attached to each worker to train potentially very large data set for your array applications. This example brings up a distributed training cluster with all TensorFlow Enterprise optimization included with 10 worker distributions. Now that you can train your model in a full enterprise scale, it is a time to make it an end-to-end pipeline to continue running it in production, taking advantage of AI Platform Pipelines and TensorFlow Extended. AI Platform Pipelines is actually hosted on the Kubernetes engine. What that means is it can also drive the exactly same TensorFlow Enterprise container image so that all the optimization is still there, and you can still be confident that your application pipeline just runs because it is all the same environment. After end-to-end application runs in production, the enterprise-grade support becomes essential to mitigate any risk of interruption operation and also to continue operating your application in a business-critical manner. Our way to mitigate this risk is to provide long-term support. With open source TensorFlow, we typically offer 1 year of maintenance window. For TensorFlow Enterprise, we provide 3 years of support that includes critical bug fixes and security patches, and additionally, optionally, we may backport the certain functionalities and features from the future release of TensorFlow as we see demand. As of today, we have TensorFlow Enterprise version 1.15 and 2.1 as a long-term supported versions. If your business is pushing the boundary of AI, and your business is sitting at the cutting edge of AI, where novel application and use cases are critical to your business model, and also your business is heavily relying on being able to continue innovating on this space, we actually want to work with you through the White Glove Service program. We, engineers and creators of both TensorFlow and Google Cloud, are willing to work with your engineers and your data scientists to mitigate any future bugs and issues that we may not have seen yet to support your cutting-edge applications, to unblock you as well as and together advance your applications as well as TensorFlow and TensorFlow Enterprise as a whole. Please check out the website and see for detail of this White Glove Service program. Looking ahead, we are really excited to keep working tightly together between TensorFlow teams and Google Cloud teams. As being the creators and experts and owner of the both products, we continue to make the optimizations and improvement to TensorFlow for Google Cloud. That includes better monitoring and debugging capabilities to your TensorFlow code that runs in cloud, as well as integration integration of this capability into your Google Cloud tooling for the better productivity of your application. We're also looking at smooth integration between TensorFlow popular high-level APIs such as Keras or Keras tuners and managed training services, as well as even more managed services such as a continuation of TensorFlow Dev for the purpose of coherent and joyful developer experiences. Please stay tuned. This concludes my talk about TensorFlow Enterprise. For more information and for details, please do check out the website. Thank you very much. And next up is Tim to talk about TensorFlow Lite for mobile.
Hi everyone, my name's Tim Davis and I'm a product manager on TensorFlow. And I'm presenting today with TJ, a TensorFlow Lite engineer who will be speaking in a bit. I'm super excited to be here today to talk about all the improvements we've made over the last few months for TensorFlow Lite. So first of all, what is TensorFlow Lite? Hopefully many of you know this by now, but we love to re-emphasize it and also provide context for users who are new to TensorFlow Lite. So TensorFlow Lite is our production-ready framework for deploying ML models on mobile devices and embedded systems. TensorFlow Lite can be deployed on Android, iOS, Linux, and other platforms used in edge computing. Now let's talk about the need for TensorFlow Lite and why we built an on-device ML solution. We are in the midst of a huge demand for doing ML on the edge. It's driven by the need for user experiences that require low latency, that work in situations with poor network connectivity, and enable privacy-preserving features. All of these are the reasons why we built TF Lite back in 2017. And just look at our journey since then. As the world's leading ML mobile framework, we have made a ton of improvements across the board. Recently, we've increased the ops we support, delivered numerous performance improvements, developed tools which allow you to optimize models with techniques like quantization, increased language support for our APIs, and there'll be more on that in a bit, and we're supporting more platforms like GPUs and DSPs. Now, you're probably wondering, how many devices are we on now? Boom. TensorFlow Lite is now on more than 4 billion devices around the world across many different apps. Many of Google's own largest apps are using it, as are a large number of apps from external companies. This is a sampling of just some of the apps that use TensorFlow Lite: Google Photos, Gboard, YouTube in the Assistant, along with really popular third-party apps like Uber, Hike, and many more. So what is TensorFlow Lite being used for, you might ask? Developers are using TF Lite for use cases around image, text, and speech, but we are seeing a lot of new and emerging use cases around audio and content generation. For the rest of the talk, we're going to focus on some of the latest updates and highlights. First up, let's talk about how we're helping developers get started quickly and easily with TensorFlow Lite. At TF World, we announced the TF Lite support library, and today we are announcing a series of extensions to that. First, we are adding more APIs, such as our image API, and introducing new simplistic language APIs, all enabling developers to simplify their development. We are also adding Android Studio integration, which will be available in Canary in a couple of weeks, that will enable simple drag and drop into Android Studio, and then automatically generate Java classes for the TF Lite model with just a few clicks. This is powered by our new CodeGen capability. CodeGen makes it easy for TensorFlow Lite developers to use a TF Lite model by handling the various details around inputs and the outputs of the model, and saves you a heap of time. Here's a small example to show you what I mean. With the additions to the support library, you can now load a model, set an input on it, and then run the model, then easily get access to the resulting classifications. The CodeGen tool reads the model metadata and automatically generates the Java wrapper with the model-specific API and code snippet for you. This makes it easy to consume and develop with TF Lite models without any ML expertise. And this is a sneak peek of how this will look in Android Studio. Here you can see all of the model metadata from the drag and dropped TF Lite model. This will then CodeGen Java classes just for image models to begin, but later for many different types of TensorFlow Lite models. How cool is that? We're then committed to making mobile ML super, super easy. Check out this in the next couple of weeks on the Android Studio Canary channel. In addition to CodeGen, all of this is made possible through the new extended model metadata. Model authors can provide a metadata spec when creating and converting models, making it easier for users of the model to understand how it works and then how to use it in production. Let's take a look at an example. The metadata descriptor provides additional information about what the model does, the expected format of the model inputs, and the meaning of the model outputs. All of this is encoded via a simple protobuf, and our new release has tools to help you generate the right metadata for your model. We have made our pre-trained model repository much richer and added many more models. All of this is available via TensorFlow Hub. We've got new mobile-friendly flavors of BERT, including Mobile BERT and LBERT for on-device NLP applications, in addition to EfficientNet Lite. Again, all of these are hosted on our central model repository, TensorFlow Hub, so check out TF Hub for all the details. Now let's talk about transfer learning. Having a repository of ready-to-use models is great for getting started and trying them out. But developers regularly want to customize these models with their own data. That's why we're releasing a set of APIs which makes it easy to customize these models using transfer learning. And we're calling this TF-Lite Model Maker. It's just 4 lines of code. You start by specifying your dataset, then choose which model spec you would like to use, and boom, it just works. You can see some stats of how the model performs, and lastly, export it to a TF-Lite model. We've got text and image classification already supported, and new use cases like object detection and QA are coming soon. Now, we've got an exciting development in graph delegation. There are multiple ways to delegate your model in TF-Lite through GPU, DSP, or through the NN API in Android P and up. Recently, we've added increased GPU performance and DSP delegation through Hexagon. And we've increased the number of supported ops through the Android NN API. But you already knew all that. So what's new? Well, we have a really big announcement that I'm incredibly excited to share today. I'm excited to announce the great news that as of today, we are launching a CoreML delegate for Apple devices to accelerate floating point models in the latest iPhones and iPads using TensorFlow Lite. The delegate will run on iOS 11 and later, but to get benefits over using TF-Lite directly, you'll want to use this delegate on devices with the Apple Neural Engine. The Neural Engine is dedicated hardware for accelerating machine learning computations on Apple's processors. And it's available on devices with the A12 SoC or later, such as the iPhone XS with iOS 12 or above. With the Neural Engine acceleration, you can get between 4 to 14 times speed up compared to CPU execution. So that's our update on delegates. We've heard from developers about the need for more and better tutorials and examples, so we're releasing several full example apps which show not only how to use a model, but the full end-to-end code that a developer would need to write to work with TF-Lite. They work on multiple platforms: Android, iOS, Raspberry Pi, and even the Edge TPU. Now I'd like to hand over to TJ, who's going to run through some more exciting improvements to TF-Lite and dive into the engineering roadmap more.
Awesome. Thanks, Tim. Hi, everyone. I'm TJ, and I'm an engineer on the TensorFlow Lite team. So let's talk about performance. A key goal of TensorFlow Lite is to make your models run as fast as possible on CPUs, GPUs, DSPs, or other accelerators. And we've made serious investment on all these fronts. Recently, we've seen significant CPU improvements, added OpenCL support for faster GPU acceleration, and have full support for all Android Q and NN API ops and features. Our previously announced Qualcomm DSP delegate targeting low and mid-end devices will be available for use in the coming weeks. We've also made some improvements in our benchmarking tooling to better assist model and app developers in identifying optimal deployment configurations. We've even got a few new CPU performance improvements since we last updated you at TensorFlow World. More on that in a bit. To highlight these improvements, let's take a look at our performance about a year ago at Google I/O. For this example, we're using MobileNet v1. And compare that with our performance today. This is a huge reduction in latency and can be expected across a wide range of models and devices from low-end to high-end. Just pull the latest version of TensorFlow Lite into your app, and you'll benefit from these improvements without any additional changes. Digging a bit more into these numbers, floating point CPU execution is the default path, providing a great baseline. Enabling quantization, now made easier with our post-training quantization tooling, provides a nearly 3x faster inference. Enabling GPU execution provides an even more dramatic speedup, about 7x faster than our CPU baseline. And for absolute peak performance, we have the Pixel 4's Neural Core, accessible via the NN API TensorFlow Lite delegate. This kind of specialized accelerator, available in more and more of the latest phones, unlocks capabilities and use cases previously unseen on mobile devices. And we haven't stopped there. Here's a quick preview of some additional CPU optimizations coming soon. In TensorFlow Lite 2.3, we're packing in even more performance improvements. Our model optimization toolkit has allowed you to produce smaller quantized models for some time. We've recently optimized the performance of these models for our dynamic range quantization strategy. So check out our model optimization video coming up later to learn more about quantizing your TensorFlow Lite models. On the floating point side, we have a new integration with the XNNPACK library, available through the delegate mechanism, but still running on CPU. If you're adventurous, you can make use of either of these new features by building from source, but we're shipping them in version 2.3 coming soon. Last thing on the performance side, profiling. TensorFlow Lite now integrates with Perfetto, the new standard profiler in Android 10. You can look at overall TF Lite inference, as well as op-level events on the CPU or GPU delegation. Perfetto also supports profiling of heap allocation for tracking memory issues. So that's performance. OK, now let's talk model conversion. Seamless and more robust model conversion has been a major focus for the team. So here's an update on our completely new TensorFlow Lite conversion pipeline. This new converter was built from the ground up to provide more intuitive error messages when conversion fails, support control flow operations, and it's why we're able to deploy new NLP models like BERT or Deep Speech V2, or image segmentation models like Mask-R CNN and more. The new converter is now available in beta and will be available more generally soon as the default option. We want to make it easy for any app developer to use TensorFlow Lite. To that end, we've released a number of new first-class language bindings, including Swift, Objective-C, C# for Unity, and more. Thanks to community efforts, we've seen the creation of additional TensorFlow Lite language bindings in Rust, Go, and Dart. This is in addition to our existing C++, Java, and Python bindings. Our model optimization toolkit remains the one-stop shop for compressing and optimizing your models, and it's now easier than ever to use with post-training quantization. So check out the optimization talk coming up later for more details. Finally, I want to talk a bit about our efforts in enabling ML, not just for billions of phones, but also for the hundreds of billions of embedded devices and microcontrollers used in production globally. TensorFlow Lite for microcontrollers is that effort and uses the same model format, converter pipeline, and kernel library as TensorFlow Lite. So what are these microcontrollers? These are small, low-power, all-in-one computers that power everyday devices all around us, like microwaves, smoke detectors, toys, and sensors. And with TensorFlow, it's now possible to use them for machine learning. You might not realize that embedded ML is already in use in devices you use every day. For example, hot word detection, like OK Google, on many smartphones typically runs on a small DSP, which then wakes up the rest of the phone. You can now use TensorFlow Lite to run models on these devices with the same tooling and frameworks. We're partnering with a number of industry leaders in this area. In particular, ARM, an industry leader in the embedded market, has adopted TensorFlow as the official solution for AI on ARM microcontrollers. And together, we've made optimizations that significantly improve performance on embedded ARM hardware. Another recent update, we've partnered with Arduino and just launched the official Arduino TensorFlow library. This makes it possible to start doing speech detection on Arduino hardware in about 5 minutes. You create your machine learning models using TensorFlow Lite and upload them to your board using the Arduino IDE. If you're curious about trying this out, this library is available for download today. So that's a look at where we are today. Going forward, we're continuing to expand the set of supported models, make further improvements to performance, as well as some more advanced features like on-device training and personalization. So please check out our roadmap on tensorflow.org and give us feedback. We'd love to hear from you. OK, that's it. Thanks, everyone, for listening. Next up is Nick to tell you about Project Jacquard.
Okay, we've just heard from the TensorFlow Lite team how it's getting even easier to place machine learning directly on devices. And I'm sure this got many of you thinking, what's possible here? Now I'm going to tell you about how we're using Jacquard to do exactly this. embed machine learning directly into everyday objects. Before I jump into the details, let me tell you a little bit about the Jacquard platform. So Jacquard is a machine learning-powered ambient computing platform that extends everyday objects with extraordinary powers. At the core of the Jacquard platform is the Jacquard tag. This is a tiny embedded computer that can be seamlessly integrated into everyday objects, like your favorite jacket, backpack, or pair of shoes. The tag features a small embedded ARM processor that allows us to run ML models directly on the tag, with only sparse gesture or motion predictions being emitted via BLE to your phone when detected. What's interesting is that the tag has a modular design, where the ML models can either run directly on the tag as a standalone unit, or via additional low-power compute modules that can be attached along with other sensors, custom LEDs, or haptic motors. A great example of this is the Levi's trucker jacket that I'm wearing. Let me show you how this works. So if we can switch over to the overhead camera. So here I can take the Jacquard tag and add it to a specifically designed sensor module, which is integrated into the jacket. Let me check that again. What happens now is that this talks to an M0 processor that's running on the jacket itself, which is talking to some integrated sensor lines in the jacket. The M0 processor not only reads data from the sensor lines, but it also allows us to run ML directly on the tag. This allows us to do gestures, for example, on the jacket to control some music. So for example, I can do a double tap gesture, and this can start to play some music. Or I can use a cover gesture to silence it. Users can also use swipe in and swipe out gestures to control their music, drop pins and maps, or whatever they'd like, depending on the abilities in the app. What's important here is that all of the gesture recognition is actually running on the M0 processor. This means that we can run these models at super low power, sending only the events to the user's phone via the Jacquard app. So I'm sure many of you are wondering how we're actually getting our ML models to be deployed, in this case, in a jacket. And by the way, this is a real product that you can go to your Levi's store and buy today. So as most of you know, there are 3 big on-device ML challenges that need to be addressed to enable platforms like Jacquard. So first is, how can we train high-quality ML models that can fit on memory-constrained devices? Second, let's assume we've solved problem 1 and have a TensorFlow model that's small enough to fit within our memory constraints. How can we actually get it running on low compute embedded devices for real-time inference? And third, even if we've solved problems 1 and 2, it's not going to be a great user experience if the user has to keep charging their jackets or backpacks every few hours. So how can we ensure the ML model's always ready to respond to a user's actions when needed, while still providing multi-day experiences on a single charge? Specifically for Jacquard, these challenges have mapped to deploying models as small as 20 kilobytes in the case of the Levi's jacket, or running ML models on low compute microprocessors like a Cortex M0 Plus, which is what's embedded here in the cuff of the jacket. To show you how we've addressed these challenges for Jacquard, I'm going to walk you through a specific case study for one of our most recent products. So recent, in fact, that it actually launched yesterday. First, I'll describe the product at a high level, and then we can review how we've trained and deployed ML models that, in this case, fit in your shoe. So the latest Jacquard-enabled product is called Gamer. This is an exciting new product that's being built in collaboration between Google, Adidas, and the EA Sports FIFA Mobile team. With Gamer, you can insert the same tag that's inserted in your jacket into an Adidas insole and go out in the world and play soccer. So you can see here where the tag inserts at the back. The ML models in the tag will be able to detect your kicks, your motion, your sprints, how far you've ran, your top speed. We can even estimate the speed of the ball as you kick it. Then, after you play, the stream of predicted soccer events will be synced with your virtual team in the EA FIFA mobile game, where you'll be rewarded with points by completing various weekly challenges. This is all powered by our ML algorithms that run directly in your shoe as you play. So Gamer is a great example of where running ML inference on device really pays off, as players will typically leave their phone in the locker room and go out and play for up to 90 minutes with just the tag in their shoes. Here you really need to have the ML models run directly on device and be smart enough to know when to turn off when the user is clearly not playing soccer to help save power. So this figure gives you an idea of just how interesting a machine learning problem this is. Unlike, say, normal running, where you would expect to see a nice, smooth, periodic signal over time, soccer motions are a lot more dynamic. For example, in just 8 seconds of data here, you can see that the player moves from a stationary position on the left, starts to run, breaks into a sprint, kicks the ball, and then slows down again to a jog, all within an 8-second window. For a gamer, we needed our ML models to be responsive enough to capture these complex motions and work across a diverse range of players. Furthermore, this all needs to fit within the constraints of the Jacquard tag. For a gamer, we have the following on-device memory constraints. We have around 80 kilobytes of ROM, which needs to be used not just for the model weights, but also the required ops, the model graphs, and of course the supporting code required for plumbing everything together so this can be plugged into the Jacquard OS. We also have around 16 kilobytes of RAM, which is needed to buffer the raw IMU sensor data and also be used as scratch buffers for the actual ML inference in real time. So how do we train models that can detect kicks, a player's speed and distance, and even estimate the ball speed within these constraints? Well, the first step is we don't. Well, at least initially. We train much larger models in the cloud to see just how far we can push the model's performance. In fact, this is using TFX, which is one of the systems that was shown earlier today. This helps inform the design of the problem space and guide what additional data needs to be collected to boost the model's quality. After we start to achieve good model performance without the constraints on the cloud, we then use these learnings to design much smaller models that start to approach the constraints of the firmware. This is also when we start to think about not just how the models can fit within the low compute and low memory constraints, but how they can run at low power to support multi-day use cases. For a gamer, this led us to design an architecture that consists of not 1, but 4 neural networks that all work coherently. This design is based on the insight that even during an active soccer match, a player only kicks the ball during a small fraction of gameplay. We therefore use much smaller models that are tuned for high recall to first predict if a potential kick or active motion is detected. If not, there's no need to trigger the larger, more precise models in the pipeline. So how do we actually get our multiple neural networks to actually run on the tag? To do this, we have built a custom C model exporter. For this, the model exporter is using a Python tool that calls a number of C ops from a lookup. This then generates custom C code with a lightweight ops library that can be shared across multiple graphs, and the actual .h and .c code that you get for each model. This allows us to have 0 dependency overheads for our models and make every byte count. Here, for example, you can see an example of one of the C ops that would be called by the library. So this is for a rank 3 transpose operation, which supports multiple I/O types, such as int8s or 32-bit floats. So with this, you can see how we're taking our neural networks and actually getting them to run on the Jacquard tag live. I hope that you're inspired by projects like Jacquard, and this makes you think about things that you could possibly do with tools like TF Lite Micro to actually build your own embedded ML applications. Next up is Na, who's going to be talking about TensorFlow JS.
Hi, my name is Nali, and I'm one of the engineers for TensorFlow JS team. TensorFlow JS is an open source AI platform for developing, training, and using ML models in browsers, or anywhere JavaScript can run. Today, I'm going to show you how TensorFlow JS powers some amazing web applications and its usage beyond the web. TensorFlow JS was started in 2017 and launched in 2018, along with the models repo and Node.js support. This graph shows the major development milestones of TensorFlow JS. In 2019, we launched 1.0. We added 4 more models, covering more use cases of ML, including body segmentation, toxicity detection, and sound recognition. We launched 2 exciting features, AutoML and Direct Save Model support. We'll show you how ML is made easy with these new features. Also in 2019, we started to see adoption by large users such as Uber and Airbnb. We've also seen increasing adoption by app developers of mini platforms such as WeChat and TikTok. In the last few months, we kept expanding the models repo to include some of the most popular models. Today, we're going to showcase them to you. We also kept expanding our platform functionalities. We launched a 4th backend, Wasm, around Christmas. We also made TFJS React Native package global available last month. In terms of user adoption, we collaborated with Glitch and CodePen, 2 largest online JS playgrounds, to further support JS developers to learn and use machine learning in their applications. In 2020, we will add more models, and we will keep investing in the TFJS platform to support more production and research use cases. This includes modularize the library, add TFX support, and integrate with more products in the TF ecosystem. We will release 2.0 later this year, so please stay tuned. ML is made easy with TensorFlow JS. We provide multiple starting points for your needs. You can directly use pre-trained models. You can retrain an existing model in the browser, or you can build your model from scratch with a Keras-like Layers API. We try to make running existing models really easy for everyone. We provide a collection of models suitable for directly use with inputs widely accessible in web applications such as image, video, audio, and texts. If you already have a trained model somewhere, we provide a converter for you to convert the model to TFJS format. And we just launched the Converter Wizard, an interactive command line tool to help you figure out the correct parameters. If you have a saved model and your model will run in Node.js, then you can directly run it without the conversion, so no missing ops headache anymore. Now, let's take a look at some of the new applications and models we and our users built this year. First, we introduced the face mesh model. This model is able to recognize 600 facial points. Its size is under 3 megabytes. We've seen good performance on high-end phones and desktops. It performs inference at 35 FPS on an iPhone 11. Next, we introduced the hand pose model. This model has a weight size of 12 megabytes. It also shows good performance on modern phones and desktops. It's worth mentioning that applications that will be enabled by face mesh and hand pose are only possible when running on device, because as you can see here, the experience needs to be in real time, and TFJS enables this. Next, let's look at a language model, Mobile BERT. The model is 100 megabytes. It's pretty large for the web. The inference speed is 100 milliseconds. We made a Chrome extension for Smart Q&A. Users can ask any question on the web page, and the most relevant answers will be highlighted. We demonstrate it's possible to run large model in browsers. This model can also be used in conversational interfaces, such as chatbot. Thus far, we have open source 11 models. Using these models as building blocks, you can build a lot of applications for use cases such as accessibility, VR experiences such as virtual try-on, toxicity detection, and conversational agents, etc. Next, we show some applications that our users built. We're seeing a vibrant developer community building many interesting applications and APIs on top of TensorFlow.js. There has been 1.4 million NPM downloads and more than 6,000 dependent GitHub repos so far. Besides individual efforts, companies also use TensorFlow.js in their products. Modiface is an augmented reality technology company based in Canada. They have used TensorFlow.js to build virtual try-on applications for several beauty brands. Using TensorFlow.js, they were able to provide a smooth UI at 25 FPS on phones. They can mitigate users' privacy concerns by restricting user data to stay on device. They were also able to deploy their products across multiple platforms, including browsers and WeChat mini program platform. It won't be possible to support ML models to run on devices of all kinds of capabilities without the various backends TensorFlow.js provides. I will talk about the characteristic of each backend and their performance. We currently have 4 backends, which includes a CPU backend that is always available for all devices, a WebGL backend that is the fastest backend by running models on GPU, a Node backend that runs models on desktops, servers, and IoT devices. This year, we added a 4th backend, Wasm, which allows C++ code to run in browser. We also invest heavily in future technology. A web GPU backend will be coming soon. We expect to have even better performance than WebGL. A natural question is, how fast are they? We compare the performance of 3 backends in browsers on 2 models. Here you can see how fast Wasm is. On both models, Wasm is 10 times faster than plain.js across all devices, especially on small models like this face detector model on the right, which is 100 kilobytes. Wasm's performance is comparable to and sometimes even faster than WebGL. This is because our WebGL backend has a fixed overhead. Simply running an empty GLSL shader costs 0.1 to 0.2 milliseconds. This is great because we've seen a trend of ultralight models being made for running on edge devices. The Wasm backends provides a nice addition to the WebGL backend with really great performance. Especially, Wasm is more accessible in lower-end devices. Wasm is available on about 90% device. As a comparison, WebGL is only available on 53% devices. On medium to larger models, such as the one on the left, which is a MobileNet model, 3.5 megabytes, WebGL is still the fastest. The inference time can be as small as 20 milliseconds, which is 50 FPS, really good for real-time applications, whereas Wasm is about 100 to 200 milliseconds. But we're looking to further improve Wasm. With technology like SIMD, it will be 2 to 3 times faster. For node performance, people often think they need to use the Python-based TensorFlow for server-side solution because it's fast. Actually, as we will show you here, our Node.js backend provides the same performance as the Python-based version. Again, we benchmark the MobileNet model, which is shown on the left in orange bars. The Node backend has similar performance as the Python-based TensorFlow, about 20 milliseconds on CPU and about 8 milliseconds on GPU. On the right is a Q&A model with DistillBERT, developed by Hugging Face. Hugging Face is a leading research team specialized in NLP research. This graph shows their benchmark result in a local environment. The top bar is running the model on Node backend. The bottom bar is running the model using the Python API. Underneath, both are calling TensorFlow C++ code. We can see the inference time is comparable, and in some cases, Node is faster. With the 4 backends, we are able to support a variety of platforms, including all major browsers, servers, mobile devices, desktops, and IoT devices. It's also worth mentioning that our latest backend, Wasm, is available to run on all the platforms. except we still recommend to run Node backend for Node.js. We also try to make retrain existing models really easy for everyone. First of all, TFJS supports transfer learning in the browser. Now, we added AutoML for vision. It's a cloud service that allows you to train a custom model without writing any code. Never easier than before. Last, we'd like you to help us make TFJS better. We launched a campaign for people to discover community creations and join the discussion of ML for the web and beyond. Please use hashtag MadeWithTFJS on any social networks when you post your TFJS relevant stories. Thank you. Next up is Q&A.
And we're back. Hi, I'm Robert. I'm with the TensorFlow team, and I'm joined today by Sandeep and Minsheng. And we have some of your questions from the live feed, so let's get to that. First question from Morten Dalhau. I hope I got your name right. Will the new TFRT support distributed training? Minsheng, that's you.
Thank you, Morten, for the question. Yes, distributed training is very important. We are pushing on the design and implementation in parallel to supporting training that we covered in today's talk. Distributed training has its own set of challenges compared to just supporting serving. For example, we need to figure out how the hosts should talk to each other. And sometimes they should go through the normal data center network. You might be familiar with gRPC as one possible protocol. And sometimes they go through accelerator networks, such as using GPU technology, and Google also has TPU technology. So there are lots of interesting challenges that we're working through, and we would love to keep the community posted of our progress.
Great, thanks for that. Next question up, I don't have a name for, but the question is TFX 2.0 compatible? And I can take that one. Yes, TFX is 2.0 compatible. We just announced native Keras support for TFX. So you can have an entire TFX Keras pipeline that supports 2.0. There is one feature of Keras, feature layers that we don't yet support. But other than that, yeah, it's 2.0 compatible. And next question. This is from Andrei Moskalenko. Why is it impossible to use time-distributed wrapper over a Keras model? For example, if I have a one-frame model and want to extract features along the time axis in video. Sandeep?
Yeah, so thank you so much for the question. So the short answer is that yes, this is indeed possible to do. What you want to do is you want to use the Keras functional API. So when you use the functional API, you can pretty much use any trained model as a layer in sort of other model code. So in this case, you would wrap it with the time distributed class, and then you can basically use an image model as part of a video sequence. If you go to keras.io website and you look at the functional API guide on the Getting Started section, you will see a section there which talks about how to use pre-trained models or previously trained models as callable layers, and that shows specifically this example. So hopefully it will give you everything you need to get started.
Great, thanks for that. That was a tough question. Next one is from Tagir Akhmetchin. I hope I got your name right. Is there any way to monitor on which device, CPU or GPU, my tensors are stored? Minsheng, you want to take that one?
Sure. Thank you for the question. So let me give you a short answer, and I think we would love to learn more about the use cases as well, so we can design something that is well thought out. I think overall this seems like a very reasonable request. And from the runtime infrastructure perspective, we will be able to track where the tensors or variables live.
There's also the part of the API question, how we expose this, how user could use this. And I think that's beyond the scope of the runtime. But overall, I would love to continue to have the dialogue and learn more about what are the use cases and how we should design the feature properly.
Great, thanks. All right, next question from Subem Hua. Any tutorial pages for TFX pipelines? I can take that one too. Yes, there's a bunch of new tutorials actually available, including a nice tutorial for Cloud AI Platform Pipelines, which includes TFX. But check out our tutorial pages on tensorflow.org, and I think you'll find some good stuff there. And that was our last question for today, so thanks very much. And next up, we have the next thing. We have a break. Okay, thanks very much.
Thank you. Thank you.
Airbnb is an online marketplace. We have over 5 million different homes in 81,000 cities, which equates to hundreds of millions of photos, making it possibly the largest collection of images of homes in the world today. When a guest decides to select a home, one of the biggest influences in their decision is a diverse set of images. But a lot of times hosts will take a lot of pictures of a single room and forget to take pictures of the other rooms.
They also have the option to add captions, but a lot of cases they're totally off.
We were faced with a challenge of identifying what's actually in these pictures and present them properly on the site. That's one area where machine learning excels. But the real challenge was one of scale. We had upwards of 500 million images to get through. It was going to take months to really go through all of these.
Using TensorFlow, we were able to speed up the process and deliver a reasonable model within days. BigHead is Airbnb's machine learning platform. We had the idea of making it very agnostic to different ML frameworks, and so we leveraged TensorFlow to train the model, and then BigHead helps with the model lifecycle, the feature management, and then TensorFlow serving to help serve the model results.
Before you think about which tool to use, you first think about which model to use, right? And we did research on this. We find that ResNet 50 was one of the state-of-the-art performing models. We used that as the basic architecture.
We used TensorFlow's Keras APIs and serving and some of the distributed GPU computations. This ultimately led to a pipeline that we can deploy to go through hundreds of millions of images very quickly.
So the end goal is basically using these classifications of images to make sure that their first initial set of photos that they see aren't just a picture of the garage and bathroom, but it could be of the living room that's gorgeous, and the bedroom and the swimming pool. Future applications could be to detect different objects in homes, and if users decide to search on the website for specific amenity types, we can actually bubble that up to the surface.
If you like how Airbnb operates today, the reason was because of machine learning, because machine learning is almost everywhere in the company. Search ranking, pricing, predicting booking.
We're passing into the hundreds of models, so it's something I expect to keep growing.
And with a lot of these new frameworks coming out, we can make better experiences for our guests and better business decisions as well.
Extreme weather is changing. There's more extreme rainfall, heavy flooding, forest fires.
There isn't really a signature done.
Being able to predict these extreme events more accurately is kind of the big challenge that we're facing right now. There's 100 terabytes of climate data every day from satellites, from observations, from models. So climate data is a big data problem. We need things that are fast, that can sift through all of that data rapidly and accurately. And deep learning is almost perfectly poised for problems in climate science.
A lot of NERSC users are using TensorFlow. It's one of the more popular frameworks. We use TensorFlow to iterate quickly over different models, different layer parameters. For this particular climate project, to create the deep learning model, we started from segmentation models which have proven to be successful, for example, our satellite imagery segmentation tasks. And then we used TensorFlow to enhance the models until we found like a set of models which perform well enough for this specific task. But for the volume of the data, complexity of the data, the network required 14 teraflops. So if you want to do this on your workstation, it would take like months to train.
To really tackle these problems requires the largest computational resources that are available on the planet. So systems like the Summit supercomputer. It's 2 tennis courts in total size. I mean, this thing is state-of-the-art. It's 1 million times faster than your common laptop, 3.3 exaflops. Just imagine what you do at your workstation, but now imagine having 27,000 times that power. We can do that now.
We were surprised how good it actually scales. 1,000 nodes and 2,000 nodes, 5,000 nodes.
This was the first time anybody's ever run an AI application at this scale. Instead of having the climate scientists figure out how to write high-tune code, they could express things in a very natural way in Python in TensorFlow and get all the high-performance code that most HPC people are used to within TensorFlow.
We're now entering the space where AI can actually contribute to the predictions of these extreme weather events.
When you combine traditional HPC with AI, you can tackle things we never thought that we could tackle. Fusion reactor research, understanding diseases like Alzheimer's, cancer, right? That's incredible.
We've shown that with a high productivity framework such as TensorFlow, you can get to massive scale and you can get awesome performance and accomplish your goals.
Genetics, neuroscience, cosmology, high energy physics. That's immensely exciting for me.
Sound analysis is used in so many fields, such as identification of music,
and the identification of the type of animal based on the sounds that they produce. Sound is critical to what we're doing because physiological sounds are very important in medicine, but the traditional stethoscope hasn't changed for close to 200 years. The doctor is limited by the human ear, and they cannot hear specific frequencies. This method is very inaccurate and causes a lot of misdiagnosis. Our mission is to use machine learning and TensorFlow to revolutionize the diagnosis and treatment of respiratory diseases in low-resource areas such as sub-Saharan Africa. The Tambua app is a powerful screening tool that helps doctors make decisions quickly. The core technology is trying to mimic the human auditory system. Once the patient walks in, the doctor collects the lung sounds with symptoms, risk factors, and vitals of the patient, and then the Tambua app combines all that information and gives the doctor a probability of the patient having a specific respiratory disease.
Kuna any abnormal breath sounds?
Eric introduced TensorFlow to us because he felt that we can use TensorFlow to go through all the stages of development to deployment of our model.
Our model uses spectrograms. We take sound data from the digital stethoscope and convert it into a visual problem that the computer can best identify. We have worked with a number of clinics and pathologists, and we are able to collect data from 621 patients, and then we use that data now to build our machine learning model.
Once we had trained and evaluated our machine learning model, we deployed it on our Tambua app. TensorFlow Lite helps us to perform an inference on a mobile device without the need of a connection. So doctors can use the Tambua app offline without connecting to the cloud. There are 216 healthcare facilities that are using the Tambua app and the Tambua devices. These clinics are spread out, and some are very rural clinics.
It's really a nice project. I can elicit a crack call plus the vital sounds. Then when I add the clinical history and the other physical examination, there's no need for me to take this patient for an X-ray. Misdiagnosis, which is one of the problems leading to deaths in Kenya, is really creating a menace. Tambua is helping me. It shows me even the things that I would have missed in case I had the traditional way of doing it.
Over 2.5 million people die each year because of pneumonia, asthma, COPD, and pulmonary tuberculosis. I believe that we can use machine learning in treatment and management of these respiratory diseases.
Consultare documenti storici, soprattutto documenti medievali, richiede sempre molto tempo, molta pazienza. In Archivio Vaticano abbiamo 85 km lineari di documenti, più o meno la lunghezza del Canale di Panama. Le scritture scritte nel Medioevo sono diverse da quelle che noi conosciamo. Se qualcuno mi chiedesse un giorno di trascrivere e tradurre tutti i documenti dell'Archivio Vaticano, sicuramente gli direi che è un matto.
Looking at this book, page by page, and trying to decipher, read and transcribe whatever is there takes an enormous amount of time. You would require an army of paleographers.
What I'm excited the most about machine learning is that it enabled us to solve problems that up to 10-15 years ago we thought unsolvable.
In Codice Razio è nato da quest'idea di costruire un software per poter interpretare, per poter leggere quello che è scritto dentro i manoscritti. Quando abbiamo iniziato ad approcciare il problema ci siamo resi conto che una soluzione basata su reti neurali fosse assolutamente necessaria. La scelta su TensorFlow è stata abbastanza naturale.
Before using any kind of machine learning model, we needed to collect data first. You have thousands of images of dogs and cats in the internet, but there is very little images of ancient manuscripts. We built our own custom web application for crowdsourcing, and we involved high school students to collect the data. I didn't know much about machine learning in general, but I found it very easy to create a TensorFlow environment. When we were trying to figure out which model worked best for us, Keras was the best solution. The production model runs on TensorFlow layers and estimator interface. We experimented with binary classification with fully connected networks, and finally we moved to convolutional neural network and multi-class classification.
In poco tempo siamo riusciti a sviluppare e a testare le prime soluzioni.
When it comes to recognizing single characters, we can get 95% average accuracy.
Poter accedere a uno strumento informatico abbrevia notevolmente. Sciogliere certe abbreviazioni, comprendere un testo in quella scrittura così criptica è un qualcosa di eccezionale.
This will have an enormous impact. In a short period of time, we will have a massive quantity of historical information available.
I just think solving problems is fun. It's a game against myself and how good I can do.
Lo studio della storia è importantissimo per comprendere il nostro presente e per avere anche una prospettiva per il futuro.
Hello, everybody. My name is Joana Carrasqueira, and I'm a program manager for TensorFlow. Today, I'm very excited to bring you the greatest and the latest about our community. As you can see, our community is growing every day. And here is a snapshot of the commits to TensorFlow since we open sourced the technology in 2015. Since then, our project has received 142,000 stars. How impressive. And we couldn't have gotten this far without you, the community. I'm truly impressed by all our contributions and hard work. So thank you so much for all your efforts. Now, let's have a more in-depth look at the different groups that form our community. Our vibrant community includes code and non-code contributors, community managers, and students. But also, we onboarded 148 machine learning Google Developer Experts who are a part of the Google Developer Expert Network. We also established 73 TensorFlow user groups worldwide. We formed 11 special interest groups and welcomed 1,375 developers at the Developers at TensorFlow mailing list. And just last year, we welcomed 20 students at the Summer of Code. Furthermore, our documentation has been translated to 12 languages, and on GitHub, we have nearly 2,500 contributors and nearly 9,000 commits. How impressive, again. What a fantastic work. Altogether, we've built an open source project that we can be very proud of. I'm going to give you an overview on how you can get involved in the TensorFlow community. Firstly, the TensorFlow user groups. They aim to upscale contributions to TensorFlow with a local focus. Some examples of the initiatives conducted by these groups, they include events, meetups, and doc sprints. The machine learning GDEs, they are experts and practitioners from the community who support with outreach initiatives. And finally, the special interest groups, the SIGs. They are focus groups contributing TensorFlow to certain parts and more specific projects. Right now, we have 73 TensorFlow user groups distributed all across the world. And so far, these groups have reached more than 100,000 developers worldwide. In your country, if you don't have a TensorFlow user group yet, please feel free to reach out to us. We can help you with the resources and share best practices from other parts of the world. These events are a great way to engage with other developers and with the community. We also strongly encourage students to engage in these initiatives and learn with more experienced developers. After the TensorFlow Roadshow in São Paulo last October, we also established the first 2 TensorFlow user groups in LATAM, in São Paulo, in Brazil, and Argentina. We are extremely happy to welcome these developers to the TensorFlow community. Also, in collaboration with our machine learning ecosystem teams, we enable contributions from the local communities. And I'm very excited to announce that this year, we are going to do a series of TensorFlow bootcamps and doc sprints in Latin America. Our goal is to really get closer to you, to the machine learning and the TensorFlow communities. So we look forward to stay connected with the communities in Colombia, Argentina, Chile, and Mexico. Documentation is also the backbone of an open source project. And so far, we have 268 tutorials and notebooks translated across 12 different languages. Additionally, we have over 40 translation pull requests that are still awaiting review. We really want to provide a good experience to our contributors. And in order to achieve this goal, we'll continue to support translations of our documentation into several different languages. Just last year, the machine learning GDEs, they gave more than 100,000 talks, and they published 295 articles that reached out more than 500,000 developers. Our machine learning GDEs, they play a critical role in advancing machine learning education worldwide. And if you'd like to be a part of this brilliant group, please get in touch with us. Just to highlight a few events where our machine learning GDs spoke at last year, we have a few pictures, as you can see here, and they refer to the African Build-Up event, the Explore Machine Learning India Day, and the Doc Sprints in Korea. For bigger projects in which we have to work as a team, we created the TensorFlow Special Interest Groups. This is a program that organizes contributors into focus stream areas of work. These groups, they take ownership of specific areas to add and maintain new features to TensorFlow. It all started with a SIG build, and right now we have 11 different SIGs. The contributors are welcome to join the SIGs based on the parts of TensorFlow that they care the most. As I mentioned before, our ecosystem includes the SIG, add-ons, build, I/O, networking, GVM, and Rust, and Micro, who are community-led open source projects, whereas Keras, MLAR, Swift, and TensorBoard are Google-led with an open source philosophy. Each individual SIG meets on a monthly basis, and if you want to be part of a SIG, you can head to GitHub for more information on how to join. You can also request a new SIG, and we are here to help you and guide you through the process. There are many ways that you can contribute to a SIG, and these are just a few examples of specific projects that are looking for contributors in 2020. A great way to get feedback on a large project is through the request for comments, or RFC process. It is the primary way we communicate our design rationale and receive feedback from the community. Anyone can create or comment on an RFC. We have started tweeting our RFCs, so please keep an eye at the TensorFlow Twitter account. We manage our RFC process on GitHub, and there you can comment on an open RFC or propose a new RFC. If you want to propose a design, we strongly encourage you to socialize your idea, recruit a sponsor, write your RFC, respond to feedback, and implement it. And if you are interested in learning more about TensorFlow, you may want to consider doing one of our fantastic online courses, either on Coursera or Udacity. We are proud to also announce that our university program includes new courses about TensorFlow at MIT, Imperial College, and University of Hong Kong, just to mention a few. And lastly, as announced this morning, we are launching the TensorFlow Certificate Program. It is intended for individuals who want to advance their deep learning proficiency and want to demonstrate experience in building practical business applications using TensorFlow. Head to tensorflow.org/certificate for more information. And then, lastly, please follow us on social media for the latest news and content about TensorFlow and the community. On Twitter, you can get the latest news about TensorFlow, head to the blog for more technical use cases and best practices, and then our YouTube channel has more educational resources that will help you through your journey. Get in touch and get involved with the community. Thank you so much. Up next, we have Catherine and Miguel to talk about responsible AI.
Hi, I'm Kat from the TensorFlow team, and I'm here to talk to you about responsible AI with TensorFlow. I'll focus on fairness for the first half of the presentation, and then my colleague Miguel will end with privacy considerations. Today, I'm here to talk about three things. The first, an overview of ML fairness. Why is it important? Why should we care? And how does it affect an ML system exactly? Next, we'll walk through what I'll call, throughout the presentation, a fairness workflow. Surprisingly, this isn't too different from what you're already familiar with. for example, a debugging or a model evaluation workflow. We'll see how fairness considerations can fit into each of the discrete steps. Finally, we'll introduce tools in the TensorFlow ecosystem, such as fairness indicators, that can be used in the fairness workflow. Fairness indicators is a suite of tools that enables easy evaluation of commonly used fairness metrics for classifiers. Fairness indicators also integrates well with remediation libraries in order to mitigate bias found, and is structured to help in your deployment decision with features such as model comparison. We must acknowledge that humans are at the center of technology design, in addition to being impacted by it. And humans have not always made product design decisions that are in line with the needs of everyone. Here's one example. QuickDraw was developed through the Google AI Experiments program, where people drew little pictures of shoes to train a model to recognize them. Most people drew shoes that look like the one on the top right. So as more people interacted with the game, the model stopped being able to recognize shoes like the shoe on the bottom. This is a social issue first, which is then amplified by fundamental properties of ML, aggregation, and using existing patterns to make decisions. Minor repercussions in a faulty shoe classification product, perhaps, but let's look at another example that can have more serious consequences. Perspective API was released in 2017 to protect voices in online conversations by detecting and scoring toxic speech. After its initial release, users experimenting with the web interface found something interesting. The user tested two clearly non-toxic sentences that were essentially the same, but with the identity term changed from straight to gay. Only the sentence using gay was perceived by the system as likely to be toxic, with a classification score of 0.86. This behavior not only constitutes a representational harm. When used in practice, such as a content moderation system, this can lead to the systematic silencing of voices from certain groups. How did this happen? For most of you using TensorFlow, a typical machine learning workflow will look something like this. Human bias can enter into the system at any point in the ML pipeline, from data collection and handling to model training to deployment. In both of the cases mentioned above, bias primarily resulted from a lack of diverse training data. In the first case, diverse shoe forms, and in the second case, examples of comments containing gay that were not toxic. However, the causes and effects of bias are rarely isolated. It is important to evaluate for bias at each step. You define the problem the machine learning system will solve. You collect your data and prepare it, oftentimes checking, analyzing, and validate it. You build your model and train it off the data you just prepared. And if you're applying ML to a real-world use case, you'll deploy it. And finally, you'll iterate and improve your model, as we'll see throughout the next few slides. The first question is, how can we do this? The answer, as I mentioned before, isn't that different from a general model quality workflow. The next few slides will highlight the touch points where fairness considerations are especially important. Let's dive in. How do you define success in your model? Consider what your metrics and fairness-specific metrics are actually measuring and how they relate to areas of product risk and failure. Similarly, the data sets you choose to evaluate on should be carefully selected and representative of the target population of your model or product in order for the metrics to be meaningful. Even if your model is performing well at this stage, it's important to recognize that your work isn't done. Good overall performance may obstruct poor performance on certain groups of data. Going back to an earlier example, accuracy of classification for all shoes was high, but accuracy for women's shoes was unacceptably low. To address this, we'll go one level deeper. By slicing your data and evaluating performance for each slice, you will be able to get a better sense of whether your model is performing equitably for a diverse set of user characteristics. Based on your product use case and audience, what groups are most at risk, and how might these groups be represented in your data in terms of both identity attributes and proxy attributes? Now, you've evaluated your model. Are there slices that are performing significantly worse than overall or worse than other slices? How do we get intuition as to why these mistakes are happening? As we discussed, there are many possible sources of bias in a model, from the underlying training data to the model, and even in the evaluation mechanism itself. Once the possible sources of bias have been identified, data and model remediation methods can be applied to mitigate the bias. Finally, we will make a deployment decision. How does this model compare to the current model? This is a highly iterative process. It's important to monitor changes as they are pushed to a production setting. or to iterate on evaluating and remediating models that aren't meeting the deployment threshold. This may seem complicated, but there are a suite of tools in the TensorFlow ecosystem that make it easier to regularly evaluate and remediate for fairness concerns. Fairness Indicators is a tool available via TFX, TensorBoard, Colab, and standalone model-agnostic evaluation that helps automate various steps of the workflow. This is an image of what the UI looks like, as well as a code snippet detailing how it can be included in the configuration. Fairness Indicators offers a suite of tools that allows a suite of commonly used fairness metrics, such as false positive rate and false negative rate, that come out of the box for developers to use for model evaluation. In order to ensure responsible and informed use, the toolkit comes with 6 case studies that show how fairness indicators can be applied across use cases and problem domains and stages of the workflow. By offering visuals by slice of data, as well as confidence intervals, fairness indicators help you figure out which slices are underperforming with significance. Most importantly, Fairness Indicators works well with other tools in the TensorFlow ecosystem, leveraging their unique capabilities to create an end-to-end experience. Fairness Indicators data points can easily be loaded into the what-if tool for a deeper analysis, allowing users to test counterfactual use cases and examine problematic data points in detail. This data can also be loaded into TensorFlow data validation to identify the effects of data distribution on model performance. This Dev Summit, we're launching new capabilities to expand the Fairness Indicators workflow with remediation, easier deployments, and more. We'll first focus on what we can do to improve once we've identified potential sources of bias in our model. As we've alluded to previously, technical approaches to remediation come in 2 different flavors: data-based and model-based. Data-based remediation involves collecting data, generating data, reweighting, and rebalancing in order to make sure your data set is more representative of the underlying distribution. However, it isn't always possible to get or to generate more data, and that's why we've investigated model-based approaches. One of these approaches is adversarial training, in which you penalize the extent to which a sensitive attribute can be predicted by the model, thus mitigating the notion that the sensitive attribute affects the outcome of the model. Another methodology is demographic agnostic remediation, an early research method in which the demographic attributes don't need to be specified in advance. And finally, constraint-based optimization, we will go into more detail in over the next few slides in a case study that we have released. Remediation, like evaluation, must be used with care. We aim to provide both the tools and the technical guidance to encourage teams to use this technology responsibly. Celeb A is a large-scale face attributes dataset with more than 200,000 celebrity images, each with 40 binary attribute annotations such as is smiling, age, and headwear. I want to take a moment to recognize that binary attributes do not accurately reflect the full diversity of real attributes and is highly contingent on the annotations and annotators. In this case, we are using the dataset to test a smile detection classifier and how it works for various age groups characterized as young and not young. I also recognize that this is not the possible full span of ages, but bear with me for this example. We trained an unconstrained, and you'll find out what unconstrained means, TF-Keras sequential model, and evaluated and visualized using fairness indicators. As you can see, not young has a significantly higher false positive rate. Well, what does this mean in practice? Imagine that you're at a birthday party and you're using this new smile detection camera that takes a photo whenever everyone in the photo frame is smiling. However, you notice that in every photo, your grandma isn't smiling because the camera falsely detected her smiles when they weren't actually there. This doesn't seem like a good product experience. Can we do something about this? TensorFlow constraint optimization is a technique released by the Glassbox research team here at Google. And here we incorporate it into our case study. TF constraint optimization works by first defining the subsets of interest. For example, here we look at the not young group represented by groups tensor less than 1. Next, we set the constraints on this group such that the false positive rate of this group is less than or equal to 5%. And then we define the optimizer and train. As you can see here, the constraint sequential model performs much better. We ensured that we picked a constraint where the overall rate is equalized for the unconstrained and constrained model, such that we know that we're actually improving the model as opposed to merely shifting the decision threshold. And this applies to accuracy as well, making sure that the accuracy and AUC has not gone down over time. But as you can see, the not young FPR has decreased by over 50%, which is a huge improvement. You can also see that the false positive rate for young has actually gone up. And that shows that there are often trade-offs in these decisions. If you want to find out more about this case study, please see the demos that we will post online to the TF site. Next, finally, we want to figure out how to compare our models across different decision thresholds so that we can help them in your deployment decision to make sure that you're launching the right model. Model comparison is a feature that we launched such that you can compare models side by side. In this example, which is the same example that we used before, we're comparing a CNN and SVM model for the same smile detection example. Model comparison allows us to see that CNN outperforms SVM, in this case, has a lower false positive rate across these different groups. And we can also do this comparison across multiple thresholds as well. You can also see the tabular data and see that CNN outperforms SVM at all of these thresholds. In addition to remediation and model comparison, we also launched Jupyter Notebook support, as well as a fairness lineage with ML metadata demo collab, which traces the root cause of fairness disparities using stored run artifacts, helping us detect which parts of the workflow might have contributed to the fairness disparity. Fairness indicators is still early, and we're releasing it here today so we can work with you to understand how it works for your needs and how we can partner together to build a stronger suite of tools to support fairness questions and concerns. Learn more about fairness indicators here at our TensorFlow.org landing page. Email us if you have any questions, and the bit.ly link is actually our GitHub page and not our tf.org landing page, but check it out if you're interested in our code or case studies. This is just the beginning. There are a lot of unanswered questions. For example, we didn't quite address where do I get relevant features from if I want to slice my data by those features, and how do I get them in a privacy-preserving way? I'm going to pass it on to Miguel to discuss privacy tooling in TensorFlow in more detail. Thank you.
Thank you, Kat. So today I'm going to talk to you about machine learning and privacy. Before I start, let me give you some context. We are in the early days of machine learning and privacy. The field at the intersection of machine learning and privacy has existed for a couple of years, and companies across the world are deploying models to be used by regular users. Hundreds, if not thousands, of machine learning models are deployed to production every day. Yet, we have not ironed the privacy issues with these deployments. For this, we need you, and we've got your back in TensorFlow. Let's walk through some of those privacy concerns and ways in which you can mitigate them. First of all, as you all probably know, data is a key component of any machine learning model. Data is at the core of any aspect that's needed to train a machine learning model. However, I think one of the pertinent questions that we should ask ourselves is what are the privacy considerations that there are when we're building a machine learning system? We can start by looking at the very basics. We're generally collecting data from an end device. Let's say it's a cell phone. The first privacy question that comes up is, who can see the information in the device? As a second step, we need to send that information to the server. And there are two questions there. While the data is transiting to the server, who has access to the network? And third, who can see the information in the server once it's been collected? Is it only reserved for admins, or can regular suites also access that data? And then finally, when we deploy a model to the device, there's a question as to who can see the data that was used to train the model. In a nutshell, if I were to summarize these concerns, I think that I can summarize them with those black boxes. First, the first concern is how can we minimize data exposure? The second one is how can we make sure that we're only collecting what we actually need? The third one is how do we make sure that the collection is only ephemeral for the purposes that we actually need? Fourth,
when we're releasing it to the world, are we releasing it only in aggregate? And are the models that are we releasing memorizing or not? One of the biggest motivations for privacy is some ongoing research that some of my colleagues have done here at Google. A couple of years ago, they released this paper where they show how neural networks can have unintended memorization attacks. So for instance, let's imagine that we are training a machine learning model to predict a next word. Generally, we need text to train that machine learning model. But imagine that that data or that corpus of text has, or potentially has, sensitive information such as social security numbers, credit card numbers, or others. What the paper describes is a method in which we can prove how much is what's the propensity that the model will actually memorize some data. I really recommend you to read it, and I think that one of the interesting aspects is that we're still in the very early days of this field. The research that I showed you is very good for neural networks, but there are ongoing questions around classification models. We're currently exploring more attacks against machine learning models that can be more generalizable and used by developers like you. And we hope to update you on that soon. So how can you get started? What are the steps that you can take to do privacy machine learning in a privacy-preserving way? Well, one of the techniques that we use is differential privacy, and I'll walk you through what that means. You can look at the image there and imagine that that image is the collection of data that we've collected from a user. Now, let's zoom in into one specific corner, that blue square that you see down there. So assume that we're training on the individual data that I'm zooming in. If we train without privacy, we'll train with that piece of data. However, we can be clever about the way that we train a model. And what we could do, for instance, is just let's flip each bit with a 25% probability. One of the biggest concerns that people have when doing this approach is that it naturally introduces some noise. And people have questions as to what's the performance of the resulting model. Well, I think one of the interesting things from this image is that even after filtering or flipping 25% of the bits, the image is still there. And that's kind of the big idea around differential privacy, which is what powers TensorFlow privacy. As I said, differential privacy is the notion of privacy that protects the presence or absence of a user in a data set. And it allows us to train models in a privacy-preserving way. We released last year TensorFlow Privacy, which you can check at our GitHub repository at github.com/tensorflow/privacy. However, I want to talk to you also about some trade-offs. Training with privacy might reduce the accuracy of the models and increase training time, sometimes exponentially. Furthermore, and I think more worryingly, and tied to what Kat's talk, if a model is already biased, differential privacy might make things even worse, as in even more biased. However, I do want to encourage you to try to use differential privacy because it's one of the few ways in which we have to do privacy and ML. The second one is federated learning. As a refresher, TensorFlow Federated is an approach to machine learning where a shared model or a shared global model is trained across many participating clients that keep their training data locally. It allows you to train a model without ever collecting the raw data, therefore reducing some privacy concerns. And of course, you can also check it out at our GitHub repository. This is kind of what I was thinking mentioning about TensorFlow federated learning. The idea is that devices generate a lot of data all the time, phones, IoT devices, etc. Traditional ML requires us to centralize all of that data in a server and then train the models. One of the really cool aspects about federated learning is that each device runs locally only, and the outputs are aggregated to create improved models. Type of setting or allowing the orchestrator not to see any private user data. TensorFlow federated, as I was as a recap, allows you to train models without ever collecting the raw data. So if you remember the first slide that I showed, it really protects the data at the very edge. In terms of next steps, we would really want you to reach out to TF-privacy. We would love to partner with you to build responsible AI cases with privacy. As I said earlier, we're in this together. We are still learning, the research is ongoing, and we want to learn more from your use cases. I hope that from the paper that I show you, you have the sense that keeping user data private is super important. But I think most importantly is that this is not trivial. The trade-offs in machine learning and privacy are real, and we need to work together to find what the right balance is. And last is Masoud to tell you more about TensorFlow Quantum.
Good evening, everyone. I'm Masoud Mohseni, a research scientist at Google Quantum AI Lab. I would like to thank the organizer for invitation and making this live stream presentation happening today. Today, I'm going to announce the launch of TensorFlow Quantum, which is an open source framework for quantum machine learning. I would like to mention that in this talk, I do not assume any background in quantum physics or quantum computing. I would like to start with a famous quote from Richard Feynman that he made in 1982 that is considered as the first deep observation on computational power of quantum systems. He said that nature is unclassical, damn it, so if you want to make a simulation of nature, you better make it quantum mechanical. So, of course, we should know that machine learning is not about exactly simulating systems, but has ability to learn a model of system and predict systems behavior. So I would like to rephrase Feynman's quote as nature isn't classical, damn it. So if you want to make a model of nature or learn a model of nature, you better make it quantum mechanical. So with that in mind, we developed TensorFlow Quantum, basically as a toolbox to model natures and also artificial quantum systems. So what are the main objectives for TF Quantum? The first one is a software framework for hybrid quantum classical machine learning under TensorFlow and Cirq. And it allows researchers to perform fast prototyping, training, inference, and testing of quantum models for quantum data, which can reduce the prototyping time from weeks to hours. Also, it can help machine learning and quantum computing researchers to discover new algorithms for near-term devices or ultimately for fault-tolerant quantum computers once they become available. So, for people who have no background in quantum physics, I would like to make an introduction to quantum mechanics, quantum computing, and quantum machine learning in just one slide. So, are you ready? So this is the setting that we want to discuss. This is known as a double-slit experiment, and it's at the heart of the quantum mechanics. So let's consider that you have a ball machine. If you have played tennis, you know that how it works. You can set it up to send random balls. And if you have a wall with two slits, so some of the balls can go through the slits, and you have another wall or a screen, you can detect where these balls are hitting. So what are your expectations of the probability distribution that balls can hit the screen? So there are two possibilities. Balls going from the top correspond to orange slit, and you see a curve, a bump correspond to that. And there is another one for if they go through bottom slit. And the joint probability distribution is just summing over all two events. That's all you need to do. So what happens if the source for these particles is quantum mechanical. So assume if you have electron gowns that sends electrons, or if you have a laser to send photons, these are the particle of light. And if you have like a double slit setting, and double slits are obviously way smaller, and then you have a screen and you want to see where these particles are hitting. And now you can see that there is going to be an interference pattern emerging that is very bizarre. So here, instead of that Gaussian distribution right in front of each slit, you have this interference pattern that sometimes even right in front of the slit, there is zero chance of getting a particle. And so this was very puzzling for physicists back more than 100 years. And until they realized that actually there is a quick fix to this. All you need to do is just generalize the classical probability distributions to quantum. And for that, you just attribute a probability amplitude instead of a probability, and then that's a complex number. And so for two events, you have to just add them up and then square them. And when you square, there's a new term appearing. Instead of like the probabilities of getting through the slit top or bottom, there's the interference term. This is the third term. And this is related to the relative phase between these events. And you can manipulate this, and by manipulation of that, basically you can do computation. That's the core idea about quantum computing. And how do you do that? You place a stack of the walls at various different distances, and you place the slits at various different locations, and you set it up to sample from a probability distribution. So you create a constructive interference pattern to generate distributions that is the desired outcome. Now, that's basically is quantum computing. So congratulations, you've learned how quantum computation works. So let's look at a specific example that's pretty interesting. If you have random walls separated in different places and random slits located in these walls, you get a fancy probability distribution and is known as a Porter-Thomas. Means that it's like you have basically a quantum chaotic system. And this is sampling from the distribution of the system is exponentially hard classically. And this was at the heart of the quantum supremacy experiment that we announced last year. Basically, this is the rich computational setting already. Of course, that particular setting is not scalable, but that's a technical detail. All I want to say is that you can basically even set up a quantum machine learning on this. So how do we do that? We parameterize this arrangement. So we allocate or attribute parameters to each slit's location, and then try to learn to generate an desired output probability distribution function. Or iteratively learn to create a set of solutions that are the correct solution to a computational problem. And that's at the heart of the quantum machine learning. So you just basically learn all the concepts I want to introduce in this talk, except this setting is not scalable, so the rest of the talk is about a scalable implementation and how we can code it over TensorFlow. So to push the analogy a little bit further, you have to think about generating or engineering these interference patterns is like generating sound waves. It's like you are composing and playing music. And so there are certain strings, and the strings here becomes qubits. And instead of the note, you have quantum gates. Here is like a 2-qubit gates illustrated here. And instead of the musical instruments, you have this control microwave electronics, where you can generate electrical waves that generates these probability distributions that correspond to the wave nature of the particles. So we did this at Google. So over past 5-6 years, we have developed these superconducting technologies that you can fabricate these qubits at a scale. So this is a particular picture of a 1D arrangement of this superconducting qubits that could be a ring. And there's a pair of electrons that it's a current in that qubit that can go either clockwise or counterclockwise. But when it's quantum mechanical, it can be in superposition of both direction and goes in both ways. And this is like going through, the particle going through a slit at the same time. And you can control it here with the electrical gates. And this has to be low enough temperature for this superposition to happen. That's below a critical temperature of superconductivity. That's the reason we place it in a dilution refrigerator at 100 millikelvin. So we use that device with a 53-qubit processor to implement a set of random quantum gates, and showing that it's very hard to sample them classically. So let's back up a little bit and see what are these quantum bits. Quantum bits, basically, you can place and present them as like a vector in a Bloch sphere. So basically, if you consider this as a globe, if it's a classical bit, it's either pointing at North Pole or South Pole. For a quantum bit, it can be any point on this globe. So there are certain properties of classical bits that you can always, they always have a value of 0, 1. It can't be copied. Their state doesn't change if they are measured. And measuring one bit doesn't affect other unmeasured bits. And none of them actually in general works for quantum bits. So the challenge is how we can actually manipulate quantum information and how we can do quantum computation. So in order to do that, you can build arbitrary single qubit operation by just rotations around two fixed axes. And this can make a rotation anywhere in that globe, basically. And to do arbitrary universal quantum computation, all you need to add is to add a single non-trivial two-qubit operation, which is like here is C0. That means that if the first bit is 1, the second one is flipped. And understanding quantum circuit as like composing music is like there are these different strings correspond to qubits. So they're placed in a space, and in time you print the kind of things, operations you do, which has various different single or two-qubit rotation. At the end, you just measure them to create classical probability distributions. And that's always means for each bit is either 1 or 0, like classical bits. The thing is that these outcomes are normalized, so they sum to 1. So what is the landscape of near-term quantum computing today with this kind of technology? So basically right now, if to quantify computational power of this system, you have to consider two indexes. One is the number of qubits, one the quality of the qubits. So to have maximum computational power, you need to have high quality qubits, a lot of them. So in that shaded purple area, if you're there, it means that above the dashed line, basically things are not interesting because although you have a lot of qubits, they can be simulated classically, basically because the state of the quantum computer is localized. So it does not have this exponential power built into it. So below that dashed line, where we actually, on Sycamore, we observe this quantum supremacy, things becomes interesting. But to have fault-tolerant quantum computer, you need on the order of millions of qubits and tens of millions to do like something like Shor's algorithm that you can use it to basically decode crypto system. And it's for factoring large numbers to prime factors. But that's kind of one extreme point. In near-time quantum devices, you can actually think about on the order of tens to thousands of qubits. Still, there are potential opportunities to do something interesting like quantum machine learning that cannot be classically done, especially when you want to analyze or distill quantum data. And this is where TensorFlow Quantum comes in as a toolbox in this area that was not available, and we are introducing it this week. So how can we do machine learning over these parameterized quantum circuits? So to see a particular analogy, you have to notice that when you print this kind of unitary operations or random rotations in a space-time volume that you have, this is a kind of continuous parameterized rotation which mimic kind of classical circuits like deep neural networks that map certain input to output. So that's the reason for the term quantum neural networks that you might have heard. But how do we create these parameterized quantum circuits? Let's look at a concrete example. So we use here SIC. This is a toolbox introduced by a team for simulation of quantum circuits. So we import SIC, we import SymPy, and next we write a parameterized quantum circuit for this particular processor on the right, which is Sycamore, which is basically the SIC here in this setting is like acting as a quantum computing assembly language. We will use SymPy for adding symbolic parameters to our circuit. We define a qubit for our circuit using the SIC qubit, grid qubit command, which places a qubit on the corner here. This command can take coordinates of qubits on the grid. We place on the corner at 0, 0 coordinate. And then we can try to build a simple model. What would be that simple model? It's a parameterized quantum circuit with one gate using circ.circ. And then it's just a rotation by an angle theta about some y-axis of the qubit. To simulate the circuit, we actually need to attribute values to this symbol theta. This can be done by circ parameter resolver. And then we pass the circuit to a circ simulator object that can obtain the resulting output vector. So the output is actually a vector that just spit it out. Now, all we need to do to get the classical values from this wave function is to define a measurement. Here we choose a standard Pauli-Z operator which measures if the qubit is 0 or 1. The expectation value of the measurement is obtained by calling the expectation from wave function command on the simulator output. So how can we do machine learning on these finite space-times that we have available? So that was an introduction to SIG to just set up a parameterized model. But you have to notice for quantum machine learning, we should upload the data. Basically, we have to prepare it on the fly. This is the first part of a circuit. This is a 2D array that you can see. That first part is like basically generating the data on the fly. And second one is the parameterized circuits to try to learn it iteratively using measurement outcomes. So I mentioned quantum data. One might ask, what are the possible sources of quantum data? Basically, whenever you have a quantum computer, the output states of a quantum computer is quantum data. So you can use quantum machine learning for verification, doing inference over that output, and discover new algorithms. In particular, for simulation of chemical systems or simulation of quantum many-body systems. In particular, when we have this quantum matter near a quantum critical point, the entanglement or these correlations diverges exponentially. And so it becomes very hard to simulate them at that point. So what are the other cases? Are quantum communication networks, basically in quantum repeaters, quantum receivers, purification units. Basically, when you have data in communication networks, the networks are noisy, and you have to distill and improve it, improve the quality, and you can machine learn that. You can improve quantum metrology, which is like sensing imaging, basically high-performance measurement, or also control quantum devices. This is important for near-term devices to avoid, or mitigate errors. The simplest possible case for quantum data is just for a single qubit. Basically, you can have two clouds of data for the blue and orange correspond to two vectors, pointing in two different directions. But the things could be noisy. So it's when you have a data set, it could be any point near to that direction, but not exactly there. So the question is that if someone gives you that data, can you do a binary classification? And this is the examples, the hello world examples. I'm going to walk through it today. So as a concrete algorithm for doing quantum machine learning is variational quantum algorithms. Basically here we have two different co-processors, a CPU and QPU, that talk to each other. What happens that QPU, you run it, you collect some classical distribution of data and just pass it to CPU to come up with better suggestion for the parameters. And you do this iteratively to converge. And this is basically the iterative quantum classical optimization. But you can do more interesting stuff. Why not just combine quantum classical deep neural networks to build hybrid models? Here, you use the best of both models to increase or develop richer representation to capture some unknown data. And also, you can improve generalization. But how do we do that? We know already TensorFlow is one of the most used machine learning platform, and Circ is also one of the widely used circuit simulator for quantum circuit. Can we combine them, and what are the challenges for that? Once you start to looking into this problem, you realize there are certain technical hurdles. For example, quantum data cannot be imported, so you have to generate it on the fly. And also, you need to have both data and the models are layers in these quantum circuits, and you have to basically have a way to build these highly non-trivial computational graphs that are dynamic. So The other hurdle is that you need to pass this the quantum program to a QPU at one time. So you cannot just do computational graph, do measurements, and just pass it. Every time there is a delay, there is a latency between QPU and CPU. Because QPU works at a few microseconds, including measurement, and there are other issues with sending batches of jobs to realize many parallelized quantum circuits. And considering all those hurdles, we arrived at 4 design principles. First, we have to support differentiation of quantum circuits and hybrid backpropagation if you want to build hybrid models. Also, the circuit batching, which is, we mean that we have to be able to generate quantum data on the fly and train over so many different quantum circuits in parallel. Also, there is an issue that we need to be back-end agnostic. What it means that we should be able to switch from a simulator to a real device with few changes. So especially for theorists, so they can try a lot and then they can compare their simulation against an actual hardware real output. So, and the final principle is the minimalistic nature of our approach, is that we want to build a bridge between circuit and TF, not necessarily to reinvent the wheel. So we don't want to force the developer to learn new toolbox that is different, so much different from TF and circuit. So with that, we arrived at this software architecture. It's basically very simple. We map everything to tensors, and then we use this kind of ops on a TensorFlow framework to calculate our classical property distributions for the output. So basically, here you can see an example that a circuit can become a tensor. The parameters that describe a quantum circuit is a tensor, or Pauli operators are tensors. And also, we can have, from some ancestry nodes, getting some particular suggestion for the parameterized value to instantiate that, and then becomes the operations that you calculate the expectations, and then you can feed forward it to other nodes in the computational graph. So with that, we can look at the software stack as a whole. So at the user interface, there are 2 sets of data. Data could be classical or quantum, so the TF quantum now support quantum data. But the interesting thing is that the quantum data, as I said, it's like either circuits or operators, but you can map everything to tensors and then use a standard TF layer, TF Keras high-level layers that you can manipulate them. So below that, you can see these TFQ layers and differentiators, and just below that is the TFQ ops that they can run a simulator like Circ, or this more high-performance simulator that we just launched this week, as known as QSIM. Or you can run it on actual hardware, which is QPU. The classical part of the model can be run on CPU, GPU, or TPU, as a standard TF basically framework allows you to do. So to see a particular concrete suggestion to understand how this framework works is like looking at the pipeline for a hybrid discriminative model. Here you can see the interaction between different parts, like quantum data preparation, evaluation of quantum models, and then once you measure it, then the data becomes classical. Then you can feed it forward for further post-processing by a classical neural network. And then you can measure some cost function, feed it back to improve the parameter. Now you can improve the parameter of both quantum model and the classical neural network. And this is basically the nature of the hybrid model. So with that, we are now ready to do a hello many word examples. So this notion of many words, this comes from an interpretation of quantum mechanics known as many word interpretation. And I'm not necessarily identified with that, but it's kind of an interesting way of looking at the simplest possible case for analyzing quantum data would be a binary classification for a single qubit. So how can we do that? So here, again, as before, we import circ and SymPy and place qubit on the grid. We also import NumPy, TensorFlow, and TFQ packages. The first to do is setting up the labels and parameters for preparation of our quantum data. And then we, for simplicity here, we classify just 2 data points, A and B, correspond to 2 vectors on the block sphere. Then we can convert these vectors to tensors. And with that, we can we already generated our quantum data. Now we need to build our hybrid classifier. And in order to do that, we apply a core TFQ functionality, and that enables us to have an easy integration with TensorFlow. So the data inputs to our hybrid model can be specified using standard keras input object. The quantum portion of our model begins with a parameterized rotation about the y-axis, and then our hybrid model will learn to discriminate to the states by optimizing the theta parameter. To calculate the loss function, to basically learn this, we need to convert the quantum states into classical information. We can do this by making a measurement along the z-axis, and we embed our quantum model and measurement into a keras model. We use the TFQ PQC layer, and this layer enhanced from the TF keras layer so it's compatible with keras API. For the last stage of the classifier, we attach two basically unit dense layer with softmax activation. And then the layers are ready to basically use the result of measurement to predict the probabilities that the input data point is either from class A or class B. To train the model, we wrap our classical and quantum layers in a keras model. The weights in the dense classical layer and the parameters in the quantum models have both updated using Adam optimizer with the loss defined with the categorical cross entropy. We see that the loss is quickly driven towards zero during the training. Now we can apply this classifier that we built for distribution of the quantum data for a single qubit that I mentioned. So we can give this model quantum data points, perturb from training data points to see if this model can actually generalize, because the actual, that example was a bit artificial in a sense of a fixed data point, quantum data point to a fixed direction A and B. Now using the standard keras model, we can predict the function and see that the noisy samples are categorized with enough accuracy. So basically, this has been a very long journey, and we had a big team to be able to bring this up to you. And we would like to thank our colleague in our team, in particular the quantum team. We had contribution from X, Volkswagen, and in particular University of Waterloo. I want to mention significant contribution from Michael, Antonio, Guillaume, and Trevor over the past 2 years. And we will be excited to see what you can do with this, and we welcome your contributions. So you can dig deeper by going to the website, tensorflow.org/quantum. Also, you can look at our archive paper, which provides a detailed overview of the entire framework and also a lot of quantum applications that you can work the details in the Colab that are available in the TF Quantum website. Thanks a lot for your attention.
Thank you, Masood. And thank you, everyone, for joining us. With that, this is the end of all the presentations and demos from today. I'm Manasi again, and a big thank you to all of our speakers and staff and TensorFlow team, and more importantly, all of you for joining us for this very first virtual live stream only TensorFlow Dev Summit. We are going to make all of our presentations and demos available online on YouTube channel. So also, don't forget to check out our blog as well as Twitter account. And with that, keep those tensors flowing. And I want to take a short break and basically show you some highlights from today. Thank you.